Hello everyone, welcome to Intellipaat's YouTube channel. This video is a full course on big data and its related technologies like Hadoop, Spark and Scala. Now let us take a look at the agenda for this video. Firstly, there will be an introduction to big data Hadoop, followed by problems with big data, followed by why Hadoop and Hadoop ecosystem. And then we'll move on to some of the core concepts of HDFS, followed by HDFS components like nodes and blocks, followed by HDFS Workflow and MapReduce. And then we'll take a look at a quick hands-on on HDFS, followed by a quick installation guide for Hadoop and some of its basic commands. After this, we'll move on to Introduction to Hive, and then we'll take a look at basics of Hive and workflow of Hive. Then we'll move on to Introduction to Spark, followed by Spark and Hadoop ecosystem, followed by the Spark architecture, and finally we'll be having a look at a quick installation guide for Spark and some of its basic commands. Now, before we begin, please make sure that you subscribe to our YouTube channel and hit the bell icon for regular updates.
So fine. So what do you know about big data? So just to quickly start with, like what is this term? What does this term mean to you? What do you actually know about big data? I simply say that this is big data. What do you actually mean by it? Okay. So most of you have answered that, saying that okay, this is something to deal with the large amounts of data sets. So what is the problem that we're gonna have with large amounts of data sets? Okay. So now, what are the problems that we're gonna face with having large amounts of data sets? This is my question. So some of them said that it's cannot be stored in the regular machines. Okay, so we'll go back to the previous question. What is this big data? So definitely the term itself suggests that it's something to deal with the large amounts of data sets. So in addition to the size of the data, we also consider the type of the data. We also consider the speed with which it is getting generated, and we also consider the need for such data sets, right? So we are saying that it is large amounts of data sets. Where is it coming from? First thing, right? So why is this coming from? I mean, why is this coming in such huge amounts? And what is the need for you to store such large amounts of data sets? So if there is no real use, why do you even have to think about storing such large amounts of data sets? First thing, right? And with what speed it is getting generated, right? So it is generating at some 100 MBs per second. I mean, ideally it won't, but okay, 100 MBs per second. So you should be able to capture it with the same amount of speed, right? So it is getting generated at 100 MBs per second, and you are capturing it at 10 MBs per second, let's say. So there is definitely a lag. There is definitely a loss of data, and you are kind of getting lag. So you should also be able to consume the data with whatever speed it is getting generated. So that is one problem. So the size is definitely a problem. So what happens when the size increases? The storage problem will come, right? So in your traditional systems, you are not used to handling such large amounts of data in terabytes, petabytes. You generally don't design the systems for these amounts of data sets, right? So I'm talking pre-Hadoop days. So before Hadoop coming into existence, this is what the challenge is, or this is what the scenario is, right? So we were not used to handling such petabytes of data, definitely. So the problem with the size is definitely with the storage. I mean, we don't have the enough systems or enough hardware storage which could accumulate such large amounts of data sets. And the problem with speed is also the technology again. Like, what technologies are you going to use to capture this data that is coming with high amounts of speeds? And what is the other problem that I was talking about? The type, right? So what are these types of data which I say? When I say types of data, what does this actually mean? There are some tools which you use for storing the data, right? Already you've been using some tools like Oracle, PL/SQL, or the Postgres, or what else? You have MySQL, right? So all these tools are meant for storing a certain amount of data. What type of data are these going to store? It's definitely structured, right? So you cannot store unstructured, or you cannot store semi-structured data in a Oracle database. So we are used to mostly dealing with the structured amounts of data sets. Can anyone name me the unstructured data processing tools? Okay, interesting answer. Notepad. Okay. Anything else? I mean, how do you store this data in Notepad? How do you retrieve it? How do you kind of process it? I'm telling basically you should be able to store it. You should be able to query the results, and you should be able to kind of transform the data within it. So, not completely aligned with your answer. So, any other answers? Cassandra, MongoDB is a better example. So, have you heard about MongoDB? It's a document database, right? So there are some tools so which are not known or which are not in use mostly because in earlier days it was completely structured data that we talk about. So what we have is a structured data in terms of rows and columns. You just create the databases, create the tables, and align the data to those tables. So that is a problem. So suddenly the growth of this unstructured data or semi-structured data has increased a lot. And what has actually comprised for this growth? Why is that there is a lot of change, or why there is a lot of increase in the unstructured or semi-structured data? One simple example or one known example for all of us is kind of a social media, right? So forget about now, just think about around 10-15 years back. So do we have Facebook? Do we have Insta? Do we have what are the other tools you use? WhatsApp, right? Do we have all these things? No, right? Yeah. So the usage of these tools has increased drastically. The number of Google hits have increased. The number of people using the Gmail, using the social media accounts have increased, and there is a lot of digital data that is getting generated now. So where does all this data go? For example, you take Facebook. You liked some page, or Insta. You liked some image. You have the Snapchat. You upload some pictures, right? So what is a picture? It's some kind of an unstructured data only, right? So where does all this data go? You doing some activity on a social media account is all getting stored somewhere, right? So definitely, you whatever the likes you do, whatever the activity, or whatever the comments you post, whatever the content you share, everything is generating some amount of data, right? Let's say we take a better example, Amazon. You log into Amazon portal, you search for certain records, you search for certain products, right? So you search the product, you log into the account and you search the product, and next time you log in, you will find some suggestions, right? So how are those suggestions getting generated? Depending on your previous search, it is trying to identify your interest. Okay, if you're searching for an iPad, okay, so what are the other products which are related to the iPad? Something like a two-in-one laptop, which is Microsoft Surface Pro. It's going to give you a suggestion saying that okay, so iPad is only meant for this kind of activities. We have another product, Surface Pro, which can do both, which comes with a keyboard, which comes with a pen, and all that stuff, right? So this is some kind of a suggestion which it is giving based on your search history. And even when you log into the Google, or when you go through some other social media accounts, you kind of we kind of getting this pop-ups with the products that you have searched for, right? So how is that linking happening? I mean, how is that even linked to your social media account? So there's definitely some kind of activity that is happening beyond your control, I can say, right? So everything is being tracked. Your data, whatever the records that you search for, whatever the products you search for, is being tracked. It is being analyzed, and based on that, it is being used to give you a better experience, I can say, right? So why are you getting the suggestions? I mean, if I'm looking at the suggestions and I'm finding the product which I'm actually looking for, it's good for you only, right? So that is kind of increasing the user experience. So all these companies or all these products that you are using is kind of increasing the product experience. You can log into Facebook, there are a lot of friend suggestions that you get, so you might find a friend which you have known, right? So these are all kind of activities which has been increased a lot, and that is actually being comprised for these unstructured and semi-structured data. That's what I'm trying to come up to. So definitely there is an increase in the rate of this unstructured data, and definitely there is a need for you to process this unstructured data or store this unstructured data in a proper way. So that is what some of the problems, I can say. These are all some of the problems that we have with the data, with this big data kind of a tool. So we should have some technology which should pretty much store any amounts of data, at least with whatever the questions that we have now. So my technology should do what? It should store any amounts of data. It should not have any limitations to the storage. So if you're getting 100 petabytes of data, you should be able to capture it. So right, so that is how I have to design my new system. And then I have to capture the data with whatever the speed it is generating. So you should have some tool which should capture the data with whatever the speed the data is getting generated. So what do we call this activity? A streaming activity, I can say. Have you heard about this term, streaming, data streaming? So there is a match that is being happening on some other state, some other country, and you're able to stream the data, stream the content within seconds of time. There is definitely a lag, some seconds of lag will be there, but you are able to stream it near real time. Okay, so we call this term near real time. So there is no technology or no tool real time. It's all a near real time procedure, right? So the match which is being telecasted in some other country is being viewed here within seconds of time. So how is it done? You are streaming the data continuously from the source location to the destination location. So source is where in the country where the match is being held on, and the destination is you being a user. Okay, you can log in from any particular location. You can log into so and so application, Hotstar or whatever, and you can stream the data real time and near real time. So these are some of the tools, I can say, right? So you should have a technology. You should build a platform which should be capable of streaming the data in a near real time procedure, right? So you should be able to capture the data with whatever the speed it is getting generated without any loss of the data. Then what is the other problem that we have been talking about? Types, right? So there are different types of data. So whatever the platform that you are building, you should be able to capture the data with whatever the type it is coming. So if it is in a JPEG format, you should be able to store it. If it is in a .txt format, you should be able to store it. If it is in a .csv, .json, avro, .parquet, whatever the format it is going to generate, you should be able to capture it and store it and process it. Okay, so these are some kind of expectations that I have from the platform now, right? So we have seen what are the challenges, some of the challenges, I can say. We have seen some of the challenges, some of the major challenges, and we also have some idea on what my platform has to look like, right? So it has to store any amounts of data. It has to capture the data with whatever the speed it is generating, and it also has to store any type of data, right? So this is pretty much my big data, right? So the tool which is being used, the platform which is being used to analyze all these kind of challenges is your Hadoop. Okay, so Hadoop is a combination of multiple tools together, which pretty much solves all these problems, all these challenges that we are facing in the real-time scenarios. Are we clear? Are we clear with the introduction? What is Hadoop? Why do we need it? What is it going to provide us? Are we clear with that piece at least? Any questions? Or any deviations with whatever you have in mind and whatever I'm teaching? So, what is big data? We at least had some non-theoretical or non-technical definition, right? So something which is beyond the capability of the existing storage systems. We call that as a big data, which comes with some speed, which comes with whatever the type and all that. You can frame it with whatever we discussed. Okay, so that is going to be my big data, right? So firstly, what is data? There are different types that we have seen: unstructured, semi-structured, and structured. So structured, you must have known it already, which can be stored or which can be given some schema to it. You can give some structure to it, which comes with a row and a column definition. You will be able to store them in the databases. And the unstructured or semi-structured data is a JSON, XML, CSV. We have other such formats also. And unstructured, you have this images data, video data, uh, PDF, document related data. Everything comes under the unstructured data. So have you heard about, or have you known any tools which actually can read a PDF, or which actually can read a document or MP3 or whatever, PPT? Have you seen any tools by yourself? Excel. Someone is giving me some kind of an interesting answers actually. So Notepad is one and Microsoft Excel is one. Okay, so what do you do with Excel? How is it unstructured data processing tool? So when I say unstructured data processing tool, I should be able to store it. Okay, fine. I'm happily accepting that Excel can be used to store the data. And how can you process it? How can you kind of uh, uh, transform the data? You write some code or you write some program and you transform the data, right? And that's gonna have some limited number of rows at least, anyways, right? Excel is again, I can call it as a structured data processing tool itself, structured data storage only, not unstructured, right? So when I say PDF document, I have a .pdf file. Okay, so most of you have seen the .pdfs, right? So I have a .pdf file. Have you seen a tool which can read the data of a PDF, which can analyze the data in a PDF, whatever it could be, a text data or an image data? It can have any data, right? It can have some text, it can have some paragraphs, it can have some table, and then followed by an image, and all that. All that will be part of a PDF. So have you seen any tool which can actually do all these things? Store a PDF file is one, analyze the data of a PDF, analyze the text of a PDF, analyze the image of a PDF, and all that. Have you seen this? Or can you deal with it? Okay, let's say we don't have a tool at all, but can you handle this by yourselves? How many of you are familiar with Python or any Java uh, programming? Existing knowledge on Java or Python? So there are some packages, there are some libraries already developed. Okay, so in Python you have PyPDF, you have Tesseract, right? So these are all some kind of pre-built libraries which can help you deal with these kind of data sets, reading a data from a PDF or some kind of an extension .bam, .sam, or different extensions you might have. So there are some libraries already available, so you can do it by yourself. You can code some program, you can use that library, and you can import it. You can import the package and build some programs, and you can do it by yourself. That's what I wanted to say. So, okay, so that's what we're going to do in Hadoop as well. So you import the existing packages, and you using them, you are going to build some kind of a code to read such files. Okay, so that itself is going to be unstructured data processing. We are not going to do it very extensively, and most of the are not many clients will have the data coming in a PDF or a doc or an MPG or JPG, right? So it's very limited. There are very specific clients which are mostly related to healthcare, I can say. Okay, so which I have seen myself. So healthcare clients will have very odd formats of data. Okay, you I mean, when you look at the data, you don't have an option to read the data also. So what do you do generally? You open a PDF file, or if you generate some file in, if you get some file in some dummy format, what do? You open with a Notepad plus plus, right? But even that is not possible. You don't have a proper reader also to read the data. So there are such kind of data coming in. You have this X-ray data coming in. You have this scans, different scans related, MRI related scans data coming in. So we have actually seen that kinds of data. So that is how the scenario is gonna be. You will come across different formats of data. Everything falls under the unstructured data format only. Okay. So fine, coming back to where we are, when we say data, there are the different types of it. We've seen what is the structured, semi-structured, and unstructured, and then we'll see a little bit of a technical definition, I can say. It's a collection of extremely large data sets that may be analyzed computationally to reveal patterns, trends, associations, especially related to human behavior and interaction. So this is not a technical definition. This is just an introductory content. So where is this data coming from? The data from black box, the data from social media is pretty much accounting to what the big data is all about. And there are other examples also. This public data transport, the Google search engine data, a stock exchange data, or a power grid data. So everything falls under this big data, right? So now categorizing data as big data. So what is this 5 V's? Have you heard about this 5 V's of big data? Initially, when we learned, it was only 3 V's, I remember. Right. So later on, people started to name the other 2 V's as well. So now the documentations, everything were holding 5Vs. So I pretty much remember very strongly that initially when I got into this big data technologies, we were only talking about 3Vs. But that's fine. So let's see what are these 5Vs. These 5Vs, we can actually categorize them as the characteristics of the big data. Okay. So we've already seen 3 of them. What is it? Storage, which comes under volume. And what is the other one? Variety is the types of data. And what is the other parameter that we discussed? We discussed about storage problem. We discussed about type of the data problem. We discussed about one more. Speed. Speed is going to come under velocity. So what is the other two, like value and the veracity? So we will see what are these. So first thing is the velocity. So velocity refers to the speed with which the data is coming from. So generally, when we talk about big data, when we categorize this data into big data, one of the characteristics it can have is a velocity. So if the data is coming at full speed, then we can categorize that into a big data. So now when I build a platform, your platform should have the capability of capturing the data which is coming at high speeds, right? So this is my problem, this is my categorization, and this is my solution that I'm looking at. So with the help of the categorizations only, I'll be able to build my solution, right? So we have not yet built this solution of big data Hadoop. So we were only talking about what are these big data, what are the different characteristics that it's going to have, and when I'm building a platform, what I need to have or what I need to have in my mind so that I'll be building this particular platform, right? So now first thing I've categorized as a velocity. So if the data is coming with so and so amounts of speed, I'll categorize that as a big data. So now when I'm building the platform, I should be able to handle this challenge, right? So second thing is a volume. So when I have huge amounts of data sets, when the data size is very huge, so when do I say the data size is very huge? How can you even justify that, okay, this data is small, this data is huge? How can you categorize it? I mean, nothing technical, a simple understanding. Okay, let's say I have 100 GB machine, you have 1000 GB machine, and if I have to store 500 GB, for me it is huge, for you it is capable. I cannot say that it is a huge data, or I cannot say it's a big data. Agree? So,
Yes.
so when I say this volume, I mean, in terms of any other characteristics also. So when it becomes beyond the capability of the existing software that we have, with the existing technologies that we have, let's say I have a SQL or MySQL, or let's say I have Oracle database, right? So when it becomes beyond the capability of these known tools, these known technology tools, I consider or I categorize them as big data. If it is becoming beyond the capability of my existing tools and technologies, I categorize them as a big data, right? So when it reaches, I mean, when the size of the data reaches beyond the capability, okay, so let's say how do we categorize, how do we say that? We don't have exact numbers, let's say now. Okay, so what is my capability of MySQL and Oracle and all that, we don't know. So all of a sudden, when I kept loading the data into an Oracle database table, it became slow, right? So the query became slow, you are not able to perform joins, you are not able to perform select queries, even a simple select query is taking lots of time to generate the output. So that means it's done now. So I'm reaching the threshold level that I cannot store more amounts of data on it. So what do? You break that into two different tables and you store them. That again is going to be a challenge for you, right? So those are the things. I mean, when the size becomes beyond the reach of your existing tools and technologies, we categorize them as a big data. That's what I was trying to say. Now, variety, we know. What is a variety? The different types of data when you have structured, unstructured, and semi-structured. So it's not that we don't have the tools which can handle the semi-structured or unstructured at this moment, but it's the case where, see, for example, if the data is coming in a structured format, I'm using this tool. If the data is coming in an unstructured format, I'm using a different tool. It shouldn't be a case. I should have a single technology, or I should build a single platform which should not worry about the type of the data. Okay, if it is coming in a .csv extension, .pdf extension, .jpg extension, it does not actually have to matter. It just has to store the data with whatever the format it is coming in. So that's what my requirement is going to be. So this is my categorization. If the data is coming in different formats, in different types, with structured, unstructured, and semi-structured, when the size becomes huge on these particular varieties, we categorize them under this variety V of big data. Okay, then the veracity. So what do you mean by the veracity? Any answers? Or I can say it's going to be an grammar related answer. I mean, whoever understand these terms can answer this question. What does veracity mean? So the trustworthiness of a data, I can say in simple terms. So fine, your data is huge, it's speed, it's whatever the characteristic it can have. But how far is it trustworthy? How far is it accurate? Or how far is it, I can say, quality? So nowadays, when you talk about the data that is coming in simple terms, in known languages, let's say I'm getting some 10 million records from a source. Okay, you are a data engineer in so and so company. You're getting some 10 million records into the source from the source, and you're supposed to store them in so and so database. What are the things that you're going to consider? You'll definitely analyze. The first thing is that the 10 million records are not the purest data, or not the quality data or the accurate data. You may have to check for the duplicates first, right? It may have duplicates, or it may have some dummy records, right? Or it may have some null records, right? The ID is let's say the ID is what my most important thing. See, when I'm getting the data in a so and so file, if I have to store that data in a so and so table, I should be creating an ID column with some primary key element, and that's what my identifier, I can say, right? So when I dump these 10 million records into the so and so table, it's gonna fail because some of the records have null as an ID. You cannot definitely have null as an ID, right? It's not even pointing to any user. So that itself is a dummy record, right? So these are some of the examples that I'm saying. Duplication is one, null records are some one, and some of the records does not even exist or does not even come from this specific source. So you have to do this data validation or data filtering or data deduplication. So all this terminology we are going to use in real-time scenarios. So you have to first make the data accurate and then store it, right? So all these things come under this veracity component. So make the data trustworthy, make the data accurate, and all the procedures that you're going to do prior to giving it some kind of a storage is what this activities is going to talk about, right? So veracity is pretty much the trustworthiness of the data, how much you can trust it, or what tools you can do to filter the data, remove all the unwanted records, or pretty much make it accurate. Okay, and then the value. What do you mean by value? Okay, I'm loading some petabytes of data, 2 petabytes of data, 3 petabytes of data. I'm loading the unstructured data. Great. I'm loading the data which is coming at so and so speed. That's very great. But what am I doing with that data? What is the need for you to store that data? So ultimately, for example, you are working for an organization, you extracted the data from so and so source, you loaded it into a table, you designed it, you filtered it, you transformed it into a so and so nice table. What is the use of that table, let's say now? So if that is not giving you some amount of value for the company, what is the need for you to store that data? Right? So ultimately, any data that you capture or any data that you store has to give some value to the company. Amazon is capturing the data of a user. What is the value that it is generating? It has got a large amounts of user base. What is it doing? I don't. We don't know what it is actually doing, but it's earning a lot of money with your data, right? Or better example, Facebook. How many of you seen the discussion with? This Mark has attended some discussion with the U.S. Consulate, right? It's a very nice interview actually, right? So what are they doing with that data? Of course, in simple terms, they are giving you a better user experience. It's giving you search records, it's giving you the suggestions, it's keeping the track of all your order history. They're trying to build you a better user experience. Okay, let's talk all about the positives. So they're trying to build you a better user experience. Okay, they're trying to capture the data and they're trying to help you build a proper user experience. So that is one value that you are generating out of the data that they are storing, right? So similarly, a similar example, like you can say, so every company, or when you are dealing with such large amounts of data sets, ultimately they have to turn into some kind of a value. If they don't have a value, there is no use in storing such amounts of data sets. So the major characteristics for any data, it can be, I mean, need not be a big data. It's going to be a major characteristics is it should tune into a so and so value, some recognized value for the company, some useful information for the company, right? So that is the most important characteristics of any data that you're going to store. Agree? Are we clear with the 5 V's now? Any questions? So we have not got into the technical related stuff all this while, right? So it's only theoretical. It's kind of a nice story that we are discussing. Okay, so nothing technical. It's very generic, very basic. So any questions do we have? Shall we continue? No? Fine. So then, right. So we are getting into the concepts slowly. So we have discussed about the characteristics. We have seen what are the characteristics for a data should have. I mean, whatever the data that we are able to store, it should have so and so characteristics for it to term it as a big data. Now, what are the problems that we are gonna face with such kind of data sets? So we have already seen the problem with the storage. We've already seen the problem with the speed or the different types, right? So they are the need. Okay, I can say that's a pretty much the need for your new platform. So they should definitely have storage. They should definitely have speed. They should definitely have the uh, 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 capability to store any of the data and all that, right? So the categorization of problems with big data has been done into two different ways here. One is the hardware failure and the combining data. Let's read it what we have.
Just a quick info, guys. If you want to make a career in big data, then Intellipaat provides an advanced certification in Big Data Analytics by ENICT Council IIT Guwahati. It is taught by IIT professors and industry experts. With more than 10 years of experience, this course is designed to upskill and land your dream job. Now let's continue with the session.
So ultimately the problem is with the storage and with analysis part. Okay, so just to name it. So although the storage capacities of hard drives have increased massively over the years, access speeds, the rate at which the data can be read from the drives, have not kept up to the mark. Agree? So earlier, when we were, 10 years back, let's say, there were systems with 250 GB, 500 GB. Now we have systems with 1 TB hard disk, right? So the hard disk storage has definitely increased, I can say, right? We have already seen that. So the size of the data that you can store is kind of increasing, and you also have the hardware problems. That, I mean, you are having the necessary hardware to store the data, but the problem is with the speed with which you access. So in general, for example, which example do we have to take? Not get into the technicals of it. Okay, fine. Let's get into the details of it a little later. But in simple terms, see, it's definitely gonna take some time for you to store the data and for you to read the data from a specific hard disk. So how many of you have seen this memory processing, in-memory processing? How many of you heard about this in-memory processing term? It's very early to use this term, but that's okay. Okay. Have you guys used the transfer of data between one system to the other system, from one hard disk to the other hard disk? How much time is it going to take? let's say you're having some storage in a hard disk, okay, external hard disk. You're trying to transfer everything into your local machine, right? This is one scenario. And the other scenario is you have some data within the D drive and you're transferring the data to a different folder in the D drive. Which one is going to be faster within the local machine? Okay, so this is not a proper example, but a very known example, I can say, right? But when you are accessing the external hard disk, your transfer rate has been reduced drastically, right? So it definitely takes some time for you to read the data from an external hard disk. So that is what the problem is. So when you have the data on a hard disk, when you have the data on a storage, the time taken for you to read the data or even write the data into that hard disk is kind of a problem now, right? So you have a storage, fine, that's fine. You have 1 terabytes of hard disk, you have 2 terabytes, you have 3 terabytes of hard disk storage is available, but the problem is with the read and write speeds, right? So you're not able to store the data with a faster rate and moreover you're not able to store everything in a single data in a single machine, let's say, right? It has to be across different machines. So that is one problem. And combining data. So what do you mean by combining this data? So most analysis requires to combining data in some way. Data read from one disk may need to be combined with the data from any other 99 disks, challenging task for the distributed systems. So as we have come across the term distributed system, so how many of you know what is a distributed system? So in the previous problem that I was discussing about, I was telling that the storage problem has been solved. Okay, so we have the capability of the hard disks that they are increasing, right? The size of the hard disk is being increased, and we don't have a problem with the storage now. But the problem is with the data write and read speeds. So why am I saying that is we have we have a hard disk of 1 terabyte now. Okay, so for example, if I have a data which has to be which with a store which has with a size of 3 terabytes, let's say, what I'll do, I'll take 3 machines with 1 terabyte each, and I'll divide my 3 terabytes of data into these 3 different machines. That is my distributed storage. Instead of storing the entire data on one single machine, which is not possible, what am I doing? I'm dividing the data into multiple chunks of data and I'm storing it on different machines, right? So what I'll do, if I get 4 terabytes of data next time, I'll add one more machine. If I get 5 terabytes of data, I'll add one more machine to it. So what am I doing? I'm just increasing the number of machines in the network. What do we call this? We call this as a cluster, right? So what do you mean by a cluster? When two or more number of machines are integrated in a specific network, let's say. Okay, so both are connected to each other. When two machines are connected to each other, or when two or more machines are connected to each other, we call that as a cluster. Okay, so when I have 5 terabytes of data to be stored, it's not possible for you to store the entire data in a single machine. You cannot have a hard disk which is of 5 terabytes alone, right? So you'll find hard disks which are 1 terabytes or 2 terabytes. What do? You purchase different hard disks, you integrate them on a network, right? You put them on a same network, you connect with them with each other, and you distribute the data of 5 terabytes on this network. So now I have 5 machines with 1 terabyte each. I can store 5 terabytes of data. Tomorrow I get 2 more terabytes. I'll add 2 more machines to the network. So whenever my size of the data is increasing, whenever I'm running out of storage, I'll keep on adding new networks, new machines to the network. Are we clear with this? Right? So this is my distributed storage. So that is the reason why I said the storage is not a problem now. But the rate at which, the speed at which your data is being transferred from one machine to the other machine, or the speed at which you can read the data from the network and write the data to the network is kind of becoming a problem. So that is the reason why the second problem has come, the combining data. What do you have to do? Let's say, let's take this example. We have the voters list from 5 districts, let's say. Okay, right. we have the voters output. I mean, whatever the votes they have polled, we have the results from 5 different districts, right? So on the whole, it is around 10 terabytes of storage. Okay, whatever the data I received is around 10 terabytes, which consists of all the 5 districts related information. So now when I'm distributing the data across 10 machines, I'm distributed this so and so number of records into 10 different machines. So now when I have to calculate the winner, I mean, if I have to calculate the number of votes polled for each and every party, let's say I have got 3 parties, right? So for example, if I have to calculate it, what do I have to do? I have to read through each and every machine, read through each and every district. So which district has received which number of, how many number of votes, and how many number of votes have been polled for each and every party. 3 parties were there, 5 districts were there. So you just have to segregate the data on each and every machine, then go to another machine, then go to another machine, extract the data, and then you have to combine the data and find the final output. This is what I have to do. But how challenging is it? That is what the problem is, right? So when I'm not having a problem with the storage now. With the help of the distributed network, I'm able to store the data. But how do you combine the data from one machine to the other machine? That is what the problem is. If I have to do this use case, what I'll do, I'll collect the information from all the 5 machines, I'll combine them, I'll run some query on top of it. I have written some program, I'll run the program on that data, extract the output, and then store the data back to the existing machines. So this is what I'm going to do. That is what the problem is, right? So it's taking a lot of time for you to read the data from the machines and write the data to the machines. The read write time is what taking the time, right? So as we have solved one problem, it has brought us into another problem. As we have solved the problem of storage, okay, let's say I'm using the distributed thing, but what is it doing? When you have data, when you have the same file on different machines, which is broken into different machines, then you have to combine the data to do some processing. That's going to take some time. Agree with the challenges? Do you have any questions? Are we deviating anything? So let's go back to the solutions. Whatever the problems that we discussed, what are the solutions we're going to have? So the first thing, while we start using many pieces of hardware, the chance for one to fail is fairly high, and this might result in a data loss. A common way of avoiding data loss is through replication, creating multiple copies of data so that in the event of failure, there is another copy available. So this ultimately is coming to a solution named Hadoop Distributed File System, which is called as HDFS. And most of them call it HDFC, but it's not HDFC. We are more used to the HDFC term, but it's going to be a HDFS. Even now, I still hear people saying HDFC, but that's kind of funny. But it is gonna be HDFS, right? Hadoop Distributed File System. So we discussed about the storage problem, right? The first in the previous slide. What is the problem that we had? What is at least the solution that we gave? We were storing the data in different machines, right? In a network. So we had 5 terabytes of data, which is being distributed across 5 different machines. But in that case, what are the problems it can have? One simple problem which I can identify now at this moment. So there are other problems also, but one simple problem which we have identified in this case is loss of data. If one machine is lost, what happens to the data on it? The entire data of 1 terabytes is lost, right? So what are we doing with HDFS? In HDFS, there is a concept called as replication factor. What does this do is every data that you store in a machine, every block of data, I can say, every block of data that you store in a machine is duplicated and stored in other machine also. That means 5 terabytes has been divided into 5 different machines. Every machine will have some blocks of data inside it. So 1 terabyte will be broken into multiple small blocks of data, small boxes of data. So each block of data, when you are storing it in one machine, you will duplicate it and store it in another machine. So the question is, how many times you will be duplicating it? there is a provision for you to duplicate it once, or you can also duplicate it twice. That means the first scenario is you will not maintain any duplicates. The second scenario is you will maintain one duplicate of it. And the third scenario is you are maintaining two duplicates of it. In the first scenario, if I am having 5 terabytes of data, you are only using 5 terabytes of data, 5 terabytes of storage. In the second scenario, you'll be using 10 terabytes of storage. In the third scenario, you're going to use 15 terabytes of storage. Agree with this point? Because you're duplicating it, you're triplicating it. I mean, you're maintaining 3 copies of same data. In the second scenario, you're maintaining 2 copies of same data. In the first scenario, you're not maintaining any copy, right? So this is what your replication is going to tell. In Hadoop HDFS scenarios, the replication factor can be 1, 2, or 3. If there is 1, if you set the parameter as 1, that means it won't maintain any duplicates. If you set the parameter to 2, it will maintain 2 copies of it. If you set the parameter to 3, you will maintain 3 copies of it. So by doing this, as you have the same data available on some other machine also, in one machine or in two machines, okay, if it is two machines, it is more secure. So let's say if it is stored in one more machine, even if this machine is lost, you still can retrieve the same data from the other machine. Agree? Right? So if the replication factor is 3, let's say, if you have lost it in one machine, if you have lost it in two machines also, you still have it in the third machine. It's more secure. Right? So, but ultimately, what are we compromising on? We are getting safety, that's fine, but what are we compromising on? We are compromising on the storage, right? So instead of using only 5 terabytes of storage, we are now using 10 terabytes of storage for the same 5 terabyte of file. We are now using 15 terabytes of storage for the same 5 terabyte file. That means we are using more storage than what we actually need. But what are we getting? We are getting the security, we are getting the fault tolerance. That's what the term we are going to use. Even though the machines are lost in the network, we still have the capability of retrieving it. We still don't have any problem of losing the data, losing the actual data. So now if you look at, we've actually taken out the storage related thing. So now there is no problem at all with the storage. I can use any amount of storage. I can generate any amount of storage. Now I'm more focusing on the security of the data, right? So that is what my HDFS is going to give. It has taken the storage out of picture. It is more concentrating on the quality of the data or the fault tolerance of the data, right? So that's what the challenge. I mean, that's what your solution is going to be. So all your storage related solution problems will have one single solution, that will be HDFS, Hadoop Distributed File System. So that's not it, guys. There are other features also for HDFS. We will get into the details. This is just to show you some kind of a introduction, I can say. Okay, so this is one of the features that we have in HDFS. Okay, so all your storage related problems, whatever the problems that we have discussed about in terms of storing the data, storing the huge amounts of data, losing the data when you have data across multiple machines, everything will be solved in your HDFS related components. Now coming to the MapReduce, what do we have? There is some problem with the combining of the data that we discussed, right? So it provides a programming model that abstracts a problem from the disk's reads and writes and transforms it into a computation map and reduce over set of key values. MapReduce has a built-in reliability and interface where the mixing of map and reduce occurs. Okay, so there is a lot of technical terms in it. So in simple terms, I'll tell you this. So what is the actual problem that we had? We were having problem with the data that is residing on different machines. The same data, you have it on multiple machines now, right? So when you have to combine, you have to extract the data from the machine, combine it, do a computation, do whatever the auto calculation, and you generate the results and store it back to the nodes, to the machines. So what MapReduce has done here is you're not moving the data anywhere. The data is gonna sit wherever it is. What you will do is you will move your computation logic. So earlier, what did I do? I have written one program. So you gathered all the data from 5 different machines. You gathered all the 5 terabytes of data. You ran that program on that 5 terabytes of data. You extracted the output. and then you distributed the data again to those 5 machines. But now what I'm doing is I'm not gathering the data from any machine here. The 5 terabytes of data, 1 terabyte of data on each machine will sit wherever it is. But instead, I'll move my program, whatever the code that I've written, I'll duplicate this program and I'll submit this program to 5 different machines individually. That means the computation is happening inside the machine where the data is actually residing. You're not moving the data anywhere. The program itself is moving to the data. Data is not coming to your code. Code is coming to your data. Agree? That's the difference. So the computation has been moved to the data location. You do all the transformations or computations, whatever you have. You extract the result, only the result, right? Instead of extracting the entire 1 terabyte of data, you're only extracting the result of that 1 terabyte data. It's hardly going to be in KBs, right? So you extract the data, a result from all the 5 machines, and you combine the result and generate one final output. So how you're going to do that, how effectively you're going to do that, what are the different processes involved in it, we will discuss that later. But have you understood the core concept of it? So instead of moving the data from the storage locations, you are moving the code. The problem why we are moving the code is, see, data is 5 terabytes, but how much will my code be? Hardly MBs. Some 100 lines of program will only combine to 1 MB or 2 MBs at most. Not even 2 MBs. I mean, whatever the programs we write are going to be in KBs only, right? So instead of moving some terabytes of data, why do I have to move such amounts of data when I can move a simple KB of data to the machines individually? That's what I'm going to do here, right? So now the problem of combining the data has been avoided, right? So how am I going to do it? We will discuss that in detail, but this is what we're going to do. This is what we're going to do with the MapReduce. So your ultimate solutions will be, guys, for all the storage related problems, your HDFS is going to be a solution. For all the processing or for all the analytical related problems, your MapReduce will be a solution. Okay. So ultimately we have two components. One is HDFS and MapReduce. So these two will remain the core concepts of the platform that we are going to discuss is Hadoop. So Hadoop is going to have two core components. One is HDFS, Hadoop Distributed File System. The other is MapReduce. Are we clear? Okay. So we've seen the challenges. We've seen the solutions for storage, for analysis. And then what else? We've seen the HDFS and this MapReduce, what they are used for, right? So those two remain the core components. We also, in the initial sessions, we have seen the characteristics of the 5 V's of the big data, right? So now to start with, this is where we end up. Like, this is gonna be the platform to resolve or to take care of all the challenges that we have been facing with big data Hadoop, big data in terms of speed, storage types, all that. So how Hadoop is solving all the challenges that we discussed, we're going to discuss further. Okay. So to get a background, Apache Hadoop, it's now open source platform. It's under the license of Apache, so anyone is free to use. So Apache Hadoop is a platform used for storing big data across a spectrum of devices. This is done to help us process big data in parallel. It is made up of a distributed file system called HDFS and a computation layer called MapReduce, which is taking care of processing. It is an open source big data processing system for dealing with enormous amounts of data, and abstraction and facilitating the storage and processing needs structured, non-structured, simple programming models. So anything new from this slide? Anything that we need to discuss? I don't think so, right? Are we clear? Shall we move on to the next one? We pretty much discussed about everything and that is available. Yes, right? So this is for you to just go through the history of Hadoop. Okay, started at 2002, how it has evolved, what licenses it has gone into. It was with Hortonworks, Cloudera, MapR, and everything got merged to Cloudera then. and now it is available through the open source license of Apache. And there were 2 people of cutting, and Mike Cafferel are the people who have started it. Okay, fine. Thank you. So this is the history, guys, just for the information. So nothing in detail to be discussed here, right? So then the use cases Hadoop, we've listed some of the use cases, real-time use cases where people use Hadoop and what are the scenarios they use Hadoop in. So British Airways, we know what they are into. So using NOMI program, complete information of travelers was retrieved, such as when they are planning to travel, where they are planning to travel, and which is leading to the increase in sales and hence achieving the hike in revenue. So using Big Data Hadoop, they have gathered that information, and they have they have some of increased their revenues by gathering all the travel information, and that has used them in sales, pre-sales activities. And with Uber, with some 100 plus petabytes of data, which helped Uber in increasing their network to the countries, hence providing service with zero or negligible latency. And AWS, using Hadoop distributed computing technology, it has made access to large amounts of computing power to run data intensive tasks. Okay, so these are some of the use cases and why Hadoop is a solution. What does it provide? What are the different features of Hadoop? The first thing is the problem of scalability. So what does this problem of scalability mean? What do you mean by scalability factor? Anyone? Scalability. What do you mean by this stuff? No? Not heard about it? So scalability is the easiness of increasing or decreasing the number of machines in your cluster. Okay. So if I'm saying I'm scaling up, that means I'm increasing the number of nodes in the cluster. So I keep calling them nodes, guys, because we may have to quickly move on to this terminology. So all this while we have been terming each and every system or computer as a machine, but from now on we'll be calling them as a node. So every machine inside a cluster is termed as a node. Okay, so node, NODE. So when I'm saying that I'm scaling up, that means I'm increasing the number of nodes in a machine. I'm scaling down, that means I'm reducing the number of nodes in a machine. So this is the scalability. So these are some of the problems with the legacy systems. So the pre-Hadoop systems, whatever the existing systems that we have, these are some of the problems that we have, which Hadoop has properly overcome. So what does this scalability mean? Like they were not properly tuned for the scalability. They are not, the scalability feature is kind of complex in such scenarios, in such systems, which Hadoop has made it very easy. So what is the next one? Process only structured data. What do you mean by this? Earlier systems were only processing structured data, right? So the problem is like the size of the unstructured data kept increasing, and that is the reason why we were not able to handle the unstructured data with the existing systems. So that's the reason why we were migrating it into the latest machines. And the third problem is expensive. So why do we call this expensive? Anyone? No, nothing. So when we talk about expensive, so we can categorize them into 2 different sections. Okay, so we will keep comparing it with Hadoop solutions, and we'll see how it is different. So we know MySQL, we know Oracle, we know Postgres, we know Teradata. All these systems are the relational database processing systems, the legacy systems that we call it, right? So are they free to use? Some of them are. The MySQL is free; it's an open source. But when you talk about Oracle, the most used platform, Oracle, Postgres, these are not a free open source tools, right? They come with a license. So you're supposed to pay for whatever the services that you're using for. But on the other side, Hadoop is free of cost. You don't have to take care of any licensing costs. It's an open source solution. Now, when you talk about the other systems, we know there is a distributed mechanism available, right? So for storing the data, you're supposed to maintain the distributed structure. So when you have some 5 terabytes of data, you are dividing it into 5 different machines, and you're distributing the data into 5 different machines here. So when there is new data coming in, you keep on adding the new nodes to the machines, to new nodes to the cluster, right? So this is what we have been discussing. So this system is available in earlier days also, in legacy systems also. This is a procedure we are going to handle. And in Hadoop also, we were maintaining the same distributed mechanism. But how Hadoop is different? So when I'm storing 5 terabytes of data, that's fine. I'm maintaining it in 5 machines. When I receive 2 more terabytes, I'll add 2 more machines. When I receive 2 more, I'll keep on adding more and more machines. So what happens? The number of nodes in a cluster are increasing. Yes. So when the number of nodes in a cluster are increasing, the size or the price of each and every node in a machine is gonna accumulate, right? So the entire price of the cluster is kind of increasing. So the cost that is incurred for maintaining a single node inside a cluster is what we consider this as a the entire cluster price, right? So every node comes with a price. So for example, if you have to add a new node to the existing cluster, if there are 10 nodes in a cluster, let's say it's around 10,000 each node. So 10 into 10, like it's accumulating to 1 lakh. For example, there is another node that is being added, right? You keep on increasing the price, right? So adding more and more nodes to the existing cluster will keep on increasing the price, and that is why it is becoming expensive. But you may question me that because in Hadoop also we use the same technology. In Hadoop also we use the same distributed mechanism. In Hadoop we are kind of maintaining large amounts of data sets, and we are also maintaining the replicated copies, right? In the legacy systems, what we used to do, if 5 terabytes is my data, I used to maintain only 5 terabytes of storage. But in Hadoop, what are we doing? We are maintaining 10 terabytes of storage, 15 terabytes of storage. Why is it? Because of the replication factor. Agree? When the replication factor is set to 2, set to 3, for storing a 5 terabytes of data, I'm actually using 5, 10, 15 terabytes of storage. That's more and more number of machines than my legacy systems. But why Hadoop is not termed expensive? Any answer? Any guesses?
Just a quick info, guys. If you want to make a career in big data, then Intellipaat provides an advanced certification in Big Data Analytics by ENICT Council IIT Guwahati. It is taught by IIT professors and industry experts. With more than 10 years of experience, this course is designed to upskill and land your dream job. Now let's continue with the session.
You understood the problem that we are discussing? The question that we are discussing? Even with the distributed mechanism, even with the replication, we are still able to store it with less amount of cost. Any guesses? Right. So the reason is there is something called as a commodity hardware in Hadoop. Okay, so Hadoop is designed in such a way that it can also work with a commodity hardware. So what does this commodity hardware mean? So it's the cheapest hardware that is available in the market, I can say, right? So for example, in your existing systems, for designing your existing nodes in a cluster, you would need some high-end software. But whereas in Hadoop, you are not going to use any high-end software. The only component that we would need for your Hadoop cluster node to be is the RAM, the size, the hard disk size, right? So if I'm configuring a cluster, if I'm configuring a node in a Hadoop cluster, you just need a hard disk for it. You don't need any software allocated to it. There is some amount of minimum RAM that is required, of course, but no other additional software. It is the least, the cheapest hardware available in the market is what we call it as a commodity hardware. So by using such kind of machines, we were able to reduce the cost drastically in the cluster. So if other clusters were having a node which is of around 10,000 per node, if my cluster, my Hadoop cluster can have it only for 5,000 or 3,000, 4,000. I mean, these are not the numbers, but I'm just trying to show you the actual comparisons. Okay, so that is how by using the commodity hardware, we were able to reduce the cost of the entire cluster in your Hadoop ecosystem. So one thing is it is open source. That itself is reducing a lot of price in maintenance. And the second thing is by using the commodity hardware. You need not spend amounts on high-end machines. You just need a basic hardware that can store some amount of data in it, right? So by using this commodity hardware, you were able to accumulate more and more number of machines, and that is the reason why you're able to maintain the storage. I mean, you're able to negotiate, or it's almost negligible. The price that you are considering for storage is negligible, and that is the reason we were able to accumulate this replication as well. So we are not even worried about the storage now. With the help of commodity hardware, you are not even considering the price of the hardware. Your storage is coming at a very low cost, and you're able to replicate the data, and you're maintaining the security feature of it. You're maintaining the fault tolerance of it. Okay, so that is the reason we call it as a the other systems were called as an expensive. So cannot process huge volumes of data. That is one reason, the existing one. And cannot process heterogeneous data. So what do you mean by heterogeneous data? Any idea? Different types of data. Yeah, so with high variability or different types of formats, right? We call it as a different heterogeneous data. So Hadoop, I mean, existing legacy systems were not capable of handling such varieties or such variability of data sets or different types of data sets, right? Then why Hadoop? It is flexible. What is flexible in terms of user friendly? Someone said it's user friendly. Okay, we can consider it as user friendly, right? It's flexible to use, and fault tolerant. What is the reason for fault tolerancy? How did we achieve this fault tolerancy? Right. So through replication concept, we were able to achieve this fault tolerance by maintaining multiple copies of data, the same data. The third thing is scalability. You can scale up to any number of nodes, and you can scale down to any number of nodes depending on the requirements. So scalability is not a problem. You can keep on adding more and more machines to the cluster. High-speed data processing. So how this high-speed data processing is achieved? What are the tools comprising or which are contributing for this high-speed data processing? We will discuss. Like it is meant for high-speed data processing. MapReduce is one of the concept. Like it is processing the data with huge speed compared to the legacy systems. Then, so flexibility, we've seen the structured and unstructured data differentiation, and scalability. We know fault tolerancy, that is a replication, and high-speed data processing, that is achieved using this parallel processing. So it's almost like 10 times faster than the existing process. That is how we do this using the MapReduce. So we will discuss about these things in detail, the high-speed data processing. So that is the reason why we will quickly move on to the next one. Okay. So how this high speed is achieved? I mean, in general terms, you can also think about it. If the legacy systems were handling, you can take the same voters example, let's say, right? So the time that is consumed for you to retrieve the data from different nodes, gather them, combine them, and do the processing, do the computation, and retrieve or store the data in the so and so storage systems is kind of delayed process, right? It's taking a lot of time for you to combine. But whereas in MapReduce way of processing, what do? You, instead of moving the data, you move the code to the data, you move the program to where the data is available. That is the avoiding the data reads and writes. So you're not moving the data anywhere, that because of which your time has been reduced drastically. Okay. Then we have the comparisons with the Hadoop versus the relational databases. We have already seen some of them. So Hadoop is mainly used for it can handle structured, semi-structured, and unstructured data sets, whereas a relational RDBMS is the relational database management systems. Okay, all the structured data processing tools, Oracle, Postgres, MySQL will come under this RDBMS. Okay, if you're not aware of it. So it's only mainly used for structures of data, structured data, and the data size it can handle is in terms of TBs and PBs. We are not gonna talk in terms of GBs anyways here. But whereas in relational databases, it was only restricted to GBs. And reads and writes data quickly, only reads the data quickly. The insert operation is gonna take definitely some amount of time for you to write, right? Then Hadoop ecosystem. So when I say Hadoop, there were so many other tools which come along with it, right? It's not just a single platform. The ultimate component is going to be the HDFS for storage and MapReduce for processing, and there is some advanced processing mechanism. But in addition to that, on top of it, I can say, on top of these existing components, we built a different set of tools. So we will name some of them. So there is MapReduce, Spark, Kafka, Hive, Mahout, Pig, HBase, Zookeeper, Oozie, Solar, and Lucene. And there is Flume, there is Scoop. So the core mechanism is what? The storage, Hadoop HDFS, right? So this is not changing for anything. And there is something called as Yarn. This is the advanced version of MapReduce. Okay, so we will discuss about it. So after we discuss about MapReduce, how this MapReduce works, then we will move on to the Hadoop Yarn concepts, how Hadoop Yarn has overcome or has improved, or we can say it has enhanced the functionalities of MapReduce, how it is made some difference. So it is the latest version of MapReduce, we can call the Hadoop 3.x, I can say, right? So Hadoop HDFS, Hadoop Yarn is gonna be the same. This is for storage, this is for map processing. On top of which you have Pig. Pig is mainly for unstructured data processing. It has its own scripting language. Pig is kind of completely moved out of the market now. There are very limited companies which are using Pig in their projects. So you can assume it is gone. And the most important thing is Hive, which is still in the market, which is being used by many organizations. Hive is some kind of a tool which is similar to your relational databases. So like we have Oracle and all that, outside the Hadoop ecosystem, you have Hive inside the Hadoop ecosystem, which are going to do the same thing, that as that of the RDBMS. Okay, so the problem is, for example, I have the data. I can have any kinds of data, right? I can have structured, I can have semi-structured, I can have unstructured. So when you have a Hadoop platform available, that means you are supposed to migrate the entire existing ecosystem into your Hadoop platform, right? That means, for example, if you have some data in Oracle, okay, it has reached its maximum capacity, it has got its limitations. Now what you are saying, you are saying that you will be migrating it into Hadoop ecosystem. So when you say you are migrating it into Hadoop ecosystem, what is the first thing that you're going to do? You're supposed to migrate all the existing data into Hadoop platform. Agree? Right? So whatever the data you already have in these databases or in these tables has to be first migrated into the Hadoop ecosystem. That means you have to migrate it into HDFS. Then you think about the later stages. I mean, whatever the data is coming in future, you will be tagging it to, you'll be pulling it into Hadoop ecosystem. That's fine. But the existing data has to be migrated. So when the data is coming from an Oracle database, you should have a similar framework such as Oracle or such as any relational database inside your Hadoop ecosystem also, for you to able to process it so easily. See, if the data is available in a table, let's say, okay, so there is a database DB, there is a table sample. Okay, so you do select star from db.sample. What do you get? You get the results. You get only one column. So you do select ID from sample. Select ID from sample where ID is greater than 10. That means I only get IDs which are greater than 10. So how easy is it? How familiar are we with this kind of reading and writing the data, right? So any one of us or most of us are pretty sure about what a select star from EMP we do, right? Or some of us are even aware of some advanced concepts of SQL, but pretty much all of us will have some or the other knowledge on the SQL commands, right? So this is the most easiest and the most used way of handling the structured data. So why change it then? If this is very famous tool, or if it is a very famous way of dealing with the data, dealing with the structured data, why can't we have a similar framework inside the Hadoop ecosystem? That's what has brought into this Hive. So the same commands, the same select star from, or whatever the insert commands, the create table commands, or group by commands, or order by, or anything, everything, joins, everything you kind of import from all the relational databases. You build your own platform in the Hadoop ecosystem. That's what is called as Hive, with some advanced features. With all the additional capabilities of Hadoop, you kind of give the same look and feel for your data, for the structured data mainly, right? So you have Hive to handle the structured data inside the Hadoop ecosystem, like you have done with the other relational databases. You bring the Hive to the Hadoop ecosystem. Agree? Clear? Right? So similarly, you have other tools also. Kafka and Storm are mainly for streaming. We discussed about the data which is generating with some amount of speed, and you are able to capture the data on the destination system near real-time way, right? So all this Kafka and Storm will take care of all this kind of functionalities. And Solar and Lucene, and which is for searching, and Uzi is for scheduling, and HBase is the NoSQL way of handling, the unstructured way of handling the data. And Zookeeper is maintaining the nodes, the management and coordination between different nodes. And there is Spark. We will anyway discuss about this in detail. So the in-memory processing and all that. So these are all combining together for your Hadoop ecosystem. There is Flume, and there is also Scoop. Okay, so Scoop is basically used for integrating or connecting your relational database to your Hadoop ecosystem. So what it basically does is, be it any kind of a relational database, it is used to dump the data from source to the destination. So source can be relational database or HDFS. Destination can also be HDFS or relational database. Okay, so it's basically kind of interacting with a relational database, either via source or a destination. Okay, so in most of the migration projects, we'll be using Scoop. This is the best way of importing the data from the existing relational databases into your Hadoop ecosystem. Any questions on this slide? All clear? Okay, so we are not going to get into the details of each and every component in this session, guys. What we only discuss is the core concepts of what Hadoop ecosystem is built on: Hadoop, HDFS, MapReduce, and Yarn. Okay, so other concepts we may have to get into the detailed discussions of Hadoop sessions, and as we have signed up for, we will only discuss for Hadoop core concepts. Just to give you some kind of a flavor or kind of an introduction to what Hadoop is all about, and then later on we will move on to the Spark. So Spark will get into the details, in-depth concepts of each and every component inside your Spark. Okay, then now moving on to the HDFS. So we will discuss with the core component. The first core component is HDFS. Is a storage system that's running on a Java programming language, and it is used as a primary storage device in Hadoop application. So it is built on top of a Java. So we are not worried about it. I mean, let's not worry about what it is built upon or how we can access. So what we do need to understand is what are its features, or what is its architecture, how it is working, and what does it do basically. What is it going to do in Hadoop? It is going to take care of all your storage related needs. So in a Hadoop ecosystem, in the Hadoop platform, HDFS is going to be your ultimate storage. Okay, so regardless of what, your HDFS will be your primary source for your storage of data. Okay, so it has two components. So like we have in Hadoop, HDFS and MapReduce. So inside HDFS, you have two more components. One is name node and the other one is the data node. So we will discuss about what is name node, what is data node in detail. We will get into these concepts, but just to let you know, there is name node and a data node, two nodes inside your HDFS. There is one more secondary name node, but we will get into the details later. Okay, and this is used for storing large amounts of data across multiple nodes on Hadoop cluster. This we know. Then MapReduce, like we know, we have this MapReduce for all the processing related needs, how the data can be processed on the Hadoop ecosystem, all the executions, all the computations, all the processings can only be done through a MapReduce program. So now it is being replaced by, or it has been over or upgraded to Yarn, I can say. But earlier it was MapReduce. In the initial versions of Hadoop, it was MapReduce. So if I can go back here, see, for all this, for Hive, for Pig, for Spark built on Hadoop, for Zookeeper, for HBase, Oozie, and everything, the source for your storage will be HDFS ultimately. Okay, so there is no other layer or there is no other place where you're gonna store the data. It's only going to be HDFS. And let's say I downloaded or I transferred some data from a relational database EMP table and I migrated it into the Hadoop framework. Now what I'll do a select star from EMP on Hive, right? So where is this file available? Where is this data available? That is available in HDFS. Fine. Okay, clear. The storage is available in HDFS. The EMP related data in the table is available in HDFS. But when I run a select star from EMP, what are we writing? We are actually writing a similar SQL query, and very known SQL query, select star from EMP. But internally, what it is going to happen is it's going to convert this select star from EMP query into a MapReduce program. Okay. So that is the reason why I'm saying. So the only way you can interact with the Hadoop ecosystem is the way with MapReduce. Okay, so MapReduce is the only programmatical model, programmatical way to interact with the Hadoop ecosystem, with the Hadoop components, with the Hadoop framework. What we are writing select star from EMP is for user convenience. Okay, so internally it has to run via a MapReduce program only. Okay, so ultimately the storage is HDFS, the processing is gonna be MapReduce, regardless of what. You write a Hive query, you write a Pig script, you write some HBase query, you write some Oozie script, whatever, right? So it has to be a MapReduce processing only. So whatever the query you write might change depending on the user, depending on the feasibility, flexibility of the users. But ultimately, it's going to get converted into a MapReduce program, and it's going to execute on the MapReduce engine. There is a processing framework and all that, right? So that is what I wanted to tell. So the ultimate processing component is going to be MapReduce. So it has two components again, like we have name node and data node. In MapReduce also it has got two more components. One is the job tracker and the other one is a task tracker. So I don't think it is listed here, but the two more components, two more nodes are job tracker and the task tracker. Okay, so basically your MapReduce functionality is divided into two core functionalities. One is the map function as well as a reduce function. Okay, so we'll anyway discuss the architecture and the actual understanding of MapReduce. So let's not complicate it at this moment. So it's going to be a bit complicated for us to understand at the initial stages. Okay, we will discuss that. We'll take this discussion a little later. Okay, when we get into the core concepts. Now, are we clear with HDFS? There are two nodes, name node and the data node, and similarly in Yarn you have resource manager and the node manager. There were two more components. Okay, so we will discuss about it, how Yarn has got its importance, how is it different from MapReduce, and all that we will discuss about it in detail. Okay, then so Hadoop 2.x version versus Hadoop 3.x version. So the latest version that is running is Hadoop 3.2, I guess. Okay, earlier we were working on Hadoop 2.x versions. And how is it different with the existing 2.x and 3.x is it consumes 200% of storage in HDFS. It only consumes 50% of storage in HDFS in terms of consumption of data. And scalability is maximum we can have 10,000 nodes in a cluster, and it has gone beyond 10,000 nodes. You can have more number of nodes inside a cluster. So in real-time scenarios for us guys, to be fair, we hardly work with systems which are around 100 200 nodes at max, 200 nodes per cluster at max. But I mean, if you are lucky enough, you can deal with more number of nodes also. But you being a developer, you will nowhere see, I mean, you'll nowhere get access to see that okay, these many nodes are available, these many nodes are configured in my cluster, and all that information will not be shared to you. That's the admin job. if you yourself are setting the environment of Hadoop, then you will be able to get a hands onto it. Okay, so the one which is installed on our local systems is a single node Hadoop, which is your local system, which is your local machine. It's running on a single node, and the number of nodes can go up to 10,000 in Hadoop 2.x versions, and 3.x it has gone beyond. That's an additional feature that we've got, right? So this is supporting DFS FTP S3 file system, and all features plus Microsoft Azure Data Lake file system are also supported. So why am I saying this Amazon S3 file system and Azure Data Lake file system and all that is like, see, earlier everything is an on-premise storage. Agree? You know what is the difference between an on-premise and cloud? Yes, right. So everything was within the everything was physical storage that we had earlier. I mean, you yourself configure different nodes on your work premises, right? You configure some 10 nodes, 20 nodes, 30 nodes, and you can see this network drives and all that things. That is on-premise network. And compared to the cloud systems, like everything is a cloud storage now. So instead of you maintaining all this hardware at office premises, now everything has been migrated to cloud. So you tell the cloud provider that you need some 100 terabytes of storage, and you would need some 100 to 200 cores to interact to the systems, and they will charge you some amount and they'll give you the storage. You just need to use the host name or the IP address of those machines, and you'll just interact with it. Okay, so there is no storage available at your premises here. So everything is cloud based. So that is the advantage we get using this Amazon or Azure or Google Cloud, like for that matter, that everything is cloud based storage now. So how your Hadoop can interact with those cloud storages is what is being provided. I mean, in the latest versions of Hadoop, you got this feature of interacting or using an Amazon S3 as your HDFS, or using Hadoop Azure Data Lake ADLS storages as your HDFS, right? So earlier it was all on-premise storage. You configured your HDFS, but now you can use the existing S3 buckets as your HDFS storage. So that feature is kind of added on top of the existing versions of 2.x and 3.x. Okay, so in latest versions, you are having the support for Azure Data Lake storages as well, right? And in the earlier versions, you are using Hadoop HDFS as a load balancer, a data balancing, and now in the 3.x version, intra-data node balancing for the data balancing. So we will discuss about these concepts in detail in the Hadoop MapReduce architecture pretty much. Okay, so let's not complicate it at this moment. So are we clear? So this is something which is out of context, guys, the 2.x and 3.x, as we have not completely discussed about the actual components of Hadoop. We have not discussed about the core components of Hadoop. When we will discuss about it, then we will have a better understanding of what is available now and what is available in the latest stages of it. Okay, now, so now going back to HDFS, so we will discuss the core concepts of HDFS in this particular slides for the next 5 to 6 slides. What HDFS is going to do, what are its features, and how is it being done? I mean, in terms of architecture, how do you take care of it, right? So we know it is mainly used for storing the data. So let's just read through the data definition that we have. HDFS is a file system designed for storing very large files with streaming data access patterns running on clusters of commodity hardware. So there were some terms that have been highlighted. Large files is one, streaming data access, and commodity hardware. Okay, what does that mean? What is this large files? So HDFS is primarily meant for dealing with the large amounts of data sets. So why am I saying this is, so for example, there is a storage requirement. Okay, there is a 500 GB of storage requirement. On the first scenario, I have a one single file which is having some 500 GB of data, one single file. On the second scenario, I have some 1000 individual files which are of 500 MB each. Agree? 516 or 508 or 515, 512 or whatever the accurate numbers. Okay. One scenario is I have one single file which is of 500 GB, or in terms of less number of storages, you have one single file of 500 MB and you have 1000 single files of 512 KB each. Okay, so ultimately both the scenarios, what am I using, which storage, I mean how much storage I'm supposed to allocate in both the scenarios? I have to allocate 500 MB of storage in both the scenarios regardless of how many files I have. But the most preferred layer for storages is the first scenario, which is having the one single file which is of 500 MB. So the reason why I'm going with the first scenario is I'm not going with the second scenario is Hadoop is meant, or Hadoop is designed in such a way that for each and every file you load, you write into the HDFS, there is some amount of metadata that is getting generated. So we will talk about it in detail in the architecture. But you know what is metadata? Have you heard about this term metadata? Yes? No? So what is it going to be? What is metadata? Data about data. Okay. So it can be any information, right? So for example, in simple terms, as we are at the beginning sessions, right? So in simple terms, for example, I'm loading 1 GB of one file of 500 GB, 500 MB. So what is it going to be? What is a source file? Where is it coming from? What are the number of blocks it has got? What is the information that it has got? And how many number of records that it has got? So some information can be anything. Okay. So depending on the framework, it might vary. So some information about this file is called as a metadata. So HDFS, while you're writing this data into HDFS, it will create some information about this file. So that's going to be in some KBs, let's say. Okay, so some information about this file it's going to create, and it's going to store it within the HDFS only. So, okay, so if you're trying to access this file, this is the metadata information for it. So similarly, on the other scenario, when you have multiple such files, when you have 1000 such files, you're creating 1000 such metadata information, right? So that itself is actually increasing the storage, right? If you're maintaining some 1000 metadata information, 1000 metadata files, if I'm having around 500 KB of file and I'm generating some 100 KB of metadata for it, that does not make any sense for us, right? So if I'm storing some 100 KB of metadata for some 100 GB of data file, that's okay to handle. But if I'm only having 100 to 200 KB of file and I'm generating 100 KB of metadata for it, that does not make any difference. That does not make any sense for us. So that is the reason, as it is generating this metadata for each and every file, it's preferable, it's mostly used, I mean preferably you better use it for large amounts of data files rather than using it for small files. So that is the reason why we say that it's preferred to use large files. Okay, and there is something called as the streaming data access pattern. So we will discuss about it. I mean this has to be when how you actually write the data, how actually you read the data. The data is being written once and read as many number of times. So this is how we write once and read many is the approach that we are going to follow. That means you only write once and you scan the entire data and you kind of read any number of times after that. So that is the advantage we get with the HDFS. So this piece we will discuss that in detail when we discuss about the architecture, how you write it and how you read it. And commodity hardware, did we discuss about this?
Just a quick info, guys. If you want to make a career in big data, then Intellipaat provides an advanced certification in Big Data Analytics by ENICT Council IIT Guwahati. It is taught by IIT professors and industry experts. With more than 10 years of experience, this course is designed to upskill and land your dream job. Now let's continue with the session.
We know what is this commodity hardware, right? So with the help of this commodity hardware, you are actually able to reduce the price of the entire cluster. Agree? So when we discuss about the legacy systems, the expensive component, using this commodity hardware, you kind of taking away all the advanced features of your hardware. You're not even installing any high-end software on top of it. You just need a basic hard disk to store some information. So that is what we call it as a commodity hardware. And how is it helping us? We are able to reduce the price of the entire cluster using this commodity hardware. Okay. So these are the three components or three main features of your HDFS. And when you're designing your HDFS here, okay. So for example, you are setting up your own HDFS component. What are the things that you are supposed to look into or take care of is what this design factors is gonna let you know. So high throughput, hundreds and thousands of nodes, and handling large data sets, portability across heterogeneous hardware or software. So what does this throughput mean? Anyone? What do you mean by throughput? Okay, yeah. So the amount of data, in simple terms, the amount of data that we read or write at a specific instance of time, I can say, in simple terms, right? So, right. So, for example, I have a single node. I have a one single input output port, right? So I maximum I can read 10 MBs per second data or 10 MBs per second write. Okay, so that is what my throughput I call it. So when I have two nodes, that means I can read 10 MBs from one node, 10 MBs from two nodes. That what is it going to be? 20 MBs on a whole is my throughput. So when I have multiple nodes like this, so the throughput with which I can read the data from these nodes is very, very high. So that is one of the advantages that we get here. So write is not going to be faster, but read is definitely going to be faster, because when you have multiple nodes, the write is happening in a sequential order, but the read is happening in a parallel order. Okay. So sequentially, as in like you write the data one after the other. One node you write it, then after filling the entire node, you move on to the next node and then move on to the next node. But when you're reading the data, you can read the data across all the nodes at a single point of time. So you have a very high throughput here, where very high read throughput, I can say. Okay. And you have the feature of, you have the capability of handling hundreds or thousands of nodes. As just a while ago, we've seen the slide. The version 2.x has the capability of storing up to 10,000 nodes, configuring up to 10,000 nodes in a cluster, whereas in 3.x it has gone beyond the 10,000. So that is the number of nodes that we have. And handling large data sets in terms of TVs and PBs, that is the advantage we get, right? Just a while ago we discussed about the advantage of reading large data files, right? We hardly generate very small amounts of metadata for it, and it's feasible, or it's preferable to deal with large amounts of data sets. And portability across heterogeneous hardware solutions. We know what is this heterogeneous systems. We discussed about it a while ago in the features. The effective way of reading with the heterogeneous data sets is also available within your HDFS components, right? Now, how the design of HDFS were altered to meet the design goals. So simple coherence model, write once and read many, and moving computation close to the data and data replication. So what is this write once and read many kind of an approach? Like I said, this high throughput, that is what we achieve, right? So you're only allowed to read it once, write it once, preferably write it once, but you can read it any number of times, because the read is happening in a parallel way, whereas the write is happening in a sequential order. Okay. And moving computation close to the data. What is it? Computation close to the data. We have discussed about MapReduce way of handling. Right. The problem of combining data in Hadoop, in pre-Hadoop days, how this Hadoop has overcome it. Instead of moving data to the computation or to the code, rather we are moving the code to the location where the data is available, right? So what is the advantage we get? The read and writes with such large amounts of data sets have been overcome here. We are not moving any data anywhere. We are just moving whatever the piece of code that we have written to the data location, and we are computing it, and we are only taking out the results from there, right? And the data replication, we know what is this replication, 1, 2, 3, and how replication is helping you to achieve this fault tolerance. Okay, so kind of on the last 2 to 3 slides, we are kind of repeating most of the concepts that we discussed. Okay, so any questions, guys, so far? Architecture of HDFS. So at least we know initially, I mean, at least with whatever understanding we have, we know that there is this is used for storage, and the entire data that is available in the Hadoop platform is supposed to be stored in HDFS. So how the data is stored, how it is being accessed, and everything we will discuss. We will see that. So fine. So we have discussed about two components, right? What are those two components? Right. So first one is the name node and data node. These are the two components in my HDFS, the major components in my HDFS, right? So the architecture of HDFS is a master slave architecture. So what do you mean by this master slave architecture? There is going to be one master and rest all will be slaves. Okay. So when you are writing the data or reading the data, see, we know that there are some hundreds of nodes available inside your HDFS, right? So it's a distributed platform. We have a cluster. Inside that cluster, we have some hundreds of nodes, some thousands of nodes, right? So when we have so many number of nodes, how do you maintain the configuration or managing of all these nodes? See, when I'm supposed to load the data, how do I decide that in which node I have to load the data? When I'm supposed to read the data, how do I know that which node has so and so information, right? So there has to be one system which actually has to take care of all the admin related activities, I can say. Okay, if you're writing the data, okay, you go and write on so and so number of node. If you're reading the data, if you're looking for this information, you can go and read from so and so number of node, right? So there has to be one machine, one master inside your cluster, which pretty much has to own all the operations, all the read and write related operations. So that is why this HDFS has been designed in such a way that it is going to have a master and it's going to have a slave as well, these number of slaves. So this is my slave node and this is another slave node and this is my third slave node and this is gonna be my fourth slave node. This is gonna be my fifth slave node. So I have one master. I can increase the size, it's better. Because we are gonna supposed to write some blocks, we are gonna supposed to draw some blocks inside it. So it's better we increase the size. Okay. So these are the nodes that we have. So I'm gonna name this the master, which is my name node, right? All the other nodes are the data nodes. Okay, so all these are the data nodes. Fine. So now I have to have some connectivity between these nodes. Each and every node should have, everything is connected to the master, all the data nodes. So this is my master and slave architecture, right? One master is connected to all the slave nodes. So now my what is my cluster size? So if I have to write some text here, let's say I'm writing some text. So this is my cluster. Are you able to see this? My cluster size is 6 nodes, right? 1, 2, 3, 4, 5 and 6 nodes. This is my 6 node cluster size. 6 nodes. And what else? Let's say the storage is around 500 GB and 100 GB each. And used is, let's say, some 200 GB. Available is some 300 GB. Are we clear? This is my statistics for your cluster. Are we clear? This is my cluster, HDFS cluster, which has 6 nodes. One is the master, all the other 5 nodes are slaves. And we are only going to consider the storage available on the slave nodes, on the data nodes as the capacity. Okay. So 100 GB each, I have 500 GB of storage capacity available, and out of which 200 GB is already used. Okay, so my cluster is already in use, and 300 GB is the available storage. Clear? Now there is one more scenario. So here I have hello.txt file which is of 100 GB, which is supposed to be written into my HDFS. Okay, so this hello.txt file has to be written into, or has to be loaded into my HDFS. That means whenever I'm trying to write some data into HDFS or read some data into HDFS, the requests which are supposed to be sent will ultimately reach my name node, the master, right? So when you're saying that you're sending a request to write some data into HDFS, that means you're sending a request to the name node. Or when you say you're sending some read request to the name node, to the HDFS, that means you're sending a request to the name node ultimately. So I have a request to load some 100 GB of data in your HDFS. So first, when I send this request to the HDFS, it's gonna come and hit your name node ultimately. So what is your name node gonna do? So name node internally will have, is internal to name node. Okay, will have metadata. So what does this metadata consist of? Metadata consists of file info, block info, available node info. So what does this mean? So it's going to hold the information related to whatever the number of files that are written to your HDFS, what data is written to your HDFS, what are the number of nodes that are available to be stored, and in each and every node how much amount of data is being, how much amount of storage is being used. All this information will be available inside your metadata. Agree? So when I say that I'm supposed to write some hello.txt which is of 100 GB into your HDFS, what my name node will have to do is it will first internally read the metadata for the available storage. So it will check whether the data is, whether we can accumulate this 100 GB of data in your HDFS. So what is it going to do? My cluster information says that it is available storage is around 300 GB. So I have 300 GB of storage, then I can definitely store 100 GB of data. So I can definitely store 100 GB of data, but in which node I have to store it? Yes, which node has the availability to store 100 GB of data. So now by looking at the metadata information, I'll identify, okay, node 1, 2 and 3 have the necessary storage to load this 100 GB of data. So now I'm selecting node 1, 2 and 3 to store 100 GB of data, hello.txt file. So now what it will do, your master will grant access to your hello.txt file to the writer to go and write on these 3 nodes. So how is that data going to be written? The data will be broken into multiple blocks. So every block, every data file in HDFS will have to be written in the form of blocks, individual blocks. So each block consists of 64 MB or 128 MB of block size. That means when I have 100 GB of data, I'll break that into multiple blocks of 64 MB or 128 MB. So this is the default block size of your HDFS. So you can upgrade it to 128 MB. I don't think it's going beyond 128 now at this moment. So earlier it was only 64 MB. Now it has got the feature to upgrade it to 128 MB. So now whatever the data you have, you will divide that into 128 MB of blocks. So where do you configure it? You will be configuring in the cluster information. Okay, you will be configuring it there. And depending on the configurations of your HDFS cluster, if it is 128 MB, your data will be divided into multiple 128 MB of blocks. So where are they going to be written now? Each and every block of data will be loaded into your data node 1, 2 and 3. Okay. So let's say I have this one. I'll take small blocks. This is 1. Getting it what I'm trying to do? I'm just dividing this data into multiple blocks and I'm just trying to write them into your HDFS storages. Okay, it's difficult to create so many blocks here, so just let's assume that I have written some 128 MB blocks of data into these nodes. Okay, right? So now I have loaded this data into these 3 data nodes, hello.txt. After you load this data, you're supposed to load the replicas also. When and when you write this data block into so and so data node, the replica of it will be written on the other data nodes. So this is block 1. I have written that into this data node. Now I'll load this replica on the other data node. And as and when I write this block, I'll load that replica on some other data node. As and when I write this block, I'll be loading it on some other data node. So as and when you're writing the blocks into your HDFS data nodes, the same time your replicas also will get created on the other data nodes. So depending on the replication factor again. So here we have we might have missed that replication. So let's say replication factor is what? 2. This is my cluster information, right? So my replication factor says that I have written the data. I have to replicate the data twice. So after I write the data on one particular node, I'll be replicating it into other data node. Simple. Okay. So like this, I have written all the 100 GB of data on all these 3 data nodes, and I have replicated in on so and so data nodes. Okay. Clear? So now my cluster information will change. So now my metadata information will change. So this entire thing is your metadata, let's assume. Okay. So my cluster information will change something like this. So your availability is around, used is around 300 GB and your availability is around 200 GB. Is it 300? No, right? 400 and 100 because it is replicated. 100 GB is the original copy, 100 GB is the duplicate copy. So now you have almost used 200 GB of storage in this. So your used will be 400, availability will be 100 GB. Getting it? So now you have written the data. You have performed a write operation. Okay. So now when you are supposed to read the data, same hello.txt, now when you are supposed to read it, I'm coming now to read the data. So what do? You again send a request to the master name node. Again, name node will look into the metadata, look into the name node metadata information, and it will identify that, okay, this hello.txt is written on data node 1, 2, and 3. So that your read request will go and read the data on top of this 3 data nodes. So your hello.txt will be read from these 3 data nodes parallelly. Okay, earlier it was sequential. Now you read it parallelly. Okay. This is how your data write and read operation will be happening. In addition to this, there is also this health check signal. So at regular intervals, let's say around for 10 minutes once or 20 minutes once, at 10 minutes interval or 20-minute interval, your data nodes are supposed to send a heartbeat signal to your name node saying that they are alive. I mean, if the data node does not send a heartbeat signal, that will assume this data node to be dead, and it will not consider this data node for any further write or read request. Okay, so it's kind of a heartbeat signal which is being sent to the master at regular intervals. All the data nodes are supposed to be sending that signal. So if a data node has been failed, this data node is notified that it is not available. So now when there is a hello.txt read request coming in, it will look into the metadata. It will read that, okay, this hello.txt is written on 1, 2, and 3. And the data node 1 has not sent any heartbeat signal. In that case, what happens? What are the blocks written on this data node and which blocks have been replicated on which data node? So when the primary block is not available, it's going to look into the replicated blocks and read those blocks. Okay. So ultimately the first read operation has to be on the primary node. If the data node which is holding the primary block is not available, then it will look for the replicas. So where exactly it is being replicated, that also will be available in the metadata information. It's going to look for the replicas and it's going to read It's going to process the read request from the replica nodes, right? Primary block first. So replicas are always the secondary read operations. Replica information will not be the primary read operation. Okay, so we cannot say that okay, this block is available here and this block is same block is available here. It can't be a duplicate, right? We are maintaining the duplicates intentionally. We wanted to make sure that the safety of the data is primary, and we are maintaining 2 copies of it. First copy will be read first. If the first copy data node is not available, only then the second copy will be read. Getting it? Now, so what happens when you have to read the data? What happens when you have to write the data? Everything is being controlled by your master node. If there is no master, you definitely don't know where to write the data, or you definitely don't know where to read the data from, right? So it's basically the heart of your entire healthcare, the HDFS cluster. Okay, so now let's look at some of the failure mechanisms. So now that we know when a data node is lost, there is a duplicate copy available. With the help of replication factor, what we will do, we will maintain 2 copies, a duplicate copy of it. So if this is not available, we will read it from the other duplicate copy. So how do you set this replication factor is depending on the sensitivity of the data. So if the data is very sensitive, you're not afforded to lose the data. If the case is like you have the production data, let's say, okay, if the data is coming from some client, you're not supposed to lose the data at any cost. You maintain the replication factor to be 3 or 2. If it is a dev internal, a dev environment where the data is all duplicate, or a dummy, or all the test data, let's assume, you don't have to maintain 2 copies of it. It's okay even if you lose it, right? So you don't have to maintain in such cases the replication. So only when the data is sensitive and you're not afforded to lose it, then we will maintain the replication factor to 2 or 3. Okay, so in unnecessary scenarios, we are not going to maintain duplicate copies of it. We'll only maintain 1 copy of it as a replication factor 1. Okay, so now when we lose a data node, there is no harm or there is no damage to the cluster. At least I can say the read and write operations can go on at the same pace. But what happens when the name node is down? See, data nodes are down, we are okay. We'll continue with the operations. But what if the name node is down? So here we can consider, we can categorize this name node down into multiple scenarios. Let's say name node down. See, a name node can go down in 2 different scenarios. One is the scheduled or restart. Okay, there is some restarts going to happen at regular intervals, right? On weekdays or weekends, there is some scheduled activity. You restart on so and so after 10 days or after 15 days, you restart this machine. So there is one scenario. And unplanned outage or downtime. These are the 2 scenarios. So what happens at the scheduled restarts? This is a known activity, right? So we all know that there is a restart happening on the name node, and your HDFS will not be available from so and so time. There is a schedule email sent. There is a notification sent to all the users who are accessing it, and it is properly planned. Okay, when the systems are down and when there is not much traffic on weekends or on late Sundays, you do this scheduled activity. There is no harm or there is no problem with this kind of an activity. But what happens with an unplanned outage? What happens if there is some issue with the master node hardware and some issue, some problem, and it has gone down? What happens in that case? The entire HDFS cluster will not be accessible, right? Because this itself is going to be the point of contact for all the read and write operations of your HDFS cluster, right? If the name node itself is not available, then there is no what do you say, then there is no use in having all the data nodes also. If you don't know what to access or where to access those data nodes, you don't have to, we don't matter if the HDFS is active or not, right? So master itself is going to be the single point of contact for all your read and write operations. If the master is down, then the entire HDFS is going to be down regardless of what. Okay, now, okay, you have done some maintenance, you have resolved the issue of the master, and you have brought it back up again. Okay, so after 1 hour, you brought the name node back into action. So you done the maintenance. What if the data which is available inside the master node, I'm talking about this metadata, okay, the metadata inside the master node while you are doing the maintenance, or depending on the impact of the issue, your metadata can also be lost some cases, right? If there is a hardware corruption, right, the entire data that is available inside the metadata inside the master node hard disk will be corrupted, right? So in your unplanned downtimes, there are two scenarios. Restored master, let's say name node with metadata. Then 2.2 will be restored name node without metadata. Now, so first scenario is restoring the name node after 1 hour, whatever the time you have taken. After 1 hour, you have restored the metadata name node with the metadata. So there is no loss in the metadata also. So after 1 hour, you brought the system back up again, and your metadata is also active. So now what happens? After this is brought back up again, you continue with the operations. There is no problem with it, right? So the only downtime will be the 1 hour which you have lost in doing the maintenance activity. So this is not having any problem. But what happens if the restoration of name node is done without actually restoring the name metadata? What happens? You have the name node available, but there is no metadata. How do you interact with the data nodes now? For example, there is a write request. How do you actually write the data without the information of your metadata? Yes. So in these cases, also your name node is considered to be inactive. There is no recovery for this kind of a scenario. That means your entire HDFS cluster is supposed to be crashed. Okay. So there is no backup, I can say. Your name node is not gonna restore to the existing functionality. Your entire HDFS cluster is considered to be down, crashed. Okay. So to avoid these kind of scenarios, they have done some changes. So before we get into it, I think I missed out on some points here.
Just a quick info guys, if you want to make a career in big data, then Intellipaat provides an advanced certification in Big Data Analytics by ENICT Council IIT Guwahati. It is taught by IIT professors and industry experts. With more than 10 years of experience, this course is designed to upskill and land your dream job. Now let's continue with the session.
Are we clear, guys? With the failures, I think I missed out on the metadata information. There is some data that has to be updated. So inside the metadata, guys, sorry, I forgot to include one point. There is inside the metadata, there is something called as FS image and edit logs. But there is something called as edit logs, let's say. Okay, not FS image. So what does this FS image mean? So this is all inside the metadata only, inside this metadata information. So what does this FS image mean? So FS image is something which is going to have the image of the entire file systems. That itself is the term, right? File system image. That means it's having the information of all the data that you have inside the, right? You have the data of all the, you have the information of all the data that you have included in the HDFS cluster. That is what we call it as an FS image. Okay. And for every write operation in the previous scenario, we have done some 100 GB write, right? So you have updated something on data node 1, updated something on data node 2, you have updated something on data node 3, and there is no update happening on data node 4 and 5. So for every write operation or for every change in the HDFS data node operations, for every write or a read operation, there is something called as edit logs that is getting generated. We call it as edit logs. That means for every edit happening, for every write operation, there is an edit log that is generated which reads the changes happened across all the data nodes, and it will append this edit log to the actual FS image. That means In the previous FS image, my cluster capacity was around 300 GB used and 200 GB used and 300 GB available. But now with the edit log information that I have updated, I updated it to 400 GB used and 100 GB available. That means whatever the changes that have happened in this particular write operation have been captured in the form of an edit log, and they are going to get appended to the core FS image. Whatever the entire information that you have, you just keep appending these edit logs to the existing FS image so that your FS image is latest every time. Now, when you get a read operation, your FS image will be latest and it will be able to process the actual information. Getting it? Getting this understood this concept of edit log and FS image? Yes, guys. So edit log is for every write operation, you generate some metadata and append it with the existing metadata of your master name node. So the core, entire metadata is called as FS image, and for every edit, whatever you capture is called as an edit log. The log for each and every edit, that is what the edit log. FS image is the file system image, the entire image of the file system. Okay, you take the edit log and you go and update in the FS image. This is one thing that I missed in the previous discussion. Okay. All right. So now going back to the downtime scenario. So now you understood, guys, how many ways the downtime will be. One is the scheduled downtime. On some weekdays, weekends, you will be scheduling your name node to restart, and whatever the time it is taking to restart, your name node will be down, and after the proper activity, your name node will be brought back up again and your entire procedure will continue as planned. This is a planned downtime, I can say. But whereas for unplanned downtimes, there is some issue with the name node and it has crashed. Now you take some time to repair it. You brought back again, and when you have brought it back again, there are chances that your name node metadata can be restored completely, or your metadata can also be crashed in some scenarios. If your metadata is restored, there is no downtime. I mean, whatever the time it has taken for you to repair the system is actually the downtime. After that, you can continue with the rest of the activities. But when there is no metadata, when the metadata restore is not done, this is the entire system failure we consider it as. Okay, there is no restoration, there is no resolution for this kind of a issue, right? So this is considered to be the entire cluster failure. Okay, if your name node is down along with the metadata, then your entire cluster will be down. So to avoid this scenario, this is the earlier versions of Hadoop base. In the earlier days, this is the scenario. We had only one name node and we don't have a backup. So to avoid this scenario, what they have done is they have included something called as a secondary name node. I call this as a secondary name node. What does a secondary name node do?
It is a backup of name node.
Yes, it's a backup of your name node. It does not, let me tell you that this is here, this is here. So what it only holds is, right. So this secondary name node is considered to be the backup of your name node metadata only. Okay, so it's not a backup of your name node. That means, see, when your name node is down, your secondary name node cannot take up the process and it cannot run the HDFS cluster in the absence of your name node. Okay, what it will only do is, at regular intervals, it will just take the FS image which is available on the master name node. It will take a copy of it, store it inside the secondary name node, and then send it back to the master name node. That's the only activity it's going to do. That means we are only maintaining a backup for your metadata, FS image. Apart from that, we are not doing any other activity which your master name node does. Secondary name node does not take care of any other activities which your master name node is going to do. It is only meant to maintain a backup copy of your FS image, just to avoid this last scenario. What is that last scenario? When your name node is crashed, along with your metadata, you restore your name node and you take the latest FS image copy from the secondary name node and you continue the process. In the last scenario, there is an irreplaceable issue, right? It cannot be restored again. That is what we discussed. So to avoid that entire crash down of the system, we included something called as a secondary name node. Okay, just to maintain a backup for your FS image. So this is a very important question, guys. You might get even even now you are getting these questions in the interviews. So your secondary name node cannot take up your activities of your master name node. It is only meant to maintain a backup of your FS image. Clear? At regular intervals, it just takes out a copy of FS image, stores it within itself, and sends it back to the master name node. Okay. Okay. So yeah. So now, okay. So quickly, before we get into so many questions on secondary name node, uh, I'll also introduce to one more thing. So there is the actual solution. This is the actual solution. So in the earlier versions of Hadoop, this is all whatever we have till the secondary name node is all generation 1 of Hadoop, first generation of Hadoop. Okay, which still has a problem of name node failure, right? So when the name node is down, the entire cluster is down. There is no recovery for it, right? Only when the name node is brought back up again, you can continue with the rest of the process. So whatever the time the name node is down, that time in that particular time, you cannot access any read or write requests. Okay, that downtime is always there. But in the second generation of Hadoop, what they have done is they have included some concept called as active and passive name node. So in second generation of Hadoop, or else shall I write it in a different diagram? Shall I put it in a different file altogether? Right. So in second generation of Hadoop, the only change is gonna be here. Everything else will remain the same, but I call this, oh, there is also an option to draw like this, is it? Okay, super. How do I make it bidirectional? Right. So this is your what? Name node. I can call it passive. And this is your active. So there's a concept of active name node and a passive name node here. Okay, that means rest all concepts will remain the same. Okay, that means there are two name nodes. One is going to be active, whichever is running. The other one is going to be passive. So the same connectivities will be having a similar connection with passive name nodes also. How do I make this? I think I'm gonna become expert in draw IO. If my manager knows this, then he's gonna make me draw all these diagrams. All the architecture related diagrams is gonna make me do. Okay, super. This is how it's going to be. Understood? So that means there is a backup. There is a backup for your name node actually here. Okay, so even when the name node is gonna go down, you still can continue the operations using the passive name node. So whenever your active name node is down, your passive name node will take care of it, right? So that you are maintaining 24/7 availability of your name node. The only reason why we get this is you maintain 24/7 availability of your name node. So we are just trying to make sure your name node is available all the time. So let me just take this out for some other place here. So I'll move this here. And there has to be a connection between these two as well, because the FS image can come from any place, right? It can come from name node, active name node, or it can also come from passive name node. This is how it's going to be. So your secondary name node is going to be in the middle, and your FS image can come from any place. Understood? So many arrows, huh? So your secondary name node is again only maintaining the FS image, but your master name node active and the master name node passive is something which is going to act as a duplicate, a backup, actual backup of your name node. So when your master name node is down, all the controls will go to your passive name node, right? So it will continue with the read and write operation. So when this is brought back up again, it will come back to the controls of your active name node, right? So every time you make sure any one of the name nodes is running. Again, don't ask me if both the name nodes are down. That depends on your luck entirely. I'm calling this active and calling this passive because this is running currently. This is going to be active. If this is running, this is going to be active and this is going to be passive. That's it. Okay. So don't get misdirected about this active and passive terminology. Whichever is running will be active and the other one will be passive. Okay, simple. So any questions on this? Yeah. So we know that HDFS has two components. HDFS cluster, one is a master and one is a slave. Master is a name node, and slaves are all the data nodes. So whatever the number of nodes you have inside the cluster, so one will be allocated as one will be considered as a dedicated master, and the other rest of the nodes will be the slave nodes, right? So we know what's the functionality of a master and a slave. So let's just read through some of the operations. The name node manages the file system namespace and maintains the file system tree and metadata of all the files, and it also maintains the namespace and edit logs, and we've seen what this namespace is all about. Okay, and the data nodes, these are actually the workhorses. It stores and retrieves the data. So whatever the activity which is related to the read and write operations is going to happen on top of the data nodes. So name node is only just managing the resources or the flow of the data. Data node is something which actually stores the data. And you've also seen the replication, how the data node replication is done. And the secondary name node doesn't act as a secondary name node. So it's not a backup to the name node. That's what it means. Its main role is to periodically merge the namespace image with the edit log to prevent the edit log from becoming too large, right? So it just keeps a backup of it runs on a separate physical machine, as it is requiring plenty of CPU and memory for performing this much, right? And only just in case if the name node fails, the secondary name node will copy the existing metadata to the primary name node. And we've also seen the blocks, how the data node blocks are divided. Whatever the data size can be, your data is always going to be stored in the form of individual 128 MB blocks. Okay, so each block is around 128 MB. This is configurable. Earlier it was allowed, the maximum was allowed only 64 MB of block size. Now in the latest versions of Hadoop, it is now moved to 128 MB. So any data file has to be split into multiple blocks of 128 MB each, and these blocks will be stored on the HDFS data nodes, right? So this is some representation of how the data can be divided. So there is a data file of abc.txt. It's supposed to be divided into two blocks, considering one block size is of 128 MB. So 128 MB is block 1, and the rest 72 MB will be block 2. Right. And the block replication, we know what's the replication. The maximum, the default replication factor when you configure the system would be 1, but you can take it up to 3. You can have 3 copies of the same data maintained, so that you don't lose the data as in even when the data node fails, right? So there's also something related to the placing of this replicated blocks. See, for example, if you see, so this is just a theoretical saying. I mean, I don't know how we can prove this practically, but in general, I've gone through some documentation where it says, for example, we have 3 replication factor, right? So that means 3 copies of my data has to be maintained. So the primary data block, you store it in this data node. Okay, in whatever the data node you are supposed to write the data, you will be storing it in that particular data node. So that's the first block. That's a primary block. And the next block of data will be stored in the closest possible data node, right? So for example, I have some 10 data nodes. So whichever is near to the data node 1, the first primary block I've written on the data node 1, let's say. Okay, so whichever is nearer to the data node 1, we will consider that data node 2 or 3, whichever has got the availability of storage. So we will consider that as the second copy. Okay, so you'll store the second copy of it on the nearest data node possible. and the third copy of it is being stored on a different rack altogether. So what does this rack mean? So has anyone, have you heard about this concept, rack? So some group of data nodes, you consider them in the form of a rack. So let's say I have 100 data nodes. So 10 data nodes, I'll place it in some location. 10 data nodes, I'll place it in some other location. 10 data nodes, I'll place it in some other location. So virtually, when the physical location of the data nodes is in different regions. So one is in US, one is in some India, one is in some Canada. So different locations. So we call them as a data centers, right? You must have heard about this term. Data centers can be at different locations, but when you log into the master node, or when you are looking at a particular HDFS cluster, you tend to see them on the same, on the same network. That's what we are trying to do, right? So it doesn't make any difference whether they are available on different regions also. So you tend to see them available on the same network, which can be accessible easily. So the third block is said to be located on a different region or a different track altogether. So that's the reason being, when the first copy of the data is lost, the first copy of the block is lost, the master node, it has to look out for the next copy of it. All right. So when it is looking for a next copy of it, it does not have to traverse through multiple data nodes. It has to be available in the next data node, in the closest possible premises of the primary data node. Right. So that is one. And when the entire region is also lost, where for some reason, when the data nodes available in so and so region or in so and so rack have all been down, let's say, for some reason, okay, some natural reasons. So in that case, you still have a backup in a different region. Okay, so that's what is being done. In general, in real time scenarios, you will definitely, or in most of the scenarios, you will not have data node blocks from different regions. Everything will be in single region. But when there is a feasibility of your data nodes, I'm talking in terms of a high level, high scale architecture. So when there are the data nodes are being spread across multiple regions and different locations, then there can be a possibility of storing the third copy of it in a different region or a different track altogether. So just to avoid the worst case scenarios. Okay, so this is how it's been said to be done, and there is no proof that how this is being configured or how this is being handled. We've not seen it manually. We've not seen it hands-on anywhere. Okay, so this is just for the theoretical sake of it. Okay, so this is how the replication is going to happen. Just keep in mind, that's it. You don't have to explain it to anyone else. Okay, right. So block replication, that is how it's going to take care of. And then we have this block caching. So we know what's a caching mechanism, right? So for frequently used information, you keep it in a specific location. So for the same reason, when the specific block is being accessed multiple times, when it is being accessed frequently, you store this particular block of data in the data node memory. Okay, so that's what we call it as a caching, so that it's going to be easily retrievable. So definitely, if you compare the differences, the data available within the memory is easily accessible or quickly accessible than the data available in the hard disk of the same machine, right? So that is why we store within the memory. And even with Spark, that's the advantage we get, right? So when the data is when the data node block is frequently accessed, then you kind of put that particular block in the uh, data node memory, and you kind of access them easily. It's going to be faster compared to the hard disk read and write. Okay, and there is again some parameters how long it has to be in the memory. If that is not accessible for say for 10 minutes or for 5 minutes, it has to go back to it has to be removed from the memory, right? So we call it as persisting in the memory, and you kind of remove it from the memory, and it has to be in the hard disk of it. Understood? Yes. See, HDFS client write and client read is something who is sending the request. Okay. So whoever is sending the request to the HDFS cluster, it can be you as well, right? So you log into a specific machine which has access to the HDFS cluster. You submit a request. Oh, CP is from so and so location, so and so file. I'm trying to write it to your HDFS or into the Hadoop HDFS. So whoever submits the request, we consider them as a client. Okay, so HDFS client write and HDFS client read. So it's a write client and a read client. That's the only difference. Apart from that, do you find anything new or anything that we need to discuss? Then we have the procedure for writing to the HDFS. There is a step-by-step procedure. Okay, so client requests to create a file, and name node is contacted once a block of data is accumulated, and name node responds with the list of data nodes. So list of data nodes as in whatever the available data nodes it has got with so and so amount of space, with available space. You'll let the client know that these are the data nodes that are available to be written, and data node receives data from HDFS client and writes to local. So after you receive the data node list from the name node, the client will go to the data nodes and it will start writing it. And data nodes forwards the file to a second data node for replication and then to the third data node. So as and when a particular block of data is written, so as and when a block is written, that has to be replicated. Okay, so it's not that the entire data will be written and then replicated on the block. This also we discussed about it. So yeah, as and when you write a single block, it has to be forwarded to the other data nodes where it has to be replicated. Then and name node commits the file creation and into persistent store. It receives heartbeat and block reports. So heartbeat signal we have seen. What is a heartbeat signal? Just to make sure that the data node is active or data node is alive. So it keeps every data node keeps sending this heartbeat signal to the name node just to make sure the data node is available. Similarly, there is also another signal that keeps on sending is the block report. So every data node has to send the block report at specific intervals. So just to keep the data name node updated. So how many blocks it is holding, just the info of how many blocks it is holding and which data node block or which file it is related to. All that information will be sent in the block report. So there is two heartbeat signal as well as a block report which the data node keeps sending at regular intervals. And then yeah, we have client gets a data node list from the name node. This is for the read again. Okay, so this is for the same read again. Like your HDFS client read will will go to the name node and it will request for the information where this particular data is being written. Okay, then we have reading the data in HDFS. So this has a lot of information, right? So this is your a client, HDFS client, and you have a read request that is being sent to the name node. So what does this read request consist of? Read request consists of information that is related to block A and block B. So I'm trying to read the block A, and then the name node will send the IP addresses of data node 1 and data node 3. So where is block A and B available? Block A is available on data node 1, block B is available on data node 3, right? So this information is being sent to the client. Similar information. So don't get scared or don't get deviated by the diagrams. I'll tell you what is the switch and all that. So read request sent to name node. Name node will send the data node information. It's just the list of data nodes. So forget about IP address of DN1, DN2. So it's all internal. So you're getting the information of the data nodes where this block A and block B are available. So now it's a job of this particular client to go and read through the data nodes. So why is this core switch available? So earlier in the write operation, it was not available because this core switch is something which is going to read the data across all the data nodes. So forget about this core switch. So read operation, how is it going to happen? It will happen on all the data nodes parallelly, right? You kind of read the data across all the data nodes. So there has to be some kind of a mechanism where it has to access, it has to control, it has to read it from different data nodes. So this core switch is helping you to read the data from data node 1 and data node 3. It's kind of try to access both data node 1 and data node 3. So earlier in write operation, what has happened is like your client has gone to the data node 1, finished all the write operation, and then gone to the next data node 2. So it's all serial, it's all sequential. So you do the write operation one after the other data node, but whereas the read operation can be done across all the data nodes, Then what is the next one? So this block A is being retrieved, and then you have block B is being retrieved. So both the information of this block A and block B is sent to the actual client from the core switch. Okay, so block A is here, block B is here, and there is also block A in data node 4 and 6. They are not being shared because this primary data block is available. These are all the replicated blocks you can consider. Okay, so yeah. So any questions on this? The diagram seem to be a bit complicated, but keep it simple. What we are trying to do is you are trying to read the data from name node. It will give you the information. It will access the internal metadata, and it will identify which data nodes have the blocks A and B. It will give the information of these data nodes where to read from. So HDFS client will go and read on top of those data nodes and retrieve the data and sends it to the client, whoever has requested it. Okay, then so right. So what are the problems faced by, there are some questions, around 5 questions, I guess. Yeah, there are some 5 questions. So what are the problems faced by big data which the legacy systems weren't able to solve? So what is it? Yes, what's the problem that are faced by the big data systems which the legacy systems weren't able to solve? There are 2 problems that we listed. Yes, anyone? What is scalability? Increasing the number of nodes or decreasing the number of nodes, scale up, scale down, and all that, right? So in earlier systems, in existing systems, do we have a provision to scale the systems, to scale the number of nodes? We can increase the systems. Yes, we can increase the systems as and when it is required, but it's not something which has come into big data only, right? So hardware failure and combining data. So in existing systems also, when we deal with some 100 GBs of data, it's not available in a single system. You remember, even the Oracle databases or whatever the SQL databases you handle, they are not on a single machine. They are also distributed. But the problem is handling the failures. How are we handling the failures in HDFS in big data Hadoop?
Just a quick info guys, if you want to make a career in big data, then Intellipaat provides an advanced certification in Big Data Analytics by ENICT Council IIT Guwahati. It is taught by IIT professors and industry experts. With more than 10 years of experience, this course is designed to upskill and land your dream job. Now let's continue with the session.
By using replications. So that is one solution we provided. And combining data, how are we combining the data? Earlier, what is the problem? The problem with combining data is when you have to retrieve the data from multiple machines, 1 GB on different machines. So for example, I have 1 GB on a single machine. I have 5 machines available. That means 1 GB on each and 5 GB overall. So if I have to run some query on this 5 GB of data file, what am I supposed to do? I'm supposed to extract the data from all these 5 machines, gather it at one place, and then run the query. But with Hadoop, what are we doing? We are not moving the data anywhere. Data is going to reside wherever it is, but we'll be moving the code to the data, right? So you send code to wherever the data is available, and that will retrieve the results. So instead of moving the data, which is a very complicated task, we are just moving the code. That is the problem we had, and that is the solution we have provided, right? So network failure and combining data. Network failure, we have not discussed anything about the network failure so far, right? None of the above is also not the answer. So the answer would be B. Okay, so hardware failure and the combining data. So Apache Hadoop is used for what? Storing and analyzing data, and storing data. So storing data, how are we doing? Which component is doing it? HDFS is doing the storage part. And who is analyzing the data? Which module, which component? MapReduce. So the core components of the core functionalities of your HDFS is, one is storing it, which takes care of which is being taken care by HDFS, and the second part is the analyzing, which is being taken care by the MapReduce component. Then which command would you use for creating a directory in HDFS? So forget about HDFS or wherever we are creating. So what is the command that we use to create? I mean, in general, what is the command that you use to make a directory? Use to create a directory? Yes, what's the answer? KDIR. So forget about where we are creating it. In general, the command used to create a directory is mkdir, right? So how many of you are comfortable with the Unix commands, Linux Unix commands? So then, what next? HDFS is implemented in programming language what? Someone's going with, oh my god, it failed in the first attempt only, is it? Okay. So it's built on Java. Okay. So Scala and Python and all that will come in Spark. Okay, fine. There is something called as a rack written here. Like we discussed about this rack concept. So rack is something where you have some multiple data nodes, whatever you say, multiple data, some group of data nodes assembled together. Okay, so data node 1, 2, and 3 have been assembled as rack 1, let's say. Physical separation, I mean, manually, as in if you're doing it on cloud, you definitely cannot do it. But that's the reason I was comparing it with the regions. Okay, so let's say if you're doing it on, I mean, see, when we have to give a justification, it has to work for all the scenarios, right? So if I say in general, in other scenarios, for example, you yourself are configuring some 10 machines to the custom. So 5 machines I've put it on one single network, one single rack, and second 5 machines I'll put it on another rack. So that is something which you can do. This is a physical separation or grouping the 5 data nodes together. But when you are configuring it on a cloud, so you cannot do that separation. So rack is definitely a physical separation. It's nothing to do with the internals of Hadoop. So when you're configuring it on a cloud machine, cloud network, so it's definitely impossible for you to configure this rack systems, right? So you definitely don't know which system is available in which particular rack. So in that case, what I was comparing is I'm comparing it with them with the regions. So US East is one region, US West is one region, and Mumbai is one region, and you have other regions also. You create some 10 data nodes in US East, another 10 data nodes in US West, and other 10 data nodes in Mumbai region. So these are all the data centers I was comparing it with, right? So when you have this separation of these data nodes, a physical separation of these data nodes done, I mean, ultimately all the data nodes will comprise to the cluster, but there is some kind of a physical separation that is happening. So there is a switch that is being that you are seeing there. So when you are trying to read the data from multiple data nodes together at a specific point of time, so read is going to happen parallelly. So when you're reading the data from multiple data nodes, there is a switch which is switching from data node 1 and data node 3. In this scenario, this switch is switching from data node 1 and data node 3. Data node 1, it is reading the data for block A. Data node 3, it is reading the data from block B. Okay, so there is only one connection. There is only one single line of operation which is reading the data from multiple data nodes, right? So your client is not directly accessing data node 1 once and data node 3 once again. So using a single switch mechanism, you are reading the data from data node 1 and 3 simultaneously, and the output you are sending it to the client together. I mean, whatever the data node block 1, block A and block B, you are sending them together to the client. That is the reason I was saying the parallel read operation. But whereas in the write operation, you will not do it parallelly. You will not write the data using a switch on data node 1 and data node 3. You will finish writing the process of data node 1 first, and then the client will send the request to write the data node 3 again. Okay. So after finishing one data node, you will move on to the next data node and write the data. But read can be done parallelly. The reason being the data is already available. You just have to know where to read it from. The data is already stored and it is available. So why waste time in reading one after the other, right? So the reason also being, for example, there is a file hello.txt, let's say, which is available in the data node 1 and 3, hello.txt. Okay. So when you're writing it, you'll be breaking that hello.txt into say some 10 blocks. Okay, 10 blocks you have broken it into, and you are writing them into data node 1, 2, 3, 4, 5, and 6. Okay, so let's say 5 data nodes I have written. that's fine. I mean, I'm breaking that into some 10 blocks and I'm writing it into different data nodes. But when you're reading it, what is the expected outcome? When I say how do you read the data is HDFS DFS hyphen cat hello.txt. This will get you the contents of your hello.txt. How am I supposed to get the data? Should I get in something like first block data I'll get in line 1, second block data I should get in line 2, third block data I should get in line 3? It shouldn't be the case, right? When I do a cat, I should get the whole hello.txt file. That means I have to read all the data nodes together. I'll have to join them or I'll have to merge them, and I have to present the read request together in whatever the format I've stored it, right? So now if you're let's say you're reading it with the form of a switch. So the first block, first data node has got the 10th block. The second data node has got the 4th block. The third data node has got the 7th block. Let's say something like that. So your switch is reading across through different data node blocks, and let's say you're arranging the data together and you're sending it in the form of a proper format to the client hello.txt. The entire file is being read and will be sent. When your client is going to the data node 1 and data node 3 separately and reading the data, the first output you get is from data node 1. Then after that, you'll get an output from data node 3. But that's not what I'm looking at. I should get the data in the form of a hello.txt file where you have all the contents together. Right? That is the reason we do a parallel read using a switch. Okay. So there is no component such as a core switch or something like this inside your client or inside your Hadoop cluster, but your name node will make sure you read from so and so blocks together, and your client will be able to your client will be able to see the data all together as a one single file. Getting it? So it is some kind of a threshold where all the data is being pulled in here and is being sent to the client at once as a single file, not in the form of a block. The core switch is kind of accumulating the data from all the other switches, and one single output will be sent to the client. Okay. Yeah. So this is having some bits and pieces of it. I'll come to the proper diagram. Okay. So like we have done using the draw.io, we'll also do some MapReduce architecture diagram in detail. But let's just try to understand what is being listed here. So we have seen as the Hadoop generation 1 and generation 2. Did you remember the discussion that we had as architecture? What is generation 1? What do you have in generation 1? Name node, data node is pakka, it's going to be there. But do we have secondary name node in generation 1? For sure. Okay. And generation 2, what did we add? What do we have in addition in generation 2? Okay, that's one. The number of clusters is increased. Okay, active and passive name nodes. Okay. But yeah, so in generation 1 you have a name node, secondary name node, guys. So name node, data node, and the secondary name node will be part of your generation 1. And in generation 2, the addition that we have made is only the active and passive name node. So just to avoid the single point of failure on the name node, you kind of created a backup name node, actual backup name node, right? So Hadoop 1 is holding name node, data node, and secondary name node. Hadoop 2 is having active passive name node, secondary name node, and then the data node. Okay. So similarly, yeah, MapReduce also has two versions of it. Okay, version 1 and version 2, generation 1 and generation 2. So MapReduce version 1 is considered as the classic MapReduce, and MapReduce 2 is considered to be a yarn, yet another resource negotiator. Okay, so yarn is a different architecture altogether. So it's not something like your HDFS where you have made some minor changes to it, but the entire architecture flow, the data flows has been changed in the MapReduce 1 to 2. Okay, so we will first understand what is the basic core concepts of MapReduce, how it is actually being developed, and what is the main purpose of it. And then we'll move on to the architecture of MapReduce 1, and then we'll understand the MapReduce 2 architecture. So with that, we will have to close the Hadoop introduction. So Hadoop HDFS, MapReduce 1, MapReduce 2 will be coming under your basic introductory course. Okay, all the other ecosystem tools were not part of this particular discussion. So after we complete this, we'll move on to the Spark, right? Then, so MapReduce, what is it used for? MapReduce is some kind of a data processing tool. So after you store the data in Hadoop HDFS location, you have to do something with it, right? You have to do some kind of processing, do some joins, do some aggregations, filters, or whatever the processing methods you have, you will be doing it on the MapReduce, using the MapReduce. So MapReduce is basically built on Java using a specific Java program. You're gonna do the transformations. You write some logic inside the MapReduce program and you submit that jar file to the MapReduce engine. It will execute and do all the transformations on the data file. You'll be providing a data file input as well. Okay. So in MapReduce, you have two more components. One is the job tracker and the other one is the task tracker. Okay. So job tracker is the master again and task tracker is the slave. Okay. So like we had name node and data node in HDFS, MapReduce has job tracker and the task tracker. Okay. So these are all called as the daemons, guys, services, I can say. So Hadoop has 5 daemons. The generation 1 Hadoop has 5 daemons. One is name node, data node, secondary name node, job tracker, and task tracker. These are the 5 daemons available in your Hadoop cluster. Okay. Daemons as in the services. So you when you run these services, your Hadoop cluster is set to be available. Right. So master is the job tracker, slave is the task tracker. So whenever you are supposed to submit some kind of a job, when you are trying to execute some query, you're supposed to send it to the job tracker that will identify the job and that will run that job using the slave machines, using the task tracker machines. Okay. Then we've seen this HDFS Hadoop 1. How is it different? We will come back to the 2.x version. What's the change that we've done? But forget about all this yarn things now. There is another document altogether available for yarn. So don't worry about all this now at this moment. Okay. So I'm just quickly moving to this HDFS is done. And yeah, so this is some diagram for the secondary name node, guys. If you just look at it, this is your name node and this is your secondary name node. So there is a metadata available in the name node. So it's going to pull the metadata, it's going to keep a copy and sends the metadata after keeping a copy. Okay, so it's just pulling the data, keeping it in the disk, and then sending it back to the name node. This is the functionality of your secondary name node. So someone was asking for a diagram, the secondary name node diagram, right? So this is how it's going to interact with the secondary name node. Then that only accesses the master name node. I mean, that's only going to interact with the master. It's not going to interact with any of the data nodes. So we are coming back to the again. We are getting confused again. Okay. So a job is a full program, MapReduce terminology. We have something called as a job and a task. So job is a complete set of a program that we have written. The entire execution is called as a job. And when you break that job into multiple chunks of activities, you call them as task. Okay, right. So client is submitting a job to the MapReduce engine. That means there is a jar file or there is an XML file in using which you'll be submitting the data. You'll be submitting the program. Okay. So along with the jar file, you'll be providing the input location of the data and you will be submitting it to the master, to the job tracker. So this is a difference, guys. On the left hand side, you have this MapReduce. On the right hand side, you have this HDFS related information, right? So when you're supposed to load the data, whom are you going to connect to? You're connecting to a name node, right? You're sending a request to the name node and you're storing the data on the data nodes. So this is this, right? Block 1, block 2. What is my data? This is my data is my file. I'm trying to load it into so and so blocks. Now, after loading this my data, you're trying to run some queries on this my data. You're trying to write some program and evaluate some data on the my data file. So whom are you going to submit this request to? You'll be submitting that program to the job tracker. So now the job tracker is running the task trackers on top of the data nodes where the data is available. Getting it? So there is a data available on your HDFS on some so and so data nodes. So as and when you receive a program, as and when you receive a job to execute, it will interact with the name node and identify which location the data is available, right? So after you interact with it, after you find the data nodes, the task trackers will run on top of that data nodes to execute that program. Okay, so now going back to the actual diagrams, right? So this is your master, which is going to be your job tracker, this one, and these are all your task trackers, right? These are all your task trackers. On the other hand, there is HDFS. Let's say this is your HDFS, right? So now I'm writing a program. Let's say I have some. So the file is voter so dot csv. Okay, in voters.csv, I have the voters list for district A for 3 parties. For parties A, B, C, right? So the data is for so and so district, and you have the voters count for parties A, B, and C. The entire A, B, and C, you have some data. So voters.csv consists of some 10 lakh records, let's say. Are we clear with this scenario? Voters.csv is my file, which consists of some 10 lakh records. And this 10 lakh records are available in the HDFS in the form of a voters.csv file, which is consisting of the parties A, B, and C votes list. Okay. So for each and every candidate, whichever party they have voted for, that particular number is, that particular information is available in that CSV file. So now I store this voters.csv file in HDFS. I sent a write request to the HDFS cluster. That means I'm sending a write request to the name node. And I have written this voters.csv into, let's say, 4 data nodes. Agree? Please, I have written this data into 4 different data nodes. For our convenience, let's say, I'm dividing the data equally across 4 data nodes. Okay, so there is no need of dividing it, but let's say I am dividing it into 4 data nodes equally. That means each data node has how many records? 25,000 records. Oh, no, sorry, 2.5 lakh records. Agree? So 2.5 lakhs each on each data node. I am dividing it into 4 data nodes in your HDFS cluster. This is my scenario. Got it? So now I loaded the data, I have the data ready. So now I am supposed to calculate the winner, the final winner, whoever is receiving more number of votes will be the ultimate final winner, right? So now I have to calculate whoever has got the more number of votes. So I'll write a program here. So I'm gonna write a program somewhere here. MapReduce program. See, MapReduce program is a Java program generally. So MapReduce program, you have written a logic. MapReduce program consists of 2 classes. How many of you are comfortable with Java, or at least have some basic knowledge of Java? You know what is a class, what is a method? Everyone, right? You know, at least you know what is a class, what is a method. So a Java program, a MapReduce Java program always consists of 2 classes. One is a map class, one is a reduce class. Okay, a mapper method as well as a mapper class as well as a reduce class. So you have to write some logic in the mapper, you have to write some logic in the reducer. So that is why we call it as a MapReduce program. So by default, it's going to be mapper and a reducer. So what happens inside that, on all that, we will discuss that later. So I have written some program, I have written some mapper logic, I have written some logic 1 here. In reducer, I have written some logic 2 here. I have written some program and I have converted this into a winner.jar file. This is the jar file that I created out of this MapReduce program. Okay, so I submitted this jar file along with the location of the data, home, training. So here, this voters.csv is loaded in, see, if you are writing it into HDFS, you'll find some location allocated to it. So home, training, and then you'll find some directory where you will be storing this data/voters.csv. This is the location of the file in HDFS. So similar location, I'll have to provide that in the jar also. In the jar file, along with the jar file, data/ voters.csv. This is my input. This is my program, and the input for the program is the location of the data. You submit this to your job tracker or the MapReduce engine, for example. So what has to happen now? You submitted the program, you submitted the input file location also. So first, my MapReduce engine, I mean, when you're submitting a request to the MapReduce, that means you're submitting a request to the job tracker only. That is again the master, right? So your job tracker will analyze the program and will also look at the input data. So it has to validate whether this particular data is available in HDFS or not. So job tracker is interacting with your HDFS first, as and when a job is submitted, it is interacting with your HDFS whether this voters.csv file is available. Yes, it is available. If it is available, in which data nodes it is being written into. Understood? So the input information will consist of list of data nodes holding voters.csv. Agree? So it is available in HDFS, but in which data nodes it is available? Only then, if I know which data nodes, only then I'll go and run that query, right? Job tracker and the task trackers. Agree? Master and the slaves. Clear now? Job tracker and the task tracker. And on the other side, forget about these lines now. At least now you can forget about this. Let's say forget about all this content. There is HDFS on the other side. Okay. In HDFS, what did you do? You have written some data. Okay. So what is the data that you have written? You have written the voters data, which is voters.csv. So you have written voters.csv file. And when you write some data, you will have some location allocated to it. So home training data voters.csv is a location in HDFS where this voters.csv is written. So this voters.csv consists of some 10 lakh records for a so-and-so district for parties A, B, and C. So A, B, and C votes have been polled, and 10,000 people have polled this record, polled these votes, and the data is stored in the form of a CSV file. Now this CSV in HDFS, I have divided it into 4 data nodes. I have to write it into data nodes, right? So I have broken that into 4 data nodes, and for our convenience, for simple use case, we are breaking it into 4 different data nodes equally. So each data node will have 2.5 lakhs of records. Are we clear so far? 4 data nodes, each data node 2.5 L. Okay. Now the data is stored here. This is done and dusted now. Now we will have to run a program. So after you load the data, what you need to do? You need to write some program to it. Agree? So you are writing a program. You are writing a MapReduce program with 2 classes. One is map class and a reduce class in it. So that's the reason we call it as a MapReduce programs, which is having a mapper class and a reducer class. So what do you write inside the mapper and reducer? Let's not worry about it now. Okay, I'll tell you what we need to write, how we can define the logic. So I have written a mapper logic. This is logic 1, reducer logic, logic 2, and I have converted this into a jar file, that is winner.jar file. Along with that jar file, I'm sending the location of the data in HDFS, right? So this details, I'm submitting it into the job MapReduce engine. So MapReduce engine, as in you're submitting it into the job tracker only ultimately, right? So job tracker itself is going to be the master, right, for us. So you're submitting it into the job tracker. So after your job tracker receives the jar file as well as the voters.csv location, what it has to do initially is it has to validate whether the specified location is available in HDFS or not. Okay, whether this specified location is available in HDFS or not. So my job tracker is, what is it doing? It is interacting with the HDFS, that means with the name node, to validate whether this voters.csv file is available in HDFS or not. If it is available, in which data nodes it is available. So what is it going to get in return? It is going to get the list of data nodes which are holding the voters.csv file. Agree? Data node 1, 2, 3, and 4 are having this data of voters.csv file. This information has been shared with the job tracker. Agree? Any questions? So depending on the number of data nodes, or if I can get into the details, number of blocks. So forget about number of data nodes at least. So how many blocks this particular data node, this particular data has been written. Let's say I'm writing it into 4 different blocks, right? That is what we discussed. So I have written the data in HDFS into 4 different blocks. 4 blocks of data is available. So depending on the number of blocks of data in HDFS, your job tracker will split so many map tasks. So this entire winner.jar is a job, right? I'm submitting a job. Under this job, there is a task called as map. There is a task called as a reduce. So these two are the individual tasks. Okay, map task and a reduce task together called as a winner.jar. So whatever the program that you have written in logic 1, whatever the program you have written in mapper, that is being split into the number of input blocks. So how many input blocks are available? 4 input blocks are there. So how many map splits will be divided? 4 map splits will be divided. That means in simple terms, let's say, so I have written a program. Let's assume this is what I have written in the mapper. Okay, so simple use case. What is it going to write? It is having a program to find votes for each party. This is what I have written in the program. Given an input with whatever the input you have, whatever the input you are running in, it just identifies how many votes are for party A, how many votes are for party B, how many votes are for party C. This is what I have written in mapper. This is the logic I have written in mapper. Okay, so you have to run this logic, and it you will generate an output saying party A has received so many, party B has received so many votes, and party C has received so many votes. So this is the program that I have written. So now this program, I'm dividing it into 4 splits. 4 splits as in I'm duplicating it into 4 splits. So the same program you will duplicate into 4 splits. Why is 4 splits? Because I have 4 blocks written in HDFS. So for each block of data, your map split will go and run on top of it. So number of blocks, depending on the number of blocks, your number of map splits will be defined, so that each map split will be assigned to each block of data. So here, this task tracker running map split 1 on input.
Just a quick info guys, if you want to make a career in big data, then Intellipaat provides an advanced certification in Big Data Analytics by ENICT Council IIT Guwahati. It is taught by IIT professors and industry experts. With more than 10 years of experience, this course is designed to upskill and land your dream job. Now let's continue with the session.
And the same other task tracker is running here, which is of it's running map split 2 on input split 2. So what are they supposed to do? They have to execute some tasks. Task trackers are meant to execute some task. So out of the given job, your job tracker has divided mapper into 4 duplicates, 4 duplicate code, and each piece of code is been submitted to each task tracker. So what they have to do, they have to go and run on top of the data block that they are available, wherever the data is available, in whichever data node. So this task tracker will run this map split 1 piece of code on top of the first block of data in HDFS. Are we clear so far? This is a bit confusing, but when we get into the details, we'll have some better clarity. So number of map splits is what? Number of input blocks. So input blocks are 4. So I divided my mapper's logic into whatever the program I got. I duplicated the program into 4 copies. Each copy I'm sending it to each and every task tracker. So each and every task tracker has to go and run on top of the data blocks where the data is available. On top of each data block, I'll have to run this, execute this map split 1. So what am I going to get as an output? What is my task tracker 1 output going to be? Task tracker 1 output is number of votes for party A, comma B, comma C on how many records? 0.5 lakhs of records. So this is task tracker 1. Similarly, task tracker 2 output will be same on the other 2.5 set of records. Agree, guys? Are we clear? This is task tracker 3. So are we agreeing with the concept of moving computation to the data? So the data is available in HDFS. We are not moving the data anywhere. We are moving the code, whatever the code you have written in the form of a mapper. You are moving the code using the task tracker. You are running the code on top of the data wherever it is available. You are going to the data node, you are going to the specific block, and you are running this task tracker and you are extracting the result. You are only getting the result here. So now you have got the output from task tracker 1, task tracker 2, task tracker 3, and task tracker 4. What is the output you got? You only got 3 records. That is party A, how many votes, party B, how many votes, and party C, how many votes. That's it. So now you have to send this output of all these task trackers to your job tracker. Your job tracker will accumulate the output from all the 4 task trackers. Now what it has to do? So that is going to be written in the reducer, right? So the mapper is the individual activity that is happening, and reducer is the summation. I mean the activity that is applied on top of the outputs of the mappers. So your reducer logic will look like this: accumulate results for each party and find maximum, right? So that's what I'm going to do. After you receive the results after you submit the results to all the from all the map task trackers to the job tracker, your job tracker will run the reducer logic on top of it. What it is going to do, it's going to add the votes for each and every value from each and every task, and it's going to accumulate the data, and it's going to find out the maximum, which whether party A has received maximum, party B has received maximum, or C has received maximum. So that's going to be the winner. That output will be sent to the client. So it only depends on what you write in the program, what you write for the mapper or what you write for the reducer. So depending on the use case, depending on the requirement, you are defining the logic as, okay, finding the votes is the mapper and accumulating the votes is a reducer. For a different use case, there can be a different logic altogether. Okay, see, always mappers are going to get submitted to the task trackers and they're going to get executed first. So whatever the program you write, you can tweak and make the changes and execute it. But again, like when you want to change it to reducer and mapper, then the entire logic of operations will change, right? One map class, one reducer class. Yes, there is only one map class and there is only one reducer class. But yeah, I can also come to that. You can have multiple map classes depending on the scenario. That again we have to discuss. Yeah, I'll come to that. But let's not complicate it at this moment. Are we clear? So we've been discussing about the MapReduce architecture. MapReduce has 2 daemons again internally. One is the job tracker. The other one is the task tracker. Job tracker is considered to be the master, and all the other task trackers will be the slave machines. So after you write the data into HDFS, so we have considered an example of voters.csv file. You have written into HDFS. You have sent a request to the name node that and the data node have stored the data. And the data location is home training data voters.csv, and we've divided this into 4 data blocks. 10 lakhs data is are you seeing my screen? So 10 lakh records, each divided into 2.5 lakhs, and we're dividing it into 4 different blocks. And after you submit a request, after you create a job, you have written a program, and you've also given the input file location to the job tracker. This will analyze the MapReduce program, and it will interact with the HDFS name node to identify whether this voters.csv file is available in HDFS. If it is available, how many blocks it is loaded into. After you retrieve the number of input blocks, your job tracker will divide the number of map tasks into so many input blocks. Okay, and then each map task will be allocated to the available task trackers. This task trackers will go and run this job on the data blocks where the data is available. Okay, so you retrieve the results from each and every task tracker, right? And then you do a reduce task, which will collect the output from all the map tasks and will do an aggregation and find out the final winner of the lot. Okay, this is the flow. Then let's move on to the next one. We'll have to do a theoretical programming of how a MapReduce program can be written and how the execution flow is going to happen. Okay, so for that we'll take an example of word count program. You must have heard about word count, right? Okay, let me open a notepad. Yes, are you seeing the notepad window? Right, so we'll have to consider an input. Input will be hello.txt file. Okay, so this hello.txt is having a data something like this. Okay, so this is the content of your hello.txt, some text content. Okay, and what am I supposed to do? I'm supposed to find out the word count. That means how many times each and every word is being repeating. Okay, so how many times welcome has been repeated, how many times Hadoop has been repeated. This is my simple task. Okay, so every MapReduce program, I mean, everything has to start with a word count program only generally. So we start with a word count program and try to understand the different features of it. Okay, so you understood the question. Hello.txt is my file, and this is the data available in hello.txt, and you're supposed to find out how many times each and every word has been repeated. Got it? Now, firstly, you're supposed to write a MapReduce program for this, right? So one thing you need to understand is every MapReduce program, for that matter, any MapReduce program that you write or MapReduce engine will only understand the data in the format of a key and a value pair. Okay, just sorry guys, just give me a minute. I have to take this off. So this is a scenario. Hello.txt is a file, and we are supposed to find out the word count of the hello.txt file. So initially, so before we get into the MapReduce program, your MapReduce program mapper as well as reduce or whatever the phases you have, it's only going to understand the data that is in the format of a key and a value pair. So we have something called as a MapReduce engine as in something which is facilitating or which is executing the MapReduce programs. Okay, so whatever the core functionality of the MapReduce architecture that we have seen, right? So that's the MapReduce engine that we talk about. So MapReduce engine will make sure your data is converted into the key and a value pair before it is being submitted to the MapReduce program. The mapper class, the reducer class, or the main method, everything will have the parameters in the format of a key and a value pair. Okay, so that means your input has to be in the format of a key and a value pair for your MapReduce program to read it and to evaluate it. Okay, so what you need to do, you need to convert this data. Even in the previous example, the voters.csv file we have taken, right? So that also has to be converted. That is everything being done internally. I mean, you're not doing anything in this particular case. Okay, you'll not define or you'll not write any a logic for the conversion also. So MapReduce engine itself will convert the data and it will make sure the data in the format of a key and a value pair. So now this is your input file, and I'm dividing this input file. I'm loading this input file in HDFS into this location, home. Okay, so this is how the directory structures will be in HDFS: home, training, data, and hello.txt. And the data is divided into 3 blocks. Okay, block 1, block 2, block 3. Let's assume this is my first block. Simple line by line separation. Okay, I'm breaking this into 3 blocks. It can be anything. I mean, it can break into different numbers of blocks also, but let's understand this is being divided into 3 blocks, and it is loaded in home.training /data/hello.txt file location. So now I've written a MapReduce program. My MapReduce program is word count.jar. Okay, word count.jar is my MapReduce program. Along with it, you have given a file name called as input file name is input file path is /home. You have this path already, right? So as and when you submit this, what is going to happen? Your job tracker will go to the will receive this request, word count request, and the input file location it will receive, and your job tracker will go and hit the name node to identify whether this hello.txt is available in so and so location. If this is available, how many blocks it is being divided into. That's what the information we get from the name node, right? So the reply will be yes, available, something like this, acknowledgement, and in 3 blocks. So it's available in 3 blocks, and you also have the data available with this particular location. This is the data block that is available. So now after your data, the job tracker receives this information from the name node. So this has to make the data readily available, or this has to make the data, this has to convert the data in the format of a key and a value pair, right? So for your program to run, your data has to be in the format of a key and a value pair, right? So what it will do, it will take the block 1, it will convert into a key comma value. So how is it going to convert? Is the key comma value pair for this data block is the data comma key will be the offset. What do you mean by an offset? Offset is some kind of an address location you can consider. Okay, some address location of this particular block. So wherever it is available, 1001 or whatever, some dummy address location. So this is my first key comma value pair. So key is by default being considered as an offset, and value is the data. Okay, the entire whatever the data you have here in the block will be considered as a value. Similarly, for other blocks also, your key comma value pair will look something like this: 1032 comma this one, and something like 1060, the address comma the data block. So this is the 3 key comma value pairs available for you. This offset allocation is dynamic. I mean, we are not being involved in this offset allocation. So your MapReduce engine will convert the data into a key and a value pair, whereas key will be an offset. Okay, so whichever offset it is available, maybe the location of the first character will be the offset, and the location of the next line first character will also be an offset, right? So you're not being allowed, or we are not even being involved in the offset allocation here. Okay, so it's just an offset, and some address of that particular file location or for that particular block location will be considered as an key here. Anything. This 1001 is something which I gave just to show that. Okay, so it can be anything. It is being allocated by the MapReduce engine itself. We are not being involved anywhere here. We as a developer will not even look at this particular data. Okay, what we only need to understand is it got converted into a key and a value pair. Okay, and why is it supposed to be done like this? I mean, why are we actually creating this key comma value pair in this format only? So there is an input format available. See, when the data is in the format of a text input format as in whatever the input file that you have, hello.txt, or whatever the data you have is in the form of a text input format, this is the conversion methodology. If the data format is in the format of some sequence input format or file input format or key value text input format, there are 4 different input formats available. Once we get into the theoretical session, we will see. One is the text input format, one is the sequence input format, and one is the file text file input format, something like that. Okay, there are 4. So if the data is considered to be in the format of a text input format, this is how the data key comma value pair conversion will happen. If the data is in the format of a sequence file input format, then there is a different format of conversion. Okay, so most of our inputs that we deal with are going to be text input format only, generally. Whether it is in the CSV or whatever, the data will be in the format of a text only. Okay, so your text input formats will have a default conversion methodology, which is an offset will be a key and value will be the data. Clear? Any questions in this? Right. So after we converted this data into a key comma value pair, what are we supposed to do? We were supposed to send it to the mapper first. So in MapReduce program, you have mapper class and reducer class. Okay. So first mapper class will receive. Okay. So before that, there is also one more functionality in between. So you have 3 blocks of data. How many map splits have to be divided? Number of map splits equals to number of input blocks. Okay. So your job tracker has divided 3 map splits. So this is your map split 1. What is it? Map split 1 will receive the input for this one. This is gonna give you this is gonna be the input for your map split 1. Agree guys? Right. So 3 blocks of data you have, 3 map splits you will be dividing. So your MapReduce program will have two logics. One is map code, mapper code, and reducer code, right? So your mapper code will be divided into 3 duplicates, 3 copies of mapper code. So each mapper code will be sent into this particular map split 1, map split 2, and map split 3 will get executed. Okay. So here you have mapper code execution running. So here you'll be running a mapper code. What do you run here? So your mapper class, whatever the program that you have written in the mapper class, that is what you are going to execute here, right? So mapper class will have 2 arguments, key and a value argument. So this input is in the format of a key and a value pair, and the arguments are matching, and you have the data in the format of a key and a value pair, and you will be reading the data. So now what I'm going to do in the mapper code, I'm reading only the value. I'm picking the value, which is this. I'm not even worried about the key here, because that's just the dummy offset that it is being allocated, right? My actual data is available where? In the value only, right? I'm reading the data in the format of a value. I'm reading the value out of the key comma value pair. And what I have to do now? Any suggestions? What logic we are supposed to implement? Nothing related to MapReduce. So in general, this is your string, right? I'm converting this into a string. I just have to find out the word count of it. How do you do it? So first operation is split by an empty space. What is it going to get? I mean, what output you are going to get? Welcome is 1, 2 is 1. Your string is divided into these output files. This is the output you got, right? So after you do a split by space, this is the output you got. What do you do next? I got this as an output. And what do you say? What do you do to the mapper output? What are you supposed to do with the mapper output? You're supposed to send it to the reducer, yes or no? But your reducer also will have the input parameters as a key and a value. I mean, it's only going to accept the data in the format of a key and a value. So your mapper output also has to be converted into a key and a value pair. So what do you do to convert this mapper output to a key and a value pair? I'm doing this. I'm allocating 1 by default, saying that key is the data, 1 is the value. Any harm doing it? So I have taken the value out of the key comma value pair from the mapper arguments. I've taken the value in the form of a string. I've done a split by function on the space. After I receive the output in terms of individual values, individual string elements here, I'm allocating them, I'm considering them as a key, and I'm allocating 1 by default as a value. Why are you allocating 1 by default? Is like that's my own logic I've written. Okay, this is all being written inside the mapper program. Why only 1? Why can't I allocate something like dummy A, B, or C, or something like that? You can also allocate whatever you wanted to. Okay, the reason why I'm allocating 1 is I'm telling that this is one occurrence of welcome. This is one occurrence of 2. This is one occurrence of Hadoop training and program. So for each and every occurrence of a value of a string, I'm allocating some number to it. That means this is one occurrence of this particular value. Ultimately, what is my goal? I have to find out how many times this value has occurred, right? So how many times this has occurred here? It has occurred once. And how many times training has come? This has come once. How many times Hadoop have come? This has come once. Something like this. Agree? Now let's see what is it going to happen. So here we have welcome. So what is my mapper code supposed to do? It is going to do a split first. It's going to pick value, right? Pick value from the key comma value pair and apply split on space. Yes. And what is my output going to be? In general, what is my output? Welcome.
And then welcome is
and then the third line will be spark. So this is how your split output will be if you are not aware of it. So after you do a split, it's going to break it into space. Now what am I supposed to do? I'm supposed to allocate 1 by default just to make it look like a key comma value pair. What is it going to come now? No, see, this is an individual mapper output, map split 1 output, which is this. Okay, by default I'm allocating what? I'm allocating 1 as by default value, regardless of whatever key you get. Okay, the only reason why I'm allocating 1 in this particular scenario, at least let's assume for now, the only reason why I'm allocating 1 is just to make it look like a key comma value pair. And why I'm allocating only 1 is to tell that this is the occurrence of 1 occurrence of welcome, 1 occurrence of 2. Okay, so here also this is 1 occurrence of welcome, this is 1 occurrence of 2, and even though I got another welcome, I still am allocating 1. I didn't write any additional code for identifying whether the same key is available here. If there is a same key, I'll have to give 2 for it. I didn't write all that code. Regardless of what data you have in the form of a key, my only logic is to allocate 1 by default. Agree? Yeah. See, I mean, let's not get into that key and a value pair. See, keys are, this is just looking like a k comma v format. Okay, key and a value pair. Okay, so it's not a unique key that we are talking about. Okay, so this is my map split 2 output, and similarly map split 3 output also I'll write. So just tell me, I'll definitely write the output. So which is going to be welcome comma 1. I'll give you a proper reasoning why we have to allocate only 1 at the end of this discussion. But at least for now, let's look at this. Welcome to training program, is it? Comma 1, program comma 1. This is map split 3 output, right? So all these 3 outputs, where they have to go? They have to go to a reducer. Okay? All the 3 outputs of mapper, where are we supposed to send them? We are supposed to send it to a reducer. Now, right, this I can call it map output. Map split 1, 2, 3 together, everything will be a map output. Now where am I supposed to send them? Reducer. So looking at this output, what can I write inside my reducer? What logic I can write inside my reducer? So reducer also is in the format of a key and a value pair. Fine, that's okay. What do I have to write inside my reducer now? Tell me. Okay, so I'll find out key. I'm just writing it in a theoretical way. Okay, find repeated keys, right? And repeated keys and count them. Count values. Yes, this is what we are talking about. Agree? Right? So after the map output and before the reducer, the logic might not change, but there is something called as shuffle and sort. So this is not, I mean, you're not going to write any program for shuffle and sort. Your MapReduce engine will take care of this shuffle and sort operation. The only logic you're going to write is for mapper, and the other logic is for the reducer. So what is shuffle and sort doing is, it will shuffle the data according to the different keys. Something like this. It will shuffle something like this. Okay. Welcome 2, 3, 4. All welcomes together, all 2s together. The 2s are there, 3, right? 2s together, and all programs together, and all trainings together. Just forget about, I mean, whether they are 2 or 3, that's okay. Okay. And this is 1. So this is what your shuffle and sort doing. So the major operation, the main operation of your shuffle and sort functionality is just to make sure whether you have received the output from all the 3 mappers or not. See, I received the first map split output, that's fine. I received the second map split output, that's fine, but I did not receive the third map split output. I cannot send it to the reducer, right? So this shuffle and sort is some kind of a threshold where it will wait for all the map splits executions, all the task trackers to complete their execution and send their outputs. So I know that there are 3 task trackers allocated, 3 map splits and 3 task trackers allocated. So my shuffle and sort has to wait until you receive the output from all the 3 task trackers. This is some kind of a threshold, a checkpoint, I can say. Okay. So after you receive from all the 3 outputs, 3 map tasks, I'll be doing a shuffle and sort, and I'll be allocating the unique keys together. Understood? A simple operation. That's it. So can I write something like this? Find after that, okay, shuffle and sort output you got. This is you are sending it to the reducer. So now this is how you have the data. You are finding the repeated keys and you are finding the count of values. Can I do sum of values? Finding the repeated key, and I'll do a sum of the values. Okay. So it is just waiting. It is just making sure the data is executed. I mean, all the mappers have executed the tasks. That's it. Okay. And after you receive the output from all the mappers, it is just shuffling it and sorting it. That's it. Sorting it some depending on some order. Anyway, if there is no sorting also, there is no problem, right? We are anyway doing the read operation on top of all the results here, right, in the reducer. So you are finding the repeated keys, and you are even finding the count of the values, or you can also find the sum of the values. Agree with this point? You can do both. Both will result to the same output. This is where the result will come into. So why am I allocating only 1 by default is, this is my code, right? I'm allocating 1 by default. So for example, you contradict to the statement and say that, okay, I can't allocate 1 by default. I want to allocate A here, right? Some dummy value, you write whatever, you write your name also, whatever, right? But some unique value. So in this case, your outputs from mapper 1 you're allocating A, and outputs from mapper 2 you're allocating B, or outputs from mapper 3 you're allocating C. So at the end you will receive welcome comma A, welcome comma B, welcome comma B, welcome comma C, right? If you get like this, what is your reducer? If you're allocating different outputs other than 1 as by default value, what you need to write? You need to find out the repeated case, and you need to find out only the sum of it, as count of it. Sum will not work in this case. So depending on what you write in your mapper, you're changing the logic of your reducer. That's it. Okay. So there is no necessity that you're supposed to allocate 1 only by default. Okay. You can allocate whatever you wanted to, but based on the data that you send as an output from the mapper, so what output you're receiving from the mapper, depending on that, your reducer code will change. Okay. So now that I'm allocating 1 by default for all the values inside the map split, I can do whatever I wanted to. I can do a count of values, or I can do a sum of values also. So now in this case, can I do something like this? Reduce by key. This is a function that I'm going to use. Using the reduce by key function on this particular input, it is going to generate me an output something like this. Welcome comma 4, 2 comma 3, program comma 1, 2, training comma 3, and spark comma 1. This is what I get. Agree with this? Okay, fine. So this is how you execute a MapReduce program. Okay, so this is the logic. This is what you're gonna write. You write some code in the mapper. Depending on the mapper code, you define your reducer logic, and you can find the word count. So now we will think about some enhancements to this. Okay, so this is a core program. Mapper reducer is the core program. On top of it, what are the other enhancements that you can do? So if you look at the map split 2, so someone was pointing out, so there is welcome comma 1 here and welcome comma 1 here. Why can't we do welcome comma 2 here itself? Rather than sending 2 welcomes, you can only send 1. See, what I'm trying to say is, see, the output of map split 2, how many records do you have? 1, 2, 3, 4, and 5, right? But I'm sending welcome twice. So why do you have to send welcome twice? Why can't I do welcome comma 2 and I only can send 4 records there, right? It's anyway the duplicate. Why can't I do the aggregation here itself? What I mean to say is, so I'm converting this into this. So you understood this thing? Map split 2 output. Earlier I was sending 5. Why can't I send only 4? What is the advantage I get using this? See, I was sending 5 earlier. Now I wanted to send only 4. Why can't I send 4? The advantage I get is I reduce the network traffic between the tasks. Okay, so map task is 1, reduce task is 1, right? So how many records am I sending between the map tasks to the reduce task is the network bandwidth, I call it. So now I'm sending, so let's say some 20 records I'm sending. How many are there? 80 to 93, right? 13 records I have, right? So 14 records I have. So I'm sending 14 records here in the previous scenario. Now by doing some aggregations within the mapper task, I'm only sending 13 records. That means I'm reducing the number of records that are supposed to be sent between mapper and a reducer. See, it does not make much of a difference, 14 and 13, right? But when you have more number of records duplicating like this within the map task, it's going to make some difference, right? When you are dealing with large amounts of data sets, instead of sending the data again and again or multiple times repetitively across the same task, you can do some aggregation and filter all the repeated values and send the output to the reducer. It's reducing some burden on this task. Which shuffle and sort? Yeah, shuffle and sort will remain the same. I mean, that doesn't
No,
make
no,
any
no.
change.
That means it will take less amount of time to do that.
Less amount of records to process. See, in
Yeah.
this particular scenario, it's only one additional record we are sending, but in general, when you're dealing with large amounts of data sets with duplicate values within the same splits, same task, right, then it will definitely make some change. So okay, there is a use. I mean, what I'm trying to conclude here is there is definitely some use in reducing this duplicate values, but how do you do it? Tell me. So what am I supposed to do here? I'm supposed to convert this welcome comma 1 into welcome comma 2. How am I supposed to do it? Checking the duplicate keys and do what? What is that logic? Is it not the logic of a reducer? Means before sending the output to the reducer, I'm actually executing a reducer within the mapper itself, within the map split. Understood? So inside this map split 2, I'm calling a reducer function or reducer class. Why am I calling this reducer class? Just to remove this, just to further aggregate it. It's not about the duplicates always, but just to further aggregate it. Anyway, we are supposed to do the same thing in the reducer phase, but why am I still going to the reducer and doing it? I can do it within the mapper itself, right? So by doing this, what is happening is you are executing the reducer within the individual mapper split only, within the individual mapper task. Getting it? So in the mapper code, what you are supposed to do is, see, in mapper code, inside the mapper code, you have to call this reducer function, call reducer class. So calling this reducer class inside the mapper code is called as a combiner logic. So mapper is 1, reducer is 1. Inside the mapper, you will be writing a logic for the combiner, which is going to in turn call the reducer function. You're not writing any additional class for the combiner. It is one single line of code that you're going to include inside the mapper class, which will in turn call the reducer function. Agree? So instead of going to the reducer and executing those tasks, I'm applying a reducer function within the individual mapper task only. That running of reducer class within the individual mapper class is called as a combiner class, combiner logic. Okay, so combiner is going to reduce the network traffic or the number of records that you're going to traverse through from mapper tasks to the reducer tasks or to the shuffle and sort task. That is one way of the performance enhancement. See, how am I compromising on the code? No, right? It's only one line of code. It may take some time for the execution, but if it is worth it, then it's definitely going to be helpful. We are not increasing the number of lines of the program here. We are only just adding one line of code. You are just calling the reducer class there, right? So by calling a reducer class within the mapper class itself, you are removing the aggregate. I mean, you are combining the duplicate records or combining the repetitive records and reducing the number of outputs that you are sending it from the mapper. Any questions? Are we clear with this? Map split, map logic, reduce logic, shuffle and sort logic, and a combiner class logic. So this is one of the performance enhancement that we have, which is going to reduce some network traffic between or some number of records that are sent between the tasks, individual tasks, map to shuffle to reduce or whatever, right? Which is going to reduce the number of records. And there is one more performance enhancement. So we cannot call it as a actual performance enhancement, but the enhancement of the particular output. See, for example, I have this as an output, right? Reducer class is giving me this as an output. What if I'm saying, see, when you look at the output path will look something like this in HDFS. You are saying the output again in HDFS only. So your output will be stored in somewhere like this, home training. You give some output, and under output folder, you will have part hyphen 0000005. So under output folder, you will have part hyphen 00000 file name and also a success file name. So this is the format of the output file. Okay, so don't get confused by this. So part hyphen 00 output file will be your, this is going to sit in this particular location, in this particular file. Okay, and there is a log message, that is a success message. For every successful MapReduce execution, you will find a success message listed. There is nothing written in this, it's just a success empty file. Okay, and you will have a partition file 00000 with the output in it under the output folder. Okay, so now this is my output file, but what if I want to do something like this? See, our partition output file will have all these outputs. So what I want to do is I want to generate an output file which consists of values only which are repeating more than once. That means only which are, whatever the values are repeating more than once, only those values I need. I don't need the values which are repeating once, only once. Okay, I just have to segregate, or I just have to partition the output into two, wherein one folder will have the output where which are repeating more than once, and the other file will have the output which is only repeating once. Or otherwise you can just ignore these values. I just want to find only one output file wherein it should generate only the data that is repeating more than once, right? Even in the earlier scenario, voters.csv we have seen, right? So output file, what does it show? Party A has received so many votes, party B has received so many votes, and party C has received so many votes. This is the output you get.
Yes.
But why do you have to think about party B and C when you have party A as a winner, right? So my output file should filter the data according to the maximum number of votes, and it should only generate an output file which has got the more number of votes, right? That is, you're filtering the output and you're only receiving whatever the output you need, only filtering whatever the required output you wanted to generate. So here my required output is whichever words have received the count more than once, I wanted to load them in one file, and all the other dummy values I wanted to load them in the other file. Or more than 3 or 4 times I wanted to generate, I'll load them into one file, and other values will load into another file. So this is what you call it as a partitioning of your output. Okay, so we do a partitioning of your output file depending on the user specific scenarios. So depending on whether you wanted to filter them or whether you wanted to divide them into two different files, all that you will be doing that. So there are two ways of partitioning it. So in again, like we have done in mapper and reducer, you have to write a partitioner class for it. So in partitioner class, you are supposed to write some program. You are supposed to write some logic for it. Okay. So there are two ways of doing it again. One is dynamic partitioning and custom partitioning. So in dynamic partitioning, you just have to specify how many partitions you are supposed to divide them. Let's say 2. In dynamic partitioning, you're not supposed to, you're not required to write any logic. See, I only wanted to divide the output into 2 partitions. How am I going to divide? I'm not defining any logic for it. The system itself will define it. So let's say if I tell them that I need 2 partitions, let's assume greater than 3 and 4 will be one partition, and less than 3 and 4 will be one partition. Divide depending on the amount of output that you have. It will try and divide the output into 2 different partitions. It will break the output into 2 different partitions. If there are more number of records greater than 4, If there are less number of records greater than 3, it will find out another viable, logic. Okay, some dynamic way of partitioning it. Okay, we are not having any control on it. System itself will decide which data should go into which partition and which data should go into the second partition. Okay? So this is dynamic. You're not specifying any logic here. So what you tell is only the number of partitions. So set number of the value, that the parameter that you're going to set here is this is not written in the partitioner class, but this is written inside the main method itself. So you have to write set number of reducers is 2. Set number of reducers to 2, as in you are telling the system to create 2 partitions and you're not writing any logic for it. That means it's going to be collected dynamically. And in custom partitioning, you set the number of partitions to 2 and you define the logic in the partitioner class. What logic you're saying? Okay, count greater than or equals to 3 will be first partition, and else all the records will be second partition. Getting the difference? Dynamic partition and the custom partition. So dynamic partition, you'll only tell the system that you need 2 partitions or 3 partitions or 4 partitions, whatever the dependent value is. But in custom partitioning, you are specifying the filter conditions also for the partitions to take place. So in this case, what is your output file will look like? The output will look like something like this. In both the cases, your output will look something like part-0000, part-00001. This is the first reducer output, first partition output. This is the second partition output. If there is 3 number of partitions, you will have 00002. This is how you will be segregating the output of your reducer. So where do you write this partition class? Where do you execute this partition class? Before reducer or after reducer? No, it has to be before the reducer. So before the reducer itself, you're kind of segregating the data, you're kind of separating the data and executing it into 2 different partitions, 2 different reducers. Okay, see, even though you are executing it before the reducer, it does not mean that you are trying to do a filter and you are trying to do an everything. So your counts and filters and everything will happen inside the reducer only. Okay, so these partitioner class and the reducer class run parallelly, you can say. Okay, both run together and the output will be segregated. So while we are inside the reducer class, it's going to call the partitioner class and it's going to execute it. So are we clear with the logic? Partition class, what it's going to do, how the dynamic and custom partitioning is done? That's hash partitioning methodology. So depending on see, if your output is completely integer, is completely a number output, okay, integer output, let's say. Okay, if you select 2 partitions, odd values will get into one partition and even values will get into one partition. So that's how it's going to divide. Generally very basic level partitioning. If you have 10 records, first 3 will be one partition, second 3 will be second partition, and last 4 will be third partition, something like that. So it will just try and make sure that equal number of records are being populated across 2 different partitions. That's it. So what's the value or how it's going to partition it and all, we don't have much of a control in it. Until and unless you specify that, you tell the system that, okay, I want this data in partition 1 and this data in partition 2. So MapReduce is a programming model, a programming framework used to develop solutions that will process large amounts of data in parallel, compute nodes in the cluster. Generally a closed source implementation at Google. So this is just the technical definitions for it. Right. So when to use? When you have processing data in parallel and big data sets in parallel. Okay. Some scenarios. So there seems to be another documentation for this one. Just scroll up. There's no documentation. Fine. Right. So we know what is a mapper. A mapper takes the input in the format of a key and a value pair and transforms it into another key comma value pair. Right. So that's what we have done in the mapper. Right. You take the data, you convert that into a key comma value pair, apply the mapper logic, and the output of it will also be a key comma value pair. And a reducer, which is a sorts mapper output key comma value pairs, combines each unique key and all its values and delivers these key comma value combinations to reducers, right? So this is what the shuffle and sort is doing. And then if you look at the data flow, this is a MapReduce data flow with no reduce task. Okay, so the reducers, we have seen there is a mapper and a reducer, and there are multiple reducers, right? So there are also operations where you don't need a reducer at all. Okay, so some functionalities you pretty much write the logic in the mapper itself, and you don't have to specify anything in the reducer. So reducer logic will be empty. You don't have to run any reducer logic for that matter, right? So in that cases, the set number of reduced tasks to be equals to 0. Earlier we have set it to 2, right? So there you can specify that to be 0, and you can ignore the reduce class implementation. So one very known example of a zero reduced task program, we call this as a map only program. Okay, so when there is no reduced task execution, we call it as a map only task, map only MapReduce program. So when you're ingesting the data from a relational database, okay, for example, there is a source data available on some Oracle database, you are writing a program, or you're using a scoop command to ingest the data into Hadoop file system, HDFS. So source is a relational database and the destination is a HDFS. That is a map only job. So all the ingestion related or the data extraction related jobs will be map only jobs. Okay, so when you're executing the program itself, you can see the number of mappers are 0 or 1, and the number of mappers are 3 to 4, and the reducers are 0. So that is also possible scenario. So in map only jobs, for each and every split, you will have a output file getting created. So depending on the number of input splits available, after running a map output, you will find the in HDFS, you will find the partition file getting created. So for split 0, you have a part file. For split 1, you have a part 1 file. For split 2, you have a part 2 file. Okay, so this is something we have. And for a single reducer, you can see there is split 1, split 0, split 1, split 2. It's running, and there is a shuffle and sort operation which is going to combine and send it to the reducer, and the reducer output will be sent to the part-0000005. Okay, and with multiple reducers, there is part-0 file and part-1 file. So same split operation, split 1, split 2, applied to 3 different mappers. The sort output will be sent to, depending on the different partitions, you'll be sending it to the reduce 1 and reduce 2. Okay, so same thing whatever we discussed. And then Hadoop uses one mapper per data split by default. Hadoop suggests using one reducers per compute core, as it shows best parallel. So there's also one more scenario. See, we know that in the earlier scenario, in the earlier example, there were 4 task trackers, right? There were 4 task trackers, and you could run 4 mappers out of those 4 task trackers, 4 map splits. When you have a single node cluster, for example, you have defined a cluster. When you don't have any cluster at all, you have defined a cluster which is a single node. Your same mission will be master, same mission will be slave, name node, data node. The same mission will act as a job tracker, and same mission will act as a task tracker. So in that case, for example, when the data is divided into 3 input splits, let's assume. Okay, so when the data is divided into 3 input splits, how many map splits you would need? 3 map splits. But how many task trackers you have got? Only 1 task tracker. So in that case, what happens is your single task will get executed first. The map task 0 will get executed first. Then the map task 1 will execute it second, and then the map task 2 will be executed. Okay, so same task tracker will be used to running multiple map tasks. Okay, so that is one functionality we can keep in mind. So why not to use when not to use MapReduce? So when the data is too small, when a simple problem needs to be solved, when calculations depend on the data set. So when is it not suitable to use a MapReduce program? When the data is too small. So we discussed in the earlier slides, the suitable scenarios are when the data is too large. Okay, that's where you will be using MapReduce programming. And to show the best parallelism, Hadoop suggests to use one right? So Hadoop suggests using one reducer per compute as it shows best parallelism. So when you have multiple mappers running and all the mappers shuffle out to one single reducer, right? So that's when your parallel jobs are getting executed. When you have two reducers, there are two tasks again getting executed, right? So two reducers, as in it has to run sequentially. It cannot run parallel, all the two reducers. Then more the number of output files from the Hadoop, more the time taken for processing, less the time taken for processing, no change in the processing. What is it going to be? More the number of output files from Hadoop. Any other answers?
First one.
Why is it less time? In the job tracker, task tracker scenarios, like we had discussed in HDFS, what if a specific task tracker has failed? Okay, so let's assume there is this task tracker 2 has failed due to some hardware issue. What happens? What is the impact going to be? How is it going to be a loss of data? Because it will be an impact on the result, but it will be an impact on a specific task alone, okay, on the task that is submitted to it. So map split 1, 2, 3 and 4 are submitted to task tracker 1, 2, 3 and 4. If the task tracker 2 got failed, then only the task allocated to this task tracker, that is map split 2, only will get impacted. Getting it? So there is also one more scenario. Let me just discuss that first. So for example, I have divided the data across all those task trackers equally, right? We discussed about this scenario. All the task trackers have received 2.5 lakhs of records. They're working on the 2.5 lakhs of data. So I'm running the same program on top of all these 4 task trackers. Then ideally, how much time does they take? Around equal amount of time they should be able to complete, right? So let's say if this task tracker is completing it in 2 minutes, all the other task trackers are also expected to complete it in 2 minutes. That's the general assumption. But what if after the end of 2 minutes, if this particular task is complete, this is complete, this is complete, and this is still running? So what happens in that case? So at regular intervals, your task trackers are also going to send the intermediate task completion status to the job tracker. That means at the end of 30 seconds, I'll say 25% of task is complete. At the end of 30 seconds, I'm going to say some 20% of task is complete, some 20%, some 20% is complete. So this is how the intermediate status report of the task's execution is also going to be shared with the job tracker. So at the end of 1 minute, let's say this is completing 25%, this is completing 25, this is 25, and this is, let's say, 2 to 3%, somewhere around like that. That means there is some issue going on with the task tracker 4, some internal RAM issue or whatever, the availability of resources or whatever, right? So in that case, what my job tracker is going to do is the same task, whichever is allocated on top of this particular task tracker, there is going to be a duplicate task created, and the same the duplicate task is going to get applied on the same data block which this is working on. That means this is working on block 1, input block 2, input block 3, input block 4. So the task tracker 4 is taking more time than expected. There seems to be some issue with this particular task tracker, and my job tracker will allocate another map split on top of the block 4, and it will allocate a new task tracker to run on top of this block 4. That means 2 task trackers are working on the same block of data, and whichever completes first, whichever generates the results first, will be considered as a final copy. I mean, will be considered as a output. The other task will be kept on hold. Getting it? This is a cumulative execution mode, we call it as, but that's just for the theoretical understanding sake. Okay, so by analyzing the intermediate status report, what is my job tracker doing? It is identifying the slowest running task tracker, and it is allocating, by looking at the slowest running task tracker, it is allocating a duplicate task tracker to run on the same block of data. Getting it? So it's just not waiting for this task tracker to complete, but it's actually taking a proactive measure to make sure that this will not impact the final execution flow, right? So there cannot be a scenario where it will just wait for this task tracker to complete. These task trackers have completed the task in 2 minutes, and they are just waiting for this particular task to complete. This has taken 10 minutes, let's assume. So what is going to happen? The entire job execution time is going to get hold, right? So to avoid that, at intermediate stages itself, at the initial stages itself, it's going to identify the slowest running task tracker, and it's going to allocate a duplicate task tracker to run on the same block of data. And whoever send the results first will be considered as a final copy. The other task tracker activity will be terminated. Okay, the other task tracker duplicate activity will be terminated. If the other task itself is sending the same, sending the output quickly, then that itself will be considered as a final copy. Okay, so what if I don't have the availability of this task trackers? I don't have the task trackers available. What is going to happen? After successful completion of all these task trackers, existing task trackers, it will pick any one of the existing task trackers to run on the same block of data. It's going to parallelly run on the same block of data. So this slowest running machine will at least have some backup on using the other machine. Okay, so whichever is going to complete first will send the result as usual. It's all going to be dependent on the resources. Understood? So this is one way of doing it. And now you understood that when there is an issue with the task tracker, so the impact is going to be only on the task that is allocated to this task tracker, and your job tracker will identify this issue, and it's going to run a duplicate task. It's going to run, and it's going to allocate another task tracker to work on this particular job splitter, map splitter, right? So that is the impact it's going to be. The impact is only going to be restricted to this particular task alone. And what if the job tracker itself has got failed? The impact is going to be for all the jobs, for the job that has been submitted now, and for also the other jobs that are going to get executed, right? So this also is a single point of failure. So when the task tracker or when the job tracker is down, then the MapReduce engine is considered to be down. Yes or no? There are no other backup, and the entire MapReduce functionality is being kept on hold until the job tracker is brought back up again. Getting it? So this is one issue. And whenever there is a MapReduce program that is running in, okay, there is a MapReduce program that is getting executed, let's assume. And the first MapReduce program, when I've submitted, it has identified that it would need 4 task trackers to run. Okay, I allocated 4 task trackers. What if there is another program that got submitted at the same time? Getting it? So there is a MapReduce program submitted first. One MapReduce program got submitted. Now the job tracker got the results from the HDFS. It's analyzed the program, and it has decided that it would need 4 task trackers. Out of the available 4 task trackers, I've allocated all the 4 task trackers to the same machine. Let's say I have one more. Let's assume I have 5 task trackers, but I have allocated 4 to one single machine only.
Just a quick info guys, if you want to make a career in big data, then Intellipaat provides an advanced certification in Big Data Analytics by ENICT Council IIT Guwahati. It is taught by IIT professors and industry experts. With more than 10 years of experience, this course is designed to upskill and land your dream job. Now let's continue with the session.
Getting it? I've allocated 4 to one single job only. Then there is a new job that got submitted. What happens? Again, it has analyzed the job. It has got to the HDFS. It has got the information of the blocks. Now it would need some 3 to 4 task trackers to run. But do you have the availability? I don't have the availability. I have only one task tracker available. So that means this job 2 has to wait for job 1 to complete. Only then your task trackers will get freed up, and then your next job can start executing. So that means ideally, in ideal scenarios, at a time there is only one job that is getting executed. Yes or no? Not more than one jobs are allowed to execute, depending on the resources again. But how well is it managing the resources? If there is a scenario where the first job would have taken only 3 resources, and the second job would have only taken 2 resources. Okay, I could have managed the first job to take only 3 resources, and the second job I could have managed with the 2 resources, considering both of the jobs are running parallel. at least both of the jobs have been allocated some resources and they are at least running in parallel. So that scenario would have been possible, but that feature is not available with the existing job tracker functionalities in the MapReduce generation 1. There is no parallel job execution process, or there is no dynamic allocation of resources, proper maintenance of resources to multiple MapReduce jobs that are getting submitted. So whenever the resources are available, it is allocating in bulk. And when the new job comes in, it's just making it to wait for the previous job to complete. What I could have done, if there is a better management, I could have allocated only 3 for the first job and kept 2 on spare. And when there is a new job coming in, I could have allocated these 2 for the other 2 resources for the other second job. So this resource management are the failures of the jobs. There is no recovery, and all these issues have comprised for the version 2 of MapReduce. That's what we call it as a YAN, MapReduce version 2, which is a YAN, yet another resource negotiator. The major concentration of the MapReduce version 2 is on the resource management functionality. Okay, and also whenever a job is being submitted, whenever any MapReduce job is being submitted, what is the first activity that we are doing? We are converting the input data into a key comma value pair. But what if my input is in the format which cannot be converted into a key comma value pair? We know there is a sequence file, we know there is a text format, we know there is a file input format, or different formats we know. But what if the data is in a format which you cannot convert it into a key comma value pair, some graph data or some video data or whatever. If the data is not getting converted, or if you are not able to convert the data into a key comma value pair, if the data is in such a format, then your MapReduce framework will not be able to work on that kind of data sets. So this is also one of the drawbacks. So for your MapReduce version 1 to work, your data has to be converted into a key comma value pair. Your program only understands the data which is converted in the format of a key comma value pair. If the data cannot be converted, then that kind of data sets would not be able to process using the MapReduce engine. So first thing is the resource management. Resource management is not properly done, and the second thing is with the data conversion, key comma value pair conversion. These are all some of the challenges that we have with the version 1, which have got into the version 2, YAN, yet another resource negotiator. So in version 2, we have resolved all these pending issues. Okay. So the major problem was what? Like, we don't have a backup for the job tracker. If the job tracker is failing, all the jobs running on that particular job tracker is going to get failed, right? There is no backup. And the resource management or the what else? The key comma value pair conversion. So all these problems we had, and that is why we are going to the next version of MapReduce engine. Clear, guys? Any questions? That's a master slave architecture. I'll just quickly give you a recap. There's a master slave architecture. A master is going to be your job tracker, whereas the slave machines are the task trackers, right? So whenever you create some MapReduce program and you convert that into a jar file, and you provide the input path. So all these things you'll be submitting as a job to your MapReduce engine. And what your job tracker will do, after you submit a job, your job tracker will receive those details. Like, that's a master, and it is a point of contact for all your MapReduce related executions. So your job tracker will will analyze the job that you have submitted, and it also will check the input path. So to check whether the input path is valid, it has to interact with the HDFS cluster with the name node, to be specific. So job tracker will interact with the name node to identify whether the specified input path is a valid input path. I mean, do you actually have that data in the HDFS? So if the data itself is not available, that's going to be a failure. I mean, that's going to be a written message saying that the input data provided is not valid. So if you have the input data in the HDFS, what is the next step? What are we going to do? What is your name node doing after getting a request from the job tracker? First step is to check whether the input path is valid. Second step is to provide the number of blocks the data is being written into, right? So how many blocks it has been divided, that number of blocks will be shared with the job tracker. So depending on that information, what is the next activity that your job tracker will do? Yes, anyone? What is it going to do? So we got the block level information, how many input blocks the data is stored from the HDFS. So after you receive that information, your job tracker will divide the number of map splits, right? So your map task has been submitted, your map task has been submitted, a reduce task has been submitted as in the form of a program. So your map task has to be duplicated, has to be split into multiple. I mean, it's not being split, but it has been, it has to create so many number of duplicates that are equal to the number of input blocks. So after you create these duplicates of map tasks, multiple copies of this map tasks, each and every task is gonna get allocated to the input block. Okay, so your task tracker will pick a map task, and it will start executing on so and so block of data in HDFS. Agree with this, everyone? So now I have a question. Let's say I have only 3 task trackers available. Okay, so I designed my system. My cluster is not very huge, so I designed my system. I have only 3 task trackers available, and on the input side, on the HDFS side, I have some 100 blocks of data written. Okay, so my input file has been divided into 100 blocks of data. So ideally, how many map tasks it has to execute?
100.
How many map tasks it has to create? 100 it has to create. And for executing this 100 map tasks, how many job trackers do we need? We would need 100 job trackers ideally, but how many do we have? It does not
Only
mean
3.
that we have only 3 job trackers. So what's going to happen now? So how are this 100 map tasks going to get executed on top of this 3 job trackers? So that means the first 3 will get executed, then in second 3 the cumulative execution more, right? So the second 3 set of 3 will be executed, and the third set of 3 will be executed, right? So that's how we will be dividing. You submit this 3 map tasks at a time, and then after completing the execution of these 3, you submit the next 3 slots of it. Okay, so something like that you will try and execute, and this number of map splits is not exactly equal to the input blocks, but it is actually greater than or equals to the input blocks. Okay, so it's going to create some backup copies, which would be at least 1 or 2 more than the actual equal number. Okay, so it's going to be greater than or equals to the number of input blocks. Fine. So now we have executed it. So after this map task has been submitted to the task trackers, they'll start running on the input blocks. They'll execute the data and they'll generate the result. So after you generate the results, what is going to happen? There is a component called as shuffle and sort within the MapReduce framework. What is it going to do? It's going to make sure that all the map tasks have completed the execution, and all the map tasks have provided the result. Right, so it will just kind of be a checkpoint where it will wait for all the map tasks to complete the execution. Okay, so after all the results have been received, it's going to shuffle and sort the output of all the mappers, and it's going to send it to a reducer for accumulation, for aggregation of the map results. So depending on whatever the logic you write inside the mapper and inside the reducer, it's going to break, it's going to execute. Then after that, the final output will be returned to the HDFS location again. We know how the file is being created. So now we've also seen the theoretical flow of how the word count program gets executed. We have seen the split function and default allocation of 1 by as a key and a value, right? So every input or an output for this map and reduce has to be in the format of a key and a value pair. So that's why we kind of convert this into key comma value pair. So in between map and reduce, you also have a component called as combiner. So what is this combiner doing? What is the operation of a combiner? Anyone? Yes, remember? Okay, yeah, so it's something which is doing a reducer operation within the mapper itself. So see, whenever we ask what is a combiner, our answer should be something like it's going to perform a reducer operation. It's going to perform a reducer functionality within the mapper itself, within an individual mapper itself, right? So it's not always going to be identifying a duplicate key and merging both of them, because in word count we have identified, okay, there is welcome and welcome, we merged both of it and we made it two. But in general it's going to be a different functionality. It can be anything, right? So what is that we are ultimately doing is we are using the reducer functionality. So whatever is gonna happen inside the reducer, you just read that method, you just call that method and try and execute that functionality inside a mapper. Yes or no? So instead of running it on all the mapper output, we are running it on a single individual mapper output. So we are not writing any logic for combiner actually. So it's the same functionality as that of a reducer, but the only difference is we're going to execute it inside a mapper, right? So your combiner is something which is a reducer, which is going to run inside an individual mapper. So this is how the definition is going to be. I mean, this is how the explanation has to be. So we are not going to talk anything about the duplication or anything like that. Okay, so combiner is a reducer, itself is a reducer, but it's going to run on an individual mapper output rather than running on all the mapper outputs. Okay, so then we have discussed about the partitioning, how the custom partitioning and dynamic partitioning can be done. So custom partitioning is pretty much you don't write any logic to it, you don't define any logic to it, you just specify the number of reducers so that it will write the data onto different output files depending on some dynamic logic. I mean, it's all within the framework. Again, you don't have any control on how the data is being split and being written into multiple data files. But in custom partitioning, you can specify what is the logic for individual partitioner. Okay, so if this logic is satisfying, you send this output to this particular file, and if this logic is being satisfied, send this output to another file, something like that. You can specify, or you can segregate, or you can aggregate the data and send it to different output files. Right, so that's the partitioner logic we've discussed. Right, and also when it comes to the limitations, we have not handled anything related to the resource management pretty much. So like we have seen when there is already a job that is being submitted, and when there is another job that is getting executed, I mean that is getting submitted to the job tracker. In that case, what happens, it will just wait for the first job to complete rather than try and accumulate the resources, try and properly allocate the resources. It is just waiting for the job tracker. It is just waiting for the previous job to complete. So there is no proper resource allocation done for this, and moreover there is no backup for your job tracker. When there is a job tracker failure, it's kind of the entire system failure is we're going to consider, right? So yeah, so let's see how all those limitations have been overcome on the yarn side. The latest version of MapReduce, the updated version of MapReduce 2, we call it as a yarn, right? So yarn is nothing but a MapReduce 2. In HDFS, similarly, we have seen HDFS 1 version 1 and HDFS version 2, right? So in version 2, we had active and passive name nodes, and nothing else changed actually there. But in MapReduce, there has been a lot of change in terms of the architecture. Okay, so now let's start with the similar diagrams. Okay, so let's put one more. Right. So this is your master and slave architecture again. Let's write some text to it. Yarn. And there is also one more limitation that we had, right? So everything inside a MapReduce application has to be converted into a key comma value pair, regardless of whatever the input we are dealing with, right? So there is no other way of dealing with the data. So regardless of whatever the input is, you kind of convert that into a MapReduce program always, right? So that is also one of the limitation that we had with the MapReduce functionalities. So now, so inside this yarn architecture, like I said, this is going to be a MapReduce a master and a slave architecture, whereas the master is called the resource manager, and the slaves are called as the node managers. Okay, so is it visible, the text? All these are the node managers. So I'll tell you the reason why I'm writing it for all. These are all the node managers 1, 2, 3, 4, and 5. So inside the node manager, we have something called as an application master and container. So let's say, okay, let me put it this way. Application master is one, and there is something called as a container as well, right? So inside every node manager, for that matter, okay, so inside every node manager, we have an application master as well as a container. So now, starting with a job submission, right? So whenever there is a job that is getting submitted, what is going to happen? So in MapReduce, we've been calling them as jobs, right? So every jar program that we submit, every set of program that we submit, we consider this as a job, and we consider the individual components of it, the small modules of it, as the tasks. But in yarn architecture, we call them as an application. So we say there is an application 1 that is getting submitted, application 2 that is getting submitted, 3. So because the reason is, like, if it is a job, then it's going to be a MapReduce job. Okay, so in yarn, what are we dealing with? We are dealing with other ways of execution as well. It's not just a MapReduce way of execution, but it's also running on an other it also deals with the other sets of execution modes or other sets of data sets. Okay, so in MapReduce, we just call it as job. In yarn, as we are dealing with other applications also, other sets of programs also, we call this as a application. So I'll tell you the reason why. See, in MapReduce, what did we discuss? We discussed about the scoop job. We discussed about a Hive job, right? So whenever you write a select star from in Hive, whenever you write a scoop import program, or whenever you write a pick query, so everything within the Hadoop ecosystem is gonna get converted into a MapReduce program. So it actually doesn't matter what query we are writing. Okay, so what query we are writing is only for the user convenience. So in Hive, we have been provided with an SQL kind of a framework wherein we were able to write the simple SQL statements in terms of select star or any joins, group bys, and all. And in Pig, there is another a Latin script, and in Scoop, there is another format of commands. So all this syntaxes might be different, but whenever you submit them, whenever you execute them, it's again going to be a MapReduce program at the backend that is getting executed. Okay, so that's the agenda in the MapReduce framework, in the earlier versions of the MapReduce framework. But now in Yarn, everything is kind of an individual application. So now you have Hive that is again a MapReduce program, but there is a Spark, let's say. Okay, so there is a Spark application that is getting submitted. There is a Spark job that you want to submit, that you want to execute. So if Spark is built on top of Yarn system, then when you submit a Spark application, that's actually an application. It's not gonna convert the data into key comma value pairs. Getting it? It's going to execute as a proper application. It's going to execute as a proper task. Okay. So if it is related to MapReduce, then we can call it as a job. If it is related to something else, then we have to call it as an application. So Yarn is something which is going beyond the MapReduce, I can say, in simple terms. Okay. So earlier it was only restricting to this MapReduce way of execution, but Yarn has taken it to a next level wherein it can execute other applications also. You have a Spark application that it can run, and you have some kind of a Flume application that it can run, or some Flink application it can run, anything, other external systems beyond the Hadoop ecosystem. That's what I mean to say. Okay, so it has got this integrations. You can run a Spark application, you can run some other external applications and all that. So it's not only a MapReduce way of execution, but it can be an other way of executions also. So now, so for our convenience, as we are already aware of the MapReduce functionality, let's say I've submitted a MapReduce job only for this yarn system. Guys, are we confused here? Are we clear with this? Whatever we've discussed in the last 5 minutes, is it confusing? Are you clear with this concept? How is it different from MapReduce, and why it is called as an application rather than calling it as a job? Yes. So you actually need to understand what's the main difference between a MapReduce framework and a yarn framework, right? So yarn is something going beyond the MapReduce functionalities. It's not only a MapReduce, but it can also deal with other kinds of applications also, and it can also deal with MapReduce applications, right? So now, for our convenience, let's say I have submitted a MapReduce program itself for your yarn system. Okay, it can run others also. It can run a Spark application also, but I have submitted in the first place. I'm submitting a MapReduce application, let's say. So what is gonna happen? So here I have the first one as the MapReduce application. So I can call this as an application, or I can call this as a job also, because this is just a MapReduce program. Again, I can simply call it as whatever I wanted to. So this is your MapReduce application 1. So this is let me put it this way, application 1, which is a MapReduce, right? 1. So this has been submitted to your yarn system. So whenever there is an application that has been submitted to a yarn system, who is going to receive it? Again, it's going to come to the resource manager, right? So it's going to come to the resource manager, and it's going to analyze the application. So this is a MapReduce program that I'm submitting. So it will have what? It will have 2 things, a jar and a input file path. Okay, it's not the block info, but it's input file path. Along with the program, you specify which jar to execute on which particular file. The file is in HDFS, right? So the same thing I submitted to the MapReduce framework. What did it do? What did my job tracker do? It started analyzing the jar. It started looking for the HDFS path. It interacted with the name node and received what? It received the number of input blocks from the HDFS name node. But now the same application has been submitted to the resource manager to the yarn system. What is it going to do? So regardless of what application a resource manager receives, regardless of whatever the application it can be, what it is going to do is it is going to allocate this application to any one of the available node managers. So see the difference. So it's not even processing it. It's not even analyzing this particular application. So straightforward, it's just going to forward the application to any one of the available node managers. So now I have 5 node managers available. So it's going to allocate to, let's say, node manager 1. Okay. So again, it can be anything. It need not be a node manager 1, but it can be anything. What it has done, it has forwarded the application to this node manager 1. So every node manager, internal to every node manager, we will have an application master as well as a container. But a container will be started only when an application has been submitted to this node manager. Okay. So all the node managers will have this AM and C containers. Okay. Will have these components, but they will not be triggered. I mean, they will not be, this application, this container will not be started. This application master will not be triggered. They'll all be in a disabled state, let's say. Only when an application is submitted to a node manager, that's when we will start a container and we will trigger the application master. So for example, if this application 1 has been submitted to, let's say, to node manager 2, what is going to happen? The same thing, the same application master and container will get started. So whatever the node manager it can be. So to whichever node manager it gets submitted, that application master and container which is available on top of that node manager will get triggered, will get started. So now what is this container? What do you mean by a container in general terms? No, I mean, forget about the blocks and everything. So container, what is a container going to do? It is going to hold something. A container is generally used to hold something. What is that something here? It's going to be the resources. Okay. So this container in node manager 1 now, in any node manager for that matter, is generally used to store or hold some set of resources. So why is that we are going to need these resources? We need these resources to execute this application 1. Yes or no? So we received this application 1. So now I received this application 1 and I need some resources to execute this application 1. And where do I keep that resources? I'll keep that in the container. See, it's not that you will pull all the resources and put it in this particular node manager. But see, allocating a resource to a node manager is something as simple as like you just providing the IP address of the machine. You just need to use it. That's it. Okay. So in some file, the IP addresses will get tagged. And as long as these IP addresses are tagged to this particular file in the node manager, well, that means they are all working for this node manager. That itself is the allocation of resources, right? So it's not some other thing, right? So now we would need a container to use to hold the resources. So that is the reason why we will be using a container. And application master. So what does this application master mean? So for every application to run, this is an application 1 that is getting executed. So for every application to run, you would need an application master which will take care of all the execution of the application, right? So in simple terms, you can consider this application master as the job tracker in your MapReduce framework. Job tracker in the MapReduce framework. So I'm talking in terms of job tracker now. So now this application master is the job tracker for your application 1, is the sole owner. It's the whole responsible person for this application 1 to execute. Okay, so application master on node manager 1 is the complete responsible to complete this execution of this application 1. Right, so it will now act as a job tracker for application 1. So what it has to do? What is it going to do now? What did my job tracker do when there is an application got submitted? It will interact with the HDFS, right? So there is some HDFS here, let's say, and what is it going to do? It will interact with the HDFS to identify whether this input path is correct. If the input path is correct, what it's going to do, it will retrieve how many input nodes or how many input blocks it has got, right? So depending on that information, I'll point it to. So application master has interacted with the HDFS and it will identify whether the input path is correct. If the input path is correct, it will receive how many input blocks that it has been written into, right? So depending on the number of input blocks, what am I going to do? I'll be dividing those many map splits, because as this application itself is a MapReduce application, okay, I'll have a map task and I'll have a reduce task, right? So I'm taking this as an application, MapReduce application, because we already know the procedure of the MapReduce program, how it's going to execute. Okay, for Spark program, it can be a different procedure again, right? So let's talk about that little later. But now we know that there is a MapReduce application that has been MapReduce job that has been submitted to it. So now it will send it to the application master. Now your application master will interact with the HDFS and will receive how many input blocks that particular file has been written into. Depending on that, it will divide so many map tasks, right? So many map tasks it will divide. After dividing this map tasks, what is the next thing it has to do? Yes, what is the next thing that it has to do? It has to, what is the job tracker doing after dividing the map tasks? It is allocating it to a task tracker, right? Each map task has been allocated to so and so task tracker. Agree? But where are the task trackers here? So now, after analyzing this MapReduce program, after interacting with the HDFS, let's say I have 3 blocks of data on the HDFS side. Okay, so how many input splits, map splits I would need? I would need 3 map splits. So now your application master knows that it would need 3 map splits. It has been divided into 3 particular map splits. So for executing these 3 map splits, I would need 3 resources, 3 task trackers to execute. So whom I have to interact? I'll have to interact with the resource manager now. I'll be interacting with the resource manager, and then I'll be requesting for the resources. So interact with the resource manager, saying that, okay, I would need 3 resources to run this particular application 1. So now when I allocate these 3 resources, when the resource manager agrees to this request and we did allocates these 3 resources, these 3 resources will come under the control of this container. I mean, it's under this particular container, it's under this particular application master. They are being tagged now, right? So now what happens? Okay, whatever. So what is gonna happen is this application master will get the control. This is enough, right, for us, right? So now resource manager has allocated these 3 node managers to your application master available on the node manager 1. So what it has to do now, your application master has received the resources. So it will submit each and every map split to each and every node manager, and it will make sure they execute this map splits. So these node manager 2, 3, and 4 now are acting as a task tracker. Agree? Right? So now the submission has been done, the map split submission has been done, and they'll start executing the map task on top of the HDFS data block. They'll return the result, and the result has been accumulated at the application master, and then followed by it, they'll run a reducer. I mean, application master itself will execute a reducer functionality. After retrieving the output, the application master will send the output to the resource manager. So after the output has been sent to the resource manager, the resources will get untagged. I mean, they get removed from this application master, and this application 1 will get removed from this node manager 1. So now after the application 1 execution has been completed, all the node managers will go back to their routine state. I mean, all the node managers are now 1 and equal. This is not a master anymore. This is not a slave anymore. Okay, getting it? So next time when an application gets submitted, it may get submitted to node manager 2, and this also can act as a slave now. This will act as a master, and this will act as a slave. So any node manager can at any point of time for a different application can act as a master or as a slave. Okay, so that is the functionality of it. Now in the meantime, let's say in the meantime application 1 is running, there is an application 2 that got submitted. This is a Spark application, let's say. Anything it can be. Okay, so this is application 2, Spark application, anything, okay, for that matter. So this got submitted in the meantime while this particular node manager 1 is running. So what it has to do, resource manager will send or will forward the same application to the available node manager, that is this node manager 5. So what happens? It will trigger this, and then application 2 gets triggered to this. So this is all parallelly happening. I mean, while the application 1 itself is running, this particular process is being continued. So you get this application master, you get this container, because the application has been submitted to this node manager 5, right? So this gets submitted. So next, what is the process? It can be a different process now. So Spark has been submitted, the Spark application has been submitted. So everything will have some input file. So it will interact with the HDFS first to check whether the input file is correct, and then there is a different procedure altogether. There is a different functionality altogether. It is running, right? So depending on that, it will identify how many resources your application master available in the node manager 5 will identify how many resources it would need, and it will interact with the resource manager to allocate those resources. So if the resources are available, it will allocate, otherwise it will be on queue or it will be on hold until the other resources get freed up. Getting it? Are we clear, guys, with this procedure?
Yeah.
Okay. So what is that we are achieving from this is we are decentralizing the master functionality, the job tracker or the master functionality from the actual master, from the resource manager to the node managers, right? So that way we were able to execute multiple applications at the same time. So earlier when the job tracker was running on the master, when it was processing the application, it had allocated most of its resources or most of its time to complete the application that it has been submitted with. Until then, until the execution is complete, you're not in a position to submit any other application, because let's say the RAM of this resource job tracker is some 8 GB. So you submitted application 1 in the previous versions, in the previous scenarios. You submitted some application. So entire RAM or entire memory is being allocated for the application 1 only. When you submit the application 2, it does not actually have the resources to process the application 2, because there has to be some kind of an activity happening on the job tracker also, right? So it does not have the available resources. So now what is happening is your master is kept, this particular master is kept readily available always. I mean, it's not taking care of any execution process. It is just making sure it will receive the applications, any number of applications for that matter, right? It has been kept idle, it has been kept open for receiving the applications, and after receiving the applications, it is just identifying the available resources and it is just forwarding it. So you are decentralizing the entire core operation from this master to an actual slave machine. So you're actually making a slave machine as a master for a specific application. Actually, node manager is what? It's a slave machine, and you're making it as a master to execute as a specific application. So that is the advantage we get here. And moreover, the resource management is being done by a particular resource altogether. And only when after identifying the resources, you're receiving a request, your resource manager is analyzing the request, and it is just allocating the resources depending on that. So it does not mean that when you need 10 resources, it will allocate 10 resources, but there is going to be a threshold and it's going to allocate the resources in a proper order or in a proper format. Okay, so those are the limitations that we're gonna solve here. Guys, are we clear? Okay, so this is it with the yarn architecture, guys. So the change is gonna be something like this. So you have a folder named Hadoop env.sh, right? So there you will anyway update the Java home, and in core site XML. So go to the home directory, Hadoop directory, and navigate to the bin path. SBin path. SBin, you have all those. So go to the AI. One second. Hadoop 2.8. Come back. Hadoop 2.8. And here you have a etc folder. Can you open that etc folder? etc Hadoop. See, the first property file that we need to change is a core site XML. Okay. So core site XML will provide you the open that file, right? No, edit it in Notepad. If you open this XML, it will open a XML page directly. So edit it with a Notepad, right? So here you can see the fs.default fs property is been set, right? So HDFS colon 127, whatever the local host path, and 9000 is the default path for your HDFS, right? So this property has been set, and everyone might have this property value already available. This is the default port number. So what happens is, after you log into the after you start the services, you may navigate to the localhost 9000 and you will be able to see the HDFS UI, web UI. Okay, so we will see that little later. And then now open the HDFS site.xml, close this. This is the only change that we need to do in the core site. So there are other properties also, guys, but those are optional. So now you can open the HDFS site.xml. HDFS site.xml has what? So there is a dfs.replication. So this is a property that says that the replication factor is been set to 1. So here you need to make the changes 1, 2, 3, and it will accordingly update that in the data nodes. Okay, so dfs.data.directory, data node data.directory, and name node data node data.directory. So there are 2 files available here. So these files are, we have to change the path. So here you have to change the path to whatever the directory you are considering. You are considering it to be a, why is it 2.7 again here? Did we make these changes? Because it's a Hadoop 2.8 file, right? If it is coming by default, it must have had 2.8 file only. Others also having the same file with the 2.7. So what is the file name that we are reading? HDFS site.xml, right?
Yeah.
Let me check in mine. HDFS site.xml has what? This is by default giving you the 2.7 path. Okay, so here what we have to update is we have to give some C drive location or any D drive location which you wanted to consider as a data node or the name node. So whatever the data, so whatever the path you specify here will be considered as your data node location. Okay, so whatever the files you store will get loaded into that particular location. So this is for your name node, and the down below one is your data node. So name node directory is that, and the data node directory is this. So you specify c dot whatever the file names you wanted to, and that will convert it into a data node path as well as a name node path. By default, name node path and the data node path. So this is one HDFS site.xml. And can you go to the MapRed site.xml? There is one more MapRed site.xml. That no, .xml file, .xml file. The next. Yeah, here. This is the XML file. So edit it. So here you have only one property mostly. Yeah. So MapReduce framework name is Yarn. So this is anyway there. This property has already been set here. So now come back to the Yarn set XML once again. Last one. And do we have a property defined? Aux services is not required. Aux services manager is not required, but you can specify. I'll give you the property name. So I'm putting that in the chat, so you can update these two. So you can just append these two values to the existing properties. These two tags, these two property tags. This is in the yarn set XML. No. Add these two. These two should be there. In addition to those, you have to add the other properties also. So I gave you the yarn dot what is it? Yarn dot resource manager dot host name. So when you start the services, you can navigate to the 127.0.1, and that will take you to the resource manager UI, web UI. Right, that should be fine. Yeah, that should be fine. And then save it and come back to the HDFS site XML file. We didn't update, right? So that's okay. Can you give some path in the HDFS HDFS site.xml? Because that's the only file we didn't specify. Here itself. No. Come back. In the same file, HDFS site.xml. Edit that file once. Edit that file. What is it listed? File colon Hortonworks. So here, after that colon, give some C drive path or D drive path, whichever path you wanted to specify. That's okay. So D drive is editable, right? So better we give this. Create one directory here. Otherwise, no. On the D drive itself, create one directory. Create one directory saying that data or whatever data. Yeah, use this path. Use this file path to give in the HDFS site. Notepad. It's already opened, I guess. Yeah. Data node directory. So, but you have to specify this in the format of file colon. Remove that file as well. Let's see, because this Windows format, we have to see what format it is going to take. Yep, save it. Let me see if there is any other format specified. Let's save it. That's okay. Let's do one thing. Otherwise, let's create one directory inside the Hadoop itself, inside the Hadoop folder. That's better, huh? Because it's going to identify directly. Can you create one directory in the Hadoop folder? Inside the Hadoop 2.8 folder, right? Yeah, can you create one directory named data node and the name node? Yeah, name node separate, data node separate. Which one? Yeah, you can replace it. But what is the path that we need to give? We have to give a right path, right side path. I mean, left path is not identified actually. See, if you see the slash symbol, this is not a
Forward.
proper format of giving it. So do one thing, inside the C, remove that C colon and just give Hadoop 2.8 and everything in the backward slashes. Yeah, give one slash in the beginning, a backward slash. This is a backward, is it? Then the other one forward. I keep confusing with the, and give the forward slash then. Yes, and give the other slash also here. The same thing for others also. Remove and then replace it. Yeah. So now let's save this and then come back to the terminal. Save this, save it and close. Close it, close it. Don't open it. Close it. As of when you save it, then you just have to close all those windows. No, close those or notepad pages. So now Control Z will take you to the home page. Yeah. So HDFS space name node space hyphen format. Okay. So let's wait. Let's just see what is that written. Anything related to the data node block or anything, there is an error. Just scroll through, scroll up. Do you see any error here? Nothing. Yeah, scroll down. Now navigate to the Hadoop path, CD Hadoop 2.8. Wherever you are, Hadoop is available. Just do CD / and then come back to the home page and then do a CD Hadoop.
Here
Just
only.
navigate, yeah, in the command line. Just navigate to the Hadoop path. That's it. It's available on the C drive. Yeah. Control Z. Yeah. Do a CD sbin. Yeah, sbin. Enter. Now start hyphen all. Just put a start hyphen all. Just give a tab. That's okay. Just give a tab. It will give you the suggestions. It's not giving. Start hyphen all. Hyphen all. No spaces. This is all single command. So that's the reason I was asking. If you give a tab, it will give you the suggestions. .sh. Enter. Let's wait. This will open a terminal. So if the services are started properly, then okay. So couldn't find or load the main class org.apache.tools get configuration starting name node. Connect to localhost port, connection refused. So this port 22, can you check with them if this particular port is open or not on your machines? It's not required because this is all your local setup, right? That's not required. Let me share my screen for a minute. See, you're seeing my screen, right? I have these folders. Okay, these are files I have. So what changes I made in cd etc and do. So you have a core site, right? So core site.xml. What I did is I gave the temp directory. Any I mean that's fine. I can give anything. And this default name you already have with 99000 and the local host path and whatever the HDFS. So this is same. And in the HDFS site.xml, what I did was I gave the path of my data node and I gave the path for my name node. So what is a path? Some home folder in DFS data node. I created a folder named name node, and DFS data folder. I created a folder named data node. So this is all on my home path. So whatever the path you give here should be an explicit path for your C drive or D drive, wherever you create these folders. Okay. So in fact, you don't have to create these folders. The system itself will create it. So you just have to give this path which you wanted to consider as a name node or the data node, right? And the other property is the default dfs.replication, the same thing. And then I have MapReduce site.xml, which says the same thing, MapReduce framework name as the yarn. And then I have, what is the other one? Yarn site.xml. So here I have what? This yarn resource manager host name, ACL enabled, and node manager whitelist or whatever. This is all fine. Okay. So this is all the default settings. So now what I did was under Hadoop folder, under sbin, you just have a start hyphen all .sh. So this will do what? This will start all the services. Okay. So this is going to start the name node, data node, as well as the resource manager, as we have selected yarn as a MapReduce framework. So starting name node. So this particular local host, I mean, everything is a local host for us, even for you and for me, right? So it's all local host. So it's not even looking for this path. It's not even checking whether these paths are correct or whatever it is. So it's here, it will just try to connect to whatever the ports you specify. So this 127.0.0.1, so this 9000, or we have other resource manager, node manager ports, right? So it just starts connecting to all those. So when I do JPS, you can see all the services that are running. And also when I do let me see which ports I have created. I think one is, let me check the files, 98709864, right? So let me share the Chrome browser, right? So this is a page I'm able to load. So localhost 9870 is my what? Is my a name node, the entire HDFS web UI, and this 9864 is your data node UI, and the yarn, all the applications that are submitted are this is the resource manager cluster is your 8088. So these ports I have not set up anywhere. I mean, this comes default with whatever the configurations you make in the shell script. Okay, so you have not made any changes to this. So it tries connecting to these ports. So these ports have to be active. These ports have to be enabled on your machines. So whatever the local host port that is trying to connect .22, so that is not active on your machines, right? So when you start all the services, you should be able to see something like this. This is your name node information, this is your data node information, and this is your resource manager information. So all the applications that are submitted, whatever the existing memory you have, everything will be listed here. Getting it? So this is how we need to see. We need to set up.
Actually, it is asking for
just select more apps. Just open the CMD. Just more apps. So do a select start all.sh once. Up arrow and submit it once. Enter. You uncomment this. Always use this app to open sh files. Just click OK now. This is not done. Then select drop down. Where is the CLI? Look for another app in the PC. Navigate to the CMD command prompt. CMD start all.cmd.
yeah, sure.
So just go to the name node. What is that you're seeing? So this has some issues. Scroll up. You said you are able to open all these things, right? Scroll up, scroll up. There is an error message there. Right. So file, this is not a valid structure. So there you have specified HDFS site XML files, right? The location that you have specified is not in a proper format. So file 3 colons followed by C, Hadoop, and all that you are supposed to give. Okay, so that property you can change it and then rerun the name node. Okay, see if you have started the other services properly, the resource manager or the secondary node manager or whatever. So this is still having a problem. Close it, close this. Yeah, so check the other one. Everything has the same problem. File C Hadoop. So if you resolve that issue, then the problem is gonna get resolved. So you can see, right, the proper file name is not specified. So in HDFS site.xml, the data directory you have given like this. This is not a proper format. Okay. What is it? Core caused by core site XML. line number 25, column number 17, XML document. So there must have been some syntax error for you. So can you open course at XML once quickly? So what is the error? Default FS, HDFS, localhost 9000. First line, just remove our configuration and then save it and then start again. I don't think there is anything here. Everywhere you have this two configurations. Scroll down.
There is.
Yeah. So it has to be an opening tag. Remove that slash there.
This one?
Yeah, remove that slash. Yeah, save. MapRed and yarn.
Yeah.
Remove all, close all these windows. No. This is fine. This is fine. The last one is fine. Okay. Open a CMD
No,
window.
whatever he edited last, that has to be closed tag only.
No.
Before that, there will be open tag.
No, I did check. Can you open that yarn site XML once again? Just do start hyphen and then tab. It will come. It will pick you all. Yeah, just submit it. Just check the name node. Allow access. It's going to ask you for the admin again, I guess.
Admin credentials it's asking.
Cancel it and go to the name node window. Why is it asking for Java related thing? See, Hadoop data name node is in incorrect state. So storage directory does not exist or is not accessible. So whatever the data directory that you have specified, this name node folder is not created. You check once. C drive. Yeah, data here. Data name node. Yeah, and can you go to the what is it, HDFS at XML once? What is the format that you gave? etc Hadoop HDFS at XML. In which format did we give the path? Scroll down. Hadoop 2.8 data name node. Hadoop 2.8 data name node. So this is how we gave, is it? Is this a proper format? Fine, let's see. Just submit it once, rerun. So resource manager has been started, I guess, right? Remove the previous back, the one on the back. Okay, fine. Go to name node. What is the error here? Unable to load Hadoop native platform. So this native library platform has been not loaded. So go to Hadoop name node first. What is the problem? Failed to start name node. Scroll up. This is an error. So native IO windows.access. So did you update this org.apache.hadoop.io.native library in the 1 second? Let me give you that parameter. There is one more parameter that you need to update.
Just a quick info guys, if you want to make a career in big data, then Intellipaat provides an advanced certification in Big Data Analytics by ENICT Council IIT Guwahati. It is taught by IIT professors and industry experts. With more than 10 years of experience, this course is designed to upskill and land your dream job. Now let's continue with the session.
Anyone else is facing this issue? So can we do net space start and just see what are the services that are being used for by port 22? So can you do Yashwant, can you go to the home page? Yeah, HDFS space name node space hyphen format. Just try. Same window, whatever window you are in. Yeah, just submit it here. HDFS space. Yeah, so with port 22, just check what are the other applications that are running. HDFS space name node space hyphen format. So there is nothing that I have updated in the core site apart from the temp directory and the default name fs.default name, which is the 127, the local host 1090000. And similarly, I'm just showing you what are the parameters that I've updated. So data directory, you update some location in your local file system. Data dir and the DFS data dir, one is for the name node and the other is for the data node, and the DFS replication, this is a mandatory parameter for you to update. And similarly, so MapReduce site XML does not have anything else. MapReduce framework name is yarn. This is the only parameter that you need to specify. And similarly with the yarn site XML as well. Okay. So where is it? This one. So resource manager host name and the ACL enabled is 0. So these all properties I gave you in the chat yesterday. So after you update all these properties, I'm navigating to sbin and then do a start all dot sh. So this will start all the services, and also in the other window I'm going to show you the files that are getting created, cd hadoop cd and what is that, what is the path that I gave in name node and data node, home DFS data name node, right? So there should be a folder named DFS data under which you have data node. So after you start the name node and data node, when you load some data into the name node also, it's going to get created. A name node folder also will get created. Okay. So now that I've started all the processes, so it's all running. I mean, all the processes are already running. I have not stopped it. So you can just do JPS and this will list you all the services which it is holding. So name node, secondary name node, data node, node manager, resource manager, task manager, and then the name node. Okay, so all these services are currently running. So now what are we supposed to do? Yes, same thing. I mean, start all.sh is same, and maybe the JPS might not work if you have not set the proper Java home. So JPS is a list of Java applications or Java processes that are running. It's going to list you. Okay. So JPS, I don't know whether it is going to support in Windows, but it shouldn't have any problem. Right? So now after we do all this, there is a Hadoop cluster that has been initiated or that has been started. Okay. So on the same machine, you have both Hadoop and as well as a local. So the local storage is everything else. I mean, wherever you have the C drive, D drive, and whatever the storages you have will be your local storage. And the Hadoop HDFS storage is something which is only the location of this particular data block. This is where here, right? So this is the data directory I have specified, right? So only this particular portion is your HDFS location, and rest all your local file system. So in case if you configure a cluster, right? If you're having a multi-node cluster, then also you are supposed to update the worker configurations or the data node configurations, the IP address of different machines in a data node folder. You have to create a file name called as a data node or workers or slaves, under which you have to give all the IP addresses. I can show you that as well. CD etc, I'm sorry, ls etc Hadoop. Do we have any worker files in this? So cat etc Hadoop workers. So under cat under etc Hadoop, there is a file name called as workers here, right? So what does this mean? All the IP address whichever you have, which you want to consider them as your slave nodes, have to be provided in this particular workers file. Okay, so this will be read by your start command or the name node.start dfs.sh command, and it will read all, it will identify all the IP addresses which are available in this workers file. Okay, so when you're, I mean, not now, but when you're dealing with multiple nodes together, when you want to configure everything together, when you want to configure a distributed cluster with multiple nodes, then you have to specify all the IP addresses in this particular location. Okay, so from where you will pick your Hadoop will pick those machines. So in that case, your data directory will be spread across these multiple worker machines. Okay, so it's going to be something like data 1 directory, data 2 directory, data 3 directory. You can also specify multiple data node directories there. Okay, so that's how we will be doing. And after you have successfully started all the services, so let's get started with the Hadoop HDFS command. So HDFS is the command, or you can also give Hadoop and then enter. So it's going to help you with a list of commands it's going to take. So Hadoop is a command that I gave. Under Hadoop, you have different options, and there is a subcommand, there is a different subcommand options. Okay, or you can give Hadoop options, class name option. So what are the different options which it can take? So options are the config directory, the debug, the help, host names, host file name, log level, and the workers. So Hadoop configuration directory, and it's going to turn on the shell script debug mode. It's going to help you with the, it's going to give you a help, a syntactical help for all the commands that you execute. And similarly, you have different admin commands. You have archive, you have class path, and these are all commands we will not be using most probably. We being the developers, you'll not be able to use all this. And there is something called as FS, right? So what is this FS? Run a generic file system user client. So if you want to interact with the file system, the Hadoop file system, you're going to use this FS command. And if you want to add a jar file, you will be using a jar command. And similarly, the version we already know. And what else we will be using? Class path we can use, the check native we can use, right? So, but generally the FS is something which we'll be using to interact with your Hadoop file system. So what do we do? Hadoop FS, right? So what all it can take? So after Hadoop FS, what all the commands it can take? There are different, these different options you have. Getting it? So all these options can be used to make some changes, to edit, or to interact with your Hadoop file system. So there is an append to file. What does this mean? That means you are trying to append some data to an existing file. There is cat, there is checksum, chgroup, chmod. These are all permission related things. And there is copy from local, copy to local. This is all file transfer related things. There is a count option, there is a cp. We will execute all these commands, maybe most of them, but these are all the options that you have here, right? So how many of you are familiar with these commands here? The touch, or setrep, or rm, rmdir, put, mv, mkdir, ls, all this. These are all the generic Linux commands, Linux or Unix commands. So the only parameter that we are appending to it is the Hadoop FS. Okay, so if we use Hadoop FS along with these commands, then it's gonna interact with the Hadoop file system and make all those changes. So generally, in your normal system also, in this normal system also, if I come out of this directory, so what I'll do ls. That means it's gonna list you all the commands, all the files, right? So similarly, I'll do mkdir, right? So it's actually creating a folder. It's actually creating a directory for you. So similarly, similar to the commands that you have here, what I'm just trying to do, I'm just trying to append Hadoop FS in the beginning. Okay, so the activities that they are gonna do is the same. So cat is used to list the contents of the file. So we have tried and executed all the cat commands, right? All this while cat HDFS site.xml, cat MapReduce site.xml. So we've already executed all those things. So cat is used to let the content, get the content. So chmod, chown, chgroup, you specify to provide the permissions. So similarly, all this, every one of this particular thing is a Linux command only. But what we are trying to do, we are trying to work them using the Hadoop FS, which is going to interact with the Hadoop file system and make all these changes to it. Okay, so now I'll do Hadoop FS -ls. Okay, so ls is what? A normal the local file system listing of files, like something you have in dir. In Windows you have this dir command, right? So similar to that, you have this ls. So list all the files. And what I've done, Hadoop FS ls is doing what? It's giving you the files that is available on the HDFS. So what is it saying? There is no such file or directory available. So what I'll do, I'll give some beginning path. So there is one file, one directory that is available. If it is not visible for you, yeah. So Hadoop FS -ls and a slash is giving you the path of the data of which is available in the Hadoop file system. Okay, so there is one folder available in the Hadoop file system, so that has been listed. So what do you do then? Hadoop FS hyphen L hyphen mkdir. Let's do. I'm trying to create one file, a folder, hello, right? So enter. So I'm starting it with a slash because it's trying to identify, or it's trying to interact with this particular location by default if I don't give a slash. And Hadoop FS does not have permissions to interact with this folder directly. Okay, so if you give a slash, then it's going to start with user Shravan and then slash and then hello. Okay, if you look at the explicit path of this, it's going to take this particular location. So now do a ls again and then see all the files that we have created. So I created hello and I created a test. If you want to see what are the contents available in hello folder also, so do a Hadoop FS -ls and then hello. Getting it, guys? Getting the difference? Yes, right. So this is all very generic, very basic Unix commands, ls, mkdir, or cat, or whatever. Okay. So if you want to delete some file now, if you want to delete some this test, let's say, what do you do? Hadoop FS, if it is not. Okay. So there is a command called rm, and I'm giving rm, and then I'll do test, enter. So test, no such file or directory available. So if I give /test, so test is a directory. So what does that mean? Rm is a command, is a remove command, which is generally used to remove the files. Okay, only the text, only the files and not the directories. So if you want to delete a directory, I'll have to append rm-r, okay, which is a recursive mode of delete. So recursive mode on the test folder. So inside the test folder, whatever the files and directories or whatever the internal files you have, all will get deleted one after the other. So now if you do an ls on top of this HDFS, then it's going to show you only one file. The test file got deleted. Okay. So now if you want to write some file, or whatever, what you say, if you want to create some file in Hadoop file system, so there is something called as, just right, just see. So there is this append to file. There is some data which you wanted to append. This is different. And cat, we know what it is going to do. Chmod, ch group, and all that we will see. So copy from local, copy to local, we will do it. So cp is to copy within the file system. So just scroll down, scroll down, scroll down. Yes, touch. So what is this touch z and touch? So these are the commands which are used to create an empty file for you. Okay, so let's say Hadoop fs hyphen touch and on hello sample.txt. So what is it doing? Hadoop fs hyphen ls hello, and there is a sample.txt file got created. So touch commands are used to create an empty file inside your Hadoop file system. Okay, inside your Hadoop file system or wherever it is, like it's touch is generally used to create an empty file, a 0 MB file, and using Hadoop FS as a prefix, we are creating this file on the Hadoop file system. So similarly to Hadoop FS, you can also write HDFS DFS also. So both do the same thing. So if you do HDFS, it's saying there is a subcommand and subcommand options available. So the same level of subcommands are available for this. Okay, but the difference is there is DFS instead of FS. You have the DFS. So when you are using HDFS, give DFS hyphen ls and then give a tab. What is it saying? Sorry, DFS, right? So same thing it is doing. So HDFS DFS or Hadoop FS. So both can be used. Either one of it is an older version, is kind of a deprecated version, but I don't know which one is a deprecated command. So Hadoop FS I think is deprecated. HDFS DFS is something which is being in use recently. Okay. So that pretty much is like interacting with your both used for interacting with your Hadoop file system. Okay, so now regardless of where you have the data, whatever the location you have the data, it actually doesn't matter for us, right? So as long as we are, so there is a file that got created. If you see, there are some files that are getting created, right? So earlier there is no file. What is that? B, is it? So as of now, whenever you make those changes to the HDFS location, some data gets appended to the data node directory, right? So I'm trying to create a file in this. I'm trying to create a file. I'm trying to create a directory. I'm trying to create an empty file. All that changes were being tagged in your data node directory. Okay, because this is what is being used as my data node, right? So you may not be able to see the proper format of the data. It might be in a compressed format, but generally your files all will get stored into that particular location only, always. Okay, so is it simple? These are all very very basic commands. Yes, agree. No, see, we will have to interact with the HDFS, try to move some data, load some data into it, make some changes to the data, retrieve the data from HDFS to the local. So these are all commands we have. I mean, apart from that, nothing else we have. I mean, we have not discussed about it, but so what do we do now is now we have seen only creation of data files and data directories, right? So now we have some data available in some location. You'll be pushing that into HDFS, okay, using a CP command or copy from local or put command or get command or whatever, right? So interact with HDFS, load some data into it, and retrieve some data back from it. That is it we have with the HDFS. Okay, so now let's also do that. So in my local file system, what I'm doing is I'm trying to create an empty file, create a dummy file. So under home, under mkdir data, I'm just preparing the data in my local file system. So hello, so I'm writing some data into it. This is, so this data which is available in the data folder, I'm trying to, I'll try and move this particular file to your Hadoop file system in the other terminal. So there are multiple ways of doing it. If you look at Hadoop FS enter, so there is a put command and there is a copy from local command. So there are two commands which can load the data from your local file system or from some location of your network drives to your HDFS locations. Okay, so copy from local is one command and put is another command. So put command can actually get the data from any network location. Okay, so it need not be available in your local file system alone. Okay, so a copy from local is something which is available in the local file system of your machine. So whichever machine you are interacting with in the local file system, whatever the data you have, if you want to copy the data into HDFS, you can use copy from local, or put also will do the same thing. Put is the data from used to move the data, copy the data from the local file system or to from any of the network location drive to your HDFS. Okay, and there is also something called as move from local, which is a delete from the local file system and load the data into HDFS. Move from local or move to local. Move from local is local to HDFS, and move to local is from HDFS to local. Okay, so copy from local, move from local, and put. All these three commands will do the same activity, almost the same activity, which is loading the data from the local file system to the Hadoop file system. So how do we do it? Hadoop fs hyphen copy from local. What is a path? This is, I mean, the data you can just give it from data sample.txt to, just give an empty folder. Okay, I'm not giving any data sample.txt. It's not identifying. Okay, enter. So now check in Hadoop fs hyphen ls. So there is a sample.txt got loaded, right? So similarly, you can also do it using the put command also, or copy from move from local command also. So similarly, how do we get the data back? So all these commands will point to the same thing. Copy from local is one, and there is put is another, and then move from local. So move from local, what is it gonna do? From home data txt to user, whatever it is, user, no, not user. This is HDFS location. So HDFS location, I'm trying to create one new folder. Inside the new folder, I'm trying to dump the data. Let's see. So NF is not available, is no such file or directory. So I'm gonna do that in hello, but hello already has a file named sample.txt, right? So in that case, what they will do, Hadoop FS -rm hello sample.txt. Okay. So now do a move from local to your hello folder. It will load the data into sample.txt, and it will also delete the data from your the local file system and generate the normal functionality like we do. Okay. So similarly, from HDFS to the local, you have again three commands. Hadoop FS hyphen copy to local is one, move to local is one, in and get is another one. Three commands. So put, copy to local, copy from local, move from local, get, copy to local, move to local. So you can use any one command to retrieve the data from HDFS to your hello local file system. So get hello sample.txt to home data. So this will get you the data from the HDFS location. Okay, so simple data transfer commands, either from using these are all file level data transfers, guys. So not very much we are going to use these commands in day-to-day activities. Very rarely we will be using it. And within the HDFS, within this HDFS, if you want to move the data from one directory to the other directory, you have a CP command. Okay, so Hadoop FS -cp source will be HDFS and destination also will be HDFS. Within the HDFS, you're trying to migrate the data. And so these are all very generic, right? And where exactly the data actually comes from. See, if you look at the data commands that we are actually executing, these are all very, very generic or very basic commands, right? So you would not expect to load the data something like this. The HDFS would not actually interact with is not meant for this copy from local or copy to local or not something like that. So in general, when you do a copy from local, put or move from local, generally you are trying to interact with the HDFS cluster. That means you are interacting with the name node to write this sample.txt into your HDFS cluster, right? So all that operations will happen. It will check the name node, it will check the name node, it will check the metadata for available data nodes, and it will allocate some set of data nodes to it, and then you write the data to the data blocks. So these are all operations is going to happen, but in general, guys, the data mostly comes from the external systems. Okay, so it can be a relational database, or it can be some online stream, or it can be some other network drives. Okay, so which can be inserted or ingested using different tools. It's not using a command line copy or a put command, but generally via external tools you'll be loading the data, most of the data. So if it is from a relational database, you're going to do it using a scoop command. Okay, so you'll run a scoop command, give the source table and the destination HDFS location, right? So that's how your major data operations are going to happen, but this is all very generic. You just need to understand what commands do we have and how do we use them. And similarly, you also have this permission related commands. How do we change the permission modes, read, write, execute modes, chmod and chgroup? How do we allocate the permissions to a group of data, group of people? That is chgroup and chmod and chown. You can update the permissions of the files in the HDFS. Okay. See, again, for Hive installation, for Hive setup, you may have to download, because you've already done a Hadoop setup, right? 2.8 version of Hadoop setup. So you may have to find a compatible version of Hadoop Hive for your Hadoop 2.5, 2.8, right? So all those issues will come. So if you want to use that file, I can send you the VM file. I can send you the drive link. You can download the file and you can start working on it. Okay, so all that you need is, it will have a around 5.3 or 6 GB file. You just have to download it, and in addition to that, you have to install Oracle VirtualBox. Okay, fine. So let's get started. So what do you know about Hive? What is it used for? Yes, thoughts? What is Hive? At least a very high level understanding. What do you know? So it provides users with a SQL like an interface. Okay, So all this while, when we talk about MapReduce, it's all Java programming. See, we didn't discuss about MapReduce hands-on because that's out of syllabus and out of market as well. Okay, so there is no company which is still using a MapReduce programming for its daily processing needs. Okay, so that's something completely out of market, and very few, hardly 1 in 100 or 1 in 1,000 are still using it, because if their existing systems are still built on top of it, then there is no other choice, they have to use it. But other than that, there is this MapReduce programming, at least hands-on, is completely out of market. Okay, so that's the reason we don't include MapReduce programming in any of our sessions, hands-on in any of our sessions, because it's just not required at this moment. You just need to understand the flow or architecture, that should be sufficient. Okay, now, so we've seen, we at least know what MapReduce programming is like. It's written in Java. You have some classes, methods defined, and Spark, you must be knowing this is something related to Scala and Python or whatever, right? So when you before the existence of Spark, we were always discussing about MapReduce, Pig, and what Scoop, different tools. So all these data processing tools that we're talking about have their own programming framework, right? So they are kind of considering the data to be generic. So regardless of whatever the format the data is available in, if it is in a CSV, JSON, or Parquet, Avro, doesn't matter. It just takes the data in a some and so input, and it will just process it. But if the data is actually in a structured format, right? So most of the companies, what they generally do is, in the existing environments, they definitely have the data in a database, right? So they have the data in their databases, Oracle, Postgres, most frequently used, and some other Teradata or whatever, right? So when they want to migrate everything into a Hadoop ecosystem, into the Hadoop platform, they should be able to migrate the data that is already available in their databases, so relational databases, I'm saying, right? So there is no other tool, if you can reiterate this again, there is no other tool, or there is no other way which is better compared to an SQL way of handling a structured data, right? So SQL way of handling, or SQL storage, or relational database handling of a structured data is the best way to work with it, right? So even in Hadoop, when we get the data into Hadoop ecosystem, so whatever the structured data we received into the Hadoop ecosystem, so using it with MapReduce program or Pig doesn't give you proper results, doesn't give you so much control on the data, because the data is properly structured. You can create the databases, you can create the tables, you can store, you can do a lot with it. So when you have such a framework, when you have such a facility, why to go with other tools and technologies, right? So to avoid all that, they've developed an SQL kind of a framework for the data which is coming in from an external databases. Okay, so this is only meant for it. So if the data is coming in from the external databases, from the relational databases, most precisely, if the data is in a structured format, to be very precise, if the data is in a proper structured format, and if the data is coming from a relational databases, that's when we will be using Hive as a processing tool or a storage mechanism. Okay, so internal to it, it's again a MapReduce framework, or it's a Yarn framework, whatever the processing mechanism Hadoop is using, it's going to execute the same way. But what we are gonna write is a Hive query, a simple SQL query. So internally, it's going to get converted into a MapReduce program, and it's going to execute it. But that's not our concern. Okay, so we don't have to worry about what it is executing. But as long as we are writing a simple SQL query, we are fine with it. So this is kind of SQL like a framework, like I said, which is used to process a simple structured data tools, data formats. Okay, so what are its sources? Generally, most of the times, the sources would be the relational databases. So how do we get the data from a relational database? This also we discussed. We just had a quick chat about it. If the data is available in a relational database, how do we get it into a Hadoop framework? Using what tool? Okay, so we have something called as Scoop. Okay, so Scoop is a tool which is used to interact with a relational database and migrate all the data that you have in a relational database to your Hadoop file system. Okay, so after you migrate the data into Hadoop file system, it's gonna be in a proper simple plain text format. Okay, so plain text format or a CSV format, whatever, a tab separated format. So depending on the use case, you'll be creating whatever the data formats, but it's going to be in a structured format only. So on top of that data, you'll be creating the tables. Okay, so similar to whatever schema you have in a relational database, you create the same schema on Hive, and you load the data whatever you have in the HDFS locations. Okay, so that's how you'll be migrating the data from a relational database to your Hadoop ecosystem and create Hive tables on top of it. Okay, so that is the main purpose of it, and we'll see how exactly it is being done and what are the different features allocated to it. So now generally it's a data warehouse infrastructure that is built on top of Hadoop. It's a SQL-like language, and Hive uses MapReduce and HDFS for processing and storage retrieval of data. So internally, like I was saying, it's always going to be MapReduce, and HDFS is going to be the storage. And what you actually write to interact is a SQL-like program, that is HQL, Hive query language. Okay, so similar to SQL, you have something called as an HQL. Then advantages: it can be used as an ETL mechanisms, extract, transform, and load. Provide capability of querying analysis and can handle large data sets. And we have this filters, joins, group by on top of this MapReduce. So all these things we know. It is an ETL tool. It's used for querying, and it's meant for dealing with large data sets. Obviously, it's on MapReduce and Hadoop. And filters, joins, and group by on top of this MapReduce. So if you have to perform a simple filter condition using a MapReduce program, it's a complicated process. It's not a complicated process for a Java developer, but there is some amount of code that needs to be written, right? But that's simply executable using a simple Hive query. And where not to use Hive: if the data does not cross GBs, if the data is less than GB, if you don't find schema or bringing in schema, it's difficult or not possible on the data at hand. If we need response in seconds of a low latency applications, if the data RDBMS can solve, don't invest time in Hive. So this is the use case. So if there is no problem with the relational database, then there is no point in migrating the data to Hive and rewriting the same amount of queries. First thing, right? And this is a low latency application. If you want a query to generate the results in some seconds of time, it's not a suitable solution. So this is mainly meant for large amounts of data sets and dealing with large data sets or large amounts of joins or partitions. If the data does not cross GBs, if the data is very small, then what is the need for you to load into Hive, or what is the need for you to use Hadoop framework at all in this particular case, right? So it's only meant for large data sets, large data processing use cases. And if there is no problem, or if you are comfortable using the RDBMS framework for a specific use case, then don't invest time in Hive. This is what it's going to be, right? So it's just a replica of an environment on a Hadoop framework, but there is nothing Hive can provide which RDBMS cannot, at least. Okay. So if you are fine with the relational databases, if you don't have any issues managing the data or handling such large amounts of data sets, then there is no point in bringing the data to Hive. Okay. So in most of the cases, guys, in most of the real-time scenarios, the problems would be something like if the data upstream or downstream is somewhere interacted to Hadoop. Let's say the data to a relational database is coming from some so and so source, or the data from a relational database is going to a so and so source, so and so destination, right? So in that cases, if the upstream or downstream is somehow related to a Hadoop framework or a Hadoop ecosystem tool, then there might come a possibility where you have to migrate these relational databases. Because, for example, if the data is coming from a HDFS location, we don't know where the data is coming from, but the data is being loaded into HDFS. Now your RDBMS has to load the data from a HDFS location. Getting it? So the scenario is, from HDFS, you are extracting the data outside the Hadoop framework and loading it into a relational database. And from relational database, whatever the applications that are hosting on top of this relational database are also interacting with the HDFS data, or also interacting with some of the tools in the HDFS in Hadoop. So in this particular scenarios, so only relational database is something which is out of your environment, out of your Hadoop framework. So rest all are sitting inside the Hadoop framework. So in these kind of scenarios, you may have to migrate everything into Hive, and you'll make everything local to Hadoop framework, and it's going to be fast retrieval. Okay, it's going to be helpful in the quick retrieval of the data. Because apart from that, if the entire some of the times, most of the times, clients are gonna request you to migrate into Hadoop framework. That's one of the requests you're gonna get. There is no other option other than to migrate it. And in some scenarios, like I said, downstream or upstreams are somewhere related to the Hadoop ecosystem. So these are some of the scenarios you might encounter wherein there comes a need for you to migrate to a Hive environment. Okay, then the features being similarity with SQL. That's a major feature. Okay, difference from SQL. The major difference is that Hive query executes on Hadoop infrastructure rather than a traditional database. Yes, Hive to scale on a huge datasets. Datasets so large that high-end expensive traditional databases would fail. The internal execution of Hive query is by a series of automatically generated MapReduce jobs. So any new thing that we have seen. So yes, Hive executes on a Hadoop infrastructure, and that's different with the databases. And where you have large amounts of datasets, where your traditional databases would fail, that's where your Hive is gonna help you to scale the data across multiple clusters. And the internal execution to Hive is again MapReduce. Like I said, every query, every operation that you perform on Hive is getting converted into a MapReduce program ultimately, and it's going to get executed on top of the MapReduce engine and will get you the results. Okay, RDBMS versus Hive, you can just read through whatever the comparisons we have. So Pig versus Hive, we don't know what is Pig at this moment, so forget about this comparison. So Pig is mainly used for non-structured, unstructured data sets, okay, where you do not have a proper schema. So Pig is also out of the market now, guys. So there is no company which is using Pig in their environment, because there are many better tools than Pig. Okay, so MapReduce versus Hive, you can just read through them, and there is something called as Hive architecture. Okay, so CLI, JDBC, ODBC, and a web UI. So there are different ways of interacting with your Hive interface, Hive engine, execution engine. One of it is using a command line. So using a command line window, you write a Hive query, or you write an insert query, or whatever the queries you want. And there is a JDBC or ODBC. So when you are trying to interact with an external system, like I said, there is a scoop connectivity, right? So on the source side, there is a relational database. On the destination side, there is a Hive command, Hive terminal. So how do you interact with this Hive execution engine using scoop? So it's going to be through a JDBC or an ODBC connection here. And there is one more web UI. So using the web UI, it's not available for all the versions of Hadoop. It's not available in the open source version of Hadoop, but in Cloudera, in a Cloudera interface, there is something called as Hue terminal. Okay, HUE, Hue terminal. So in Hue terminal, there is an option for you to write a query in the web UI itself. Okay, so there is an option, a Hive editor available within the Cloudera Hue terminal, wherein you can write the query and you can actually interact with the Hive tables. Okay, so there are different ways of handling it. That's what it means to say, using a command line, or through a JDBC, ODBC, or through a web UI. So now whatever the query you submit is gonna get to the Hive server 2. So this Hive server 2 is kind of a master, or it's kind of a main execution engine that's going to get the request. And so this is again, Hive server 2 is an external interface where you are trying to interact with the external servers. That's when you will hit the Hive server. If the command line, it's directly running on top of your Hive execution engine. And there is compiler, optimizer, and executor. So compiler is used for compiler and optimizers are mainly used for the syntactical verifications and validating whether the particular schema is available in the particular table. So when for example, if I'm saying select ID from EMP, that's the query I submitted. So first thing is whether the syntax of the query is correct. So that validation is done, and the next process will be whether the table EMP is available in the Hive environment, Hive metastore, and whether you have the column ID available in the Hive metastore. That validation will be taken care of, and then your executor will start executing it. So what executor will do is it will convert a Hive query into a MapReduce program. Okay, so whatever the select star from query you have written, that gets converted into a MapReduce program, and it's going to get submitted to a MapReduce engine. Okay, so Hive submission is done here. Whatever the query you're submitting, it is done here. Compiler and optimizer will make sure the syntax and the validation of the query is done on the Hive side, whether the proper table is available or the proper column name is available, proper syntax is provided, and then it will send to multiple executors wherein they will convert the Hive query into a MapReduce program. Okay, so this is where actual conversion happens, and that's when your MapReduce job will get executed, and the result will be shared with the in the whatever the user interface you submitted the query. Okay, so there is this metastore available. So metastore is something which is used to store the schema or the data type formats of a particular table. So by default, Hive metastore is kind of a database. It's a Derby database which is available within the Hive environment only. Okay, you're not supposed to, I mean, you need not create any external database for it. So Hive itself is a database for us. Itself is a ETL data warehousing tool. But for that, to store the schema, to store the table information, to store the database information, you have some internal database for it. That's, we call it as a Derby database, which comes with a default Derby database. And that is what we call it as a metastore. Okay, so you can also integrate it with some external databases also, but that's again some kind of a complicated process. As in when, I mean, only when it is required, you will take care of that particular thing. Other than that, it's fine. It's straightforward installation. And physical layout is a warehouse directory. Tables are stored in subdirectories of a warehouse. Actual data is stored in the flat files. So how a data is stored in a Hive table? So one thing you need to understand here is, whenever you are loading some data into a Hive table, so generally, if you look at the relational databases, for example, on Oracle database, so when I do an insert into a so-and-so table, where is the data actually getting stored? Will you be able to see the physical storage of the data, where exactly it is being stored? How many of you have interacted with the Oracle database or Postgres database, any of the relational databases, MySQL or whatever? How many of you have actually worked with them? Okay, so you have a table, MySQL, is it? So you have a table, you have some data, 100 records in it. You now inserted another 100 records. So where is the data actually getting stored? Where is the physical storage of that data? Can you see that? Yes. So you'll have something called as a MySQL server, which will hold all the information, but you will not have a privilege, I can say, or see, not even the access, but see, you will not have a segregation of these tables, data, databases, and all that in the Hive server, in the MySQL server as well, right? So in Hive, what is going to happen is, there is no data that is holding on the Hive table. I mean, what I'm trying to say is, for example, I created a Hive table, EMP, with ID, name, and salary as the columns. So when I insert a data, your data will get loaded into HDFS. It's not on the Hive table that you're loading. When I do an insert command, or when I do a whatever the load command, the data will get loaded into HDFS, and your Hive table is actually pointing to that HDFS location. Okay, so whenever you're creating a Hive table, you will allocate some location for it in the HDFS. That means whatever the data you load from there on will get loaded into that location, or whatever the data you load into that location will be displayed on the table. Getting the difference? Okay, so whenever I'm creating a table, I'll give some location in HDFS for it. Okay, so when I do an insert on the Hive side, you will find a file getting loaded into a HDFS location, in the same HDFS location. Or when I do a normal CP, okay, CP command, move command, right? Copy from local, copy to local, all that commands. So when I load some file into that location, when I do a select star from EMP, whatever the data you have in that new file also will get displayed in the Hive table. That means the actual Hive table is only pointing to that location in HDFS. So whatever the files you load, whatever the data you remove, whatever the files you remove will reflect in the table information. That's what I meant to say. Getting it? So now if I have to show that, one second. Okay, so let's do this. I'm sharing my, is it visible? Notepad. So the Hadoop locations now, right? So this is user, some Hadoop. This is all HDFS, let's say default HDFS location. Okay, so inside user Hadoop, I have user Hive warehouse. This is a default location for your Hive. That means, so this path is your HDFS. Like in the command line, just now we have executed Hadoop FS Hadoop FS -ls. This is the command we executed, right? So after a slash, whatever the data you have inside this particular root directory, everything is Hadoop file system storage, right? So within that, you are allocating some location, some directory. User is one directory, Hive is one directory, and warehouse is one directory. So this particular location you are pointing as a Hive warehouse. That is a default location of your Hive. So I'm calling this entire thing as a HDFS. Okay. So inside this HDFS, some portion of it will be allocated for your Hive. Okay. So this path is your /user/hive/warehouse. This is your Hive directory, Hive default directory. Getting it? So this entire thing is HDFS. Okay, so it doesn't matter whether this only this particular portion is under the control of your Hive execution engine or Hive framework. Okay, so whatever the tables you create from here on. Okay, so let's say I created a database. Let's say I'm create. So create database sample. This is one command that I'm executing, and then I created table employee and inserted let's say load data into table. Okay, so these three activities I have done. So what is going to happen here? So after I create a table, after I create a database, for that matter, after I create a database, there will be a directory named /user/hive/warehouse/sample.db. Under sample.db, there will be a directory named employee. Getting it? Under employee, I'll have whatever the file. I mean, you can say hello.txt or some part file, part-000. So that means under user Hive warehouse, this is my core directory for your Hive execution. So now you logged into the Hive shell and you created a sample. So sample.db will be your primary directory under your user Hive warehouse. So when you create a new directory, there will be a new directory path that is getting created. So now you logged into the sample.db and you created a table. So table name will be your employee. So table name will be a directory name inside your sample.db folder. Getting it? So sample.db is also a directory, and every table you create inside this sample.db will also be a folder, will also be a directory. So inside the directories, whatever the data you load will be loaded as a text file or whatever the formats you want to specify, CSV, text, or whatever the formats. Getting it? So this is how the structure will be. So now you create a new DB, how it is going to be. So under /user/hive/warehouse, you'll have new db.db. So there is a new db.db which is getting created. So there is a new directory getting created with that database name. So inside that, all the tables you create will have individual directories again. Are you getting it? Yes, guys, clear?
Yes, Raman. Yes, Raman.
Right. So whenever you load some data into this table, there will be a new file getting created. So now there is a new file /part-00001. And when you load another, when you do any other insert command, there will be a new file called part-00002. So let's say I have some 10 records in it, and I have some 10 records in it, and I have some 10 records in it. Okay, so this is all I'm doing an insert from the command line, from the Hive command line, doing an insert into table name, so and so records. This is how it's going to get created. So now what I've done is, in HDFS, there is one more file, let's say. There is hello.txt in HDFS, somewhere in HDFS. Now what I've done, hello.txt, I copied it into using Hadoop FS CP, hello.txt. I moved it into whatever the location, user, Hive, warehouse, sample.db/employee. I loaded it here. This is a normal copy command. It's a normal copy command. All these are insert commands, and this is a normal copy command. This has how many let's say I have some 15 records. So now on the Hive shell, when I do select star from EMP, I'll get 10, 10, 10, 30 plus 15, 45 records I'll be getting. That means you can either load the data into a table using a CP command, or you can load a file into a HDFS location, or you can also do an insert into a Hive table. Both ways, you are ultimately storing some file in your employee directory. So whatever you have inside that employee directory will be displayed on your table info. Select star from EMP will show you those information, this data. Getting the point now? So the only reason, the only constraint should be whatever the structure, whatever the schema you gave for your Hive table creation, the data in hello.txt also should be in the format of a same schema. Okay, so same format, whatever the tab separation, the 3 columns, 3 records, how the columns are separated, how the rows are separated, that schema you have to maintain in the hello.txt to be able to display that in the table. If the schema is not maintained, it will be formed as null. All the 15 records will be formed as null. Okay, it will take 15 records, but it will show null values in it because it can't align the schema with the table schema. Okay, so that's the difference here. Now we will do that. We will do some simple basic hands-on also if required. So this is where we are. So user warehouse directory is by default user Hive warehouse only, and the tables are stored as subdirectories of the warehouse. So inside the database, you have this subdirectory with the table name, and all the data is stored in the form of a flat file. So .txt or whatever the extension, that way you'll be storing the data. Okay. So now moving on to the Hive query language, we know it's a very similar SQL. Subqueries, joins, groups, does not have any SQL. Okay, so here's the point. So Hive does not have SQL statements such as insert, update, and delete. So what does this mean? So generally, see, you can do an insert command, or you can do a delete command, or you can do an update command also. But theoretically, see, what is Hive used for generally? It is meant to use, or it is meant to deal with large amounts of data sets, right? So when you have these large amounts of data sets, we are talking in terms of some millions of records. So do you actually have to do an insert command on one single record? See, insert, update, and delete, how many records are they going to change? If you do insert, it will only insert one record. If you do update, it will only update one record. If you do delete, it will only delete one record. So this record level updations, record level insertions, or record level deletions are not preferred to be done in Hive terminal. Okay, so when we talk about the underlying functionality of HDFS, we are only meant for writing it once and reading it many number of times. So whatever you write, you dump it once. After that, you read it any number of times. Okay, so when you dump the data into HDFS, there is going to be some metadata that is going to get created, and using that metadata, you're going to read it any number of times. So for every single record you write, there has been a new metadata that is getting generated, or there has been some activity that is going behind in the HDFS, right? So when you're doing an insert, that means you're writing some data into HDFS. So in HDFS, the concept is write once and read many. So which is not in line with insert, update, and delete. So using insert, when you have some 100 lakh records in the table already, and you use insert command and do one record insert, that's not a suitable scenario for your HDFS operations, right? So you can definitely do it, but update is not going to possible. But insert and delete, I think you can definitely run it, but it's not preferred. It's not preferable to use them. And generally, you use an insert override table, using which you can do some data. You can extract some data from a different table and dump it into this insert table. Okay, so it's not that it is not possible. It can be done, but it is not preferred to use. Okay, then. So create table syntax, there is a create table command, create table, table name, the data column 1, column 2, and the location. So this is where the location will talk. So location is in HDFS where you wanted to store this data. Okay, so I have to specify a location in HDFS so that it will create a directory with the table name, and all the data from here on, whatever the data you load into it will get loaded into that particular directory only. Okay, then So there is something called as an external table and internal table. The managed table is internal table, and there is something called as an external table. So what is the difference here? So now going back to the diagram. So now we know this is all Hive warehouse, right? So whenever I say Hive warehouse, that particular location in HDFS is completely under the control of Hive framework. Okay, so user Hive warehouse, this particular folder, this particular directory, and all the subdirectories in this particular location is all under the control of Hive warehouse, Hive framework. It's not that this is not HDFS, this is all within the HDFS only, but this particular portion has some control on Hive has some control on this particular location. So now when I say I create a table, I don't give any keyword, create table, table name, and I just give some location. So that will create and manage a table, and the location will point to some location in the user Hive warehouse. So that means the data folder is getting created in the user Hive warehouse only. This data folder is getting created in the user Hive warehouse only. But if I give external, it gets created anywhere in the HDFS. It can create here, it can create here, it can create some user home or whatever the location, anywhere it can get created. When I give create table, create external table, table name. So where is it going to matter? How is it going to matter? If I create and manage a table, the data is in your user Hive warehouse, and whenever you delete or when you drop a table, the table will get deleted, and also the data will get deleted in the HDFS. But when the data is external table, when the table is an external table, it can be loaded anywhere in HDFS. When you drop a table, the table will get deleted, but the data will not get deleted. The data will still be there in HDFS location because it does not have control to delete the data from HDFS if it is an external table. If it is external to Hive, it cannot control the data in HDFS, right? Hive, if it is internal, if it is within the Hive warehouse, then it can delete it. It has the control, it has the complete control. If it is a managed table, if it has every control to it. Getting it? So my syntax will look something like this. So create table emp id int name string salary int location user Hive warehouse, and then emp some location in HDFS. This is my table creation table creation table. So I didn't give any keyword here, so same command I'll be using it, and I'll write external keyword. So this is the difference between, if you give external keyword, you can give any location, user Hadoop, some other location, okay, some emp ext, some location I'll be giving it. So this table is getting created internally within this Hadoop framework, and this table is getting created externally anywhere in the Hadoop framework. So now when I do a drop table, emp table schema table and schema and data in HDFS gets deleted. But whereas here table and schema will get deleted, data in HDFS will not be deleted. Okay, understood? Manage table and external table. Yes. Now see, this is getting created in user Hive warehouse emp folder. This is getting created in user Hadoop myext folder. So this is your user Hive warehouse is the core Hive warehouse location. Okay, internal table I'm creating it here. Okay, so now I created an internal table and I gave a location which is local to Hive, which is user Hive warehouse. So it has control of it and it is deleting emp data also. And I created an external table. I don't have to give this user Hive warehouse. Yes. Now this external, I'm creating it externally and I'm giving a different location. So now I have a question for you. So what if I create an internal table?
Just a quick info guys, if you want to make a career in big data, then Intellipaat provides an advanced certification in Big Data Analytics by ENICT Council IIT Guwahati. It is taught by IIT professors and industry experts. With more than 10 years of experience, this course is designed to upskill and land your dream job. Now let's continue with the session.
some location outside the user Hive warehouse. Anything, okay, users, Hadoop, or some dummy location. This is not user Hive warehouse. If you see the difference, I'm giving the location external to Hadoop, means getting the scenario, right? I'm creating somewhere here. I'm creating the location somewhere here, outside user Hive warehouse, and I'm creating internal table only. Okay, and there is one more scenario. I'm creating an external table with the location user Hive warehouse. Opposite scenario. So now, if I drop this table, internal table, which is outside the external to location to Hadoop, will the data get deleted? And if I create an external table with location inside the user Hive external, user Hive warehouse, will the data get deleted? So just find out these two scenarios, and then we'll continue the discussion. So just think about it. What is going to happen? Think about this internal table, external location, external table, internal location. Okay. Can you think of this too? So here, this is your managed table, this is your external table, and these are the data types. So all the data types that your Hive will support: tiny int, small int, big int, float, double, boolean, string, complex, and user defined, whatever the data types we have, right? So all these things it will support. And examples for creating a table: create table, column name, data type, create table, column name, data type. And there is something called as a row format delimited, fields terminated by a \t. So what does this mean? So now going back to, or else we will talk about it when we do hands-on. Is that okay? Fine. So I'm doing a create table, and there is a load command. So load, what is this load? So like I said, insert command, insert update, override. So generally, how do you write an insert statement? So when you already have a table, insert into so and so table, select star from the other table. Is it possible? So you have table 1, which has some 100 records, and you have table 2, which you created now. Okay. So I'm writing insert into table 2, select star from table 1. What is it gonna do? You dump all the 100 records from table 1 to table 2. That is one way of inserting it. Insert override table 1, table 2 from table 1. So that way is possible when you already have the data in the Hive environment itself. When you already have the data in the Hive tables, you move the data from one table to the other table. But in general, a normal insert statement is something which you provide manually. You give the data manually, right? So insert into table values and so columns, so data. That's what you give, right? That is not a possible scenario because Hive is meant to work with large amounts of data sets, and doing the insert, update, delete on single data is not a preferred scenario. So for that, there is a bulk load option. Okay, so when you have the data available in a file or in a proper some flat file with some hundreds of records, then you directly load the data into a Hive table in a bulk way. Okay, so it's not one by one. So what is the command? Load data local in path into table name. So what is the data? Load data local in path. So in path as in the data where the path where the data is available. So there, let's say you have some file follow.txt which is available in so and so path. So load data local in path into table, the table name. So what it actually does is it will just transfer the data from this location to the Hive table location. Getting it? So you created some location for your Hive table, right? In the previous scenario, this location. So wherever the data is available in hello.txt, whichever path the data is available, you just move this data to your Hive table. So load command is not an actual insert command, but it is a CP command which will load the data from an external location to your Hadoop Hive table location. Clear? Is it clear? And there is something called as a keyword local. So what is this local keyword? So there, the actual command is load data in path. So there is a keyword called as local. When the data input path is in your local file system, then you have to specify the local. Otherwise, if it is within the HDFS only, you don't have to specify this local keyword. Okay. So local keyword is only used when you have the data in your local file system. Getting it? So when the data is already available in HDFS, you just have to give load data in path from this location to a table name that will move the data from the file location to the table location. That's it. Okay. Then show tables, show databases is all generic. There is nothing new in it. And select star from table name is also same. Drop table name is also same. And altering table is also same. You just have to do alter table name, add columns, whatever the columns you want to give, alter table name, the table rename command. And in addition to this, there are many other alter statements. The syntax is going to be the same for everyone. And using where condition is again the same. Select star from table name where whatever the condition. If ID is greater than 100, name is so and so, all that where condition filters you can write. It's similar to SQL statement. And group by condition is also same. The column names from departments group by the column name. So it's going to group all the columns depending on the department ID column. Got it? Then there is a join condition. So in similar to your normal SQL joins, how many joins do you have in SQL normal, in normal Oracle or other SQL commands, right? So all that join conditions would work in your Hive. So inner join is the common elements from table 1 into table 2, and the outer join is the opposite of the inner join, and left outer join is common to left table, and right outer join is all the columns from right outer and common matching columns from the left table. So we will execute them anyway. So it's again the routine scenario, whatever you know. So built-in functions, there are some built-in functions available: round, floor, ceil, random expression, and these all upper, lower, count value, sum, variance, if, cast function, Unix time, to date, year. All these functions you'll be using on top of the data on a specific column. We will execute some of them when we do the hands-on. And there is also something called as partitioning in Hive. So have you heard about partitioning in normal SQL tables? Do you create these partitions? Right? So generally, when you have see, most of the times the partitions will be on, let's take one scenario. For example, I have some 1,000 records in a table. Okay. ID, name, and salary, same. Okay. I have some 1,000 records in a table. And I have written a where condition saying select star from EMP table where ID equals to some 960, whatever. Okay. Where ID equals to 960. What is going to happen? So you start searching for the records from the beginning. So start ID equals to 1. If it is equals to 960, no, you start the next record, and you traverse through all those 960 records to find the proper matching ID column. But let's take another scenario. I have 4 columns now: ID, name, salary, and gender, let's say. Okay. So out of 1,000 employees, 500 are male and 500 are female. Okay. So there is a gender column also available in the Hive table. So now I have written a filter condition. I have written a where condition saying select star from EMP where ID equals to 960 and gender equals to female, let's say. Okay. So whatever the 960 column is a female candidate, female employee. So now what is the scenario again? You have to search through all those 1,000 records, all those 960 records, and find the relevant value. So now if I partition this table, so what is this partitioning gonna do? So partitioning is done on, you have to identify a proper column where the number of occurrences, the number of different occurrences of the column values are very less. So how many different values you can have for gender? For ID, for example, you'll have all unique values, right? So ID is a primary key for me most of the times. So you'll have different unique values. You cannot have a partition on that. Name you cannot have. Name can be different. Salary you cannot have. There is no fixed bracket. Gender you can have because there are only 2 possibilities: gender male, gender female, right? So now I create a partition on top of the gender column. So now in HDFS, there are 2 folders getting created under table, under directory EMP. There are 2 subfolders with partition gender equals to male, partition gender equals to female. So all the records with gender equals to male will sit in the first directory. All the records with gender equals to female will sit in the second directory. Now when I write the same query, select star from ID where ID equals to, select star from EMP where ID equals to 960 and gender equals to female, I'll traverse to the HDFS location, I'll get into the EMP directory, and now I'll directly get into the gender equals to female directory. I'll not even search for records gender equals to male. So you are almost removing half of the possibilities. Agree? Understood? So you are trying to reduce the number of records that you are searching for in the filter condition, in the where condition, right? So for that reasons, you'll be doing the partitioning, and not just for this. When you have large amounts of data sets, like when you have every day you have some hundreds of records coming in. So how do you differentiate, or how do you segregate the data from yesterday's records to today's records is using the some date column. Okay, so you'll be partitioning it via a date column. So whenever a new record comes in, a new partition file will get created so that it will be easy for you to identify, okay, these are the records which have been received today, these are the records which have been received yesterday. So most of the times, guys, in real-time scenarios, your partition column will be a date column only. Okay, so but it may vary, but in real-time scenarios it will be mostly a date column. Okay, so segregating the data depending on different possibilities. So how do you select the partitioning column is important. When you have ID, name, and salary and gender, your partition column will be gender, because the least number of possibilities the gender can have is only 2. So for example, let's say ID, name, salary, gender, and city. If I have 5 columns like this, what will be your partition column? Gender again, and why not city? So in that case, what you're supposed to do is you have to find out the generic distinct values for a city. Okay, from the table, you try to find out the distinct values for the city. If the distinct values are only 3 or 4, that means your entire data set is only revolving around 3 or 4 cities. So for example, your company has locations only in Vizag and Hyderabad. Let's assume you'll definitely have employees within only Vizag and Hyderabad. So in that case, what will be your partition column? Is it going to be gender, or is it going to be city? You can choose both, but if I have to choose only one, so it depends on what criteria you are using for search again. So if most of your searches are on gender, if most of your searches are on city, then depending on that, you'll have to select. Okay, so if I'm searching mostly on gender values, then it doesn't make any difference if I'm doing partition on city, right? So again, if you are still confused, you can select both. So in that case, what is going to happen is partition by gender, comma, city. This is how you'll be selecting. So how is that your data will be looking like? Home, user, Hive, warehouse, under which sample DB is my database, sample.db, under which you will have a table named employee, under which you will have a folder directory, gender equals to male and gender equals to female. And under gender equals to male, you will have city. There is another folder, city equals to Hyderabad, city equals to Vizag. So inside this, you will find data file, flat file. Okay, here again, flat file or txt file. So this is how your directory structure will look like. Under gender equals to male, you will find 2 more folders, and under gender equals to female also, you will find 2 more folders. Agree? Got it? This is how your folder structure in HDFS will look like. This is a folder directory, this is a directory, this is a directory, this is also a directory, and this is where your file is available. So this file has only values with gender equals to male and city equals to Hyderabad. This file has only values with gender equals to male and city equals to Vizag. So if I am searching for a specific record with gender equals to female and Vizag, it will exclude all these values and it will come and search only in this directory. So almost 75% of results we are skipping. Getting it? So you can also have like this multiple levels of partitioning, but it is preferred to have at least, not more than 2 levels of partitioning, because it's going to complicate the structure. Okay, so it's going to complicate the entire flow of it. So not more than 2 partitions you can, it's preferred to create. So just try and make sure you have only two or at most 3 levels of partitions and not more than that. Got it? So this is what we do in partitioning. We will do this, and like this you have dynamic partitioning and custom partitioning also in Hive. We will see what is the difference. So how do you create a partition table? So create table name, column, data type, everything, and partitioned by the column name, right? This is how you specify. So okay, we will talk about this example loading in the scenarios. So if you want to list out all the partitions that are available for your table, you can run a show partitions on the table name. It will tell you what are the list of partitions it has got. Okay, and Hive queries are scripts. So if you want to write an SQL statement, if you want to write some series of SQL statements, you can put that in the form of a .html file, and you can run through the command line using hive-f and the queries.html. It will run all the scripts one after the other. So this is mainly used when you are doing a scheduling jobs. Okay, so when you have to schedule some set of HQL statements, then you can provide them and you can trigger them through an external window. Okay, so there is something called as an Oozie, which is a workflow engine, which is mainly used for scheduling the jobs at regular intervals. For example, if there is an insert operation happening, or if there has to be some load operation that is supposed to be scheduled at every 1 hour, so that can be done using Oozie. So Oozie is also out of production, guys. This is not being used. Correct. So most of the companies are using Airflow for their scheduling now, because it has got very much feasibility or very much reach to almost all the technologies. So Oozie is completely out of market. It's only relevant to, it's only restricted to a Hadoop framework, right? So Airflow has got a better reach. So it's something similar to Airflow, right? So that is done. And data management using Hive. So how do we store the Hive result to a HDFS location? So insert overwrite directory, whatever the path you wanted to specify, and whatever the query. So for example, if you are writing some complex query, and whatever the data output you receive from that query, you wanted to store it in a file. So this is how you are supposed to write. This query will have whatever the result you generate from this query will get loaded into this location in HDFS. Okay, and you want to create another table on top of this, similar to like we have done here. You can write create table, a new table as whatever the complex query you wanted to write. Okay, so all generic SQL statements. There is nothing new here. And text file versus the sequence files. So generally, this text file format allows tab spaces and JSON. Sequence files are under binary files with key value pairs. So guys, generally there are 4 to 5 file formats available. The better or the most used is the what is it? Avro format is something we have used. Parquet format we have been using, and ORC format is also something which we tend to use most often. Okay, so ORC, Avro, Parquet. So these file formats provide proper compression and proper mechanism to store the data. Some of them store it in binary format, and there are different advantages and disadvantages for each and every format. So for example, if a file is of some 100 GB, so using ORC you compress it to some 60 GB. Using Avro you compress it to some 50 GB, right? So instead of using the 100 GB of storage, by storing it in a plain text format, you compress it and store it into different formats. Okay, so there is another separate concept altogether for different file formats. So you can specify. So how do you specify in the table creation statement? So create table name, the data types, and stored as sequence file, stored as ORC file, stored as Avro file, stored as RC file. So all these are different file formats when you can use while creating the table. Okay, and the optimizations, the denormalizations, partitioning, and indexing, these are some of the concepts we can discuss. How do we create the index? So this is all again advanced concepts, guys. How do we index, how do we create the index, and how do we use that index to better retrieve the results? So partitioning, we know what to do. And there is something called as a user defined functions. So in one of the slides we have seen different built-in functions that are available, right? So if there is a functionality which you wanted to which Hive does not support, which Hive does not have any function for it, and you wanted to create your own function for it. Okay, so let's say something like for example, there is a column wherein you have the data in the format of timestamp. Okay, so you know the timestamp format, the date, month, year, hours, minutes, seconds, and the time zone, right? All these things together you form it as a timestamp column. Okay, so you don't want a timestamp column, you wanted to extract only the month out of the timestamp column. So your requirement is something like this. Okay, so we cannot tell where exactly you'll be using this scenario, but what if your requirement is something like this? So you don't have any function to extract month out of the timestamp, let's assume. So you will be creating your own function, you'll be creating your own Java program. So this is how you'll be writing. So there is a method, there is a class, abstract class, UDF abstract class. You extend this UDF abstract class and define your own logic for it. and create one function for it, and then you start using it. So there are 6 steps, I guess, 5 to 6 steps available. This is how you write the program. So this is again a MapReduce program, and how many steps? So add jar, creating this particular program is one step. Creating a jar from this program and adding the jar to the Hive class path and creating a temporary function and then using the temporary function. So 4 to 5 steps are available in the UDF process creation. So generally user-defined functions are used when you don't have any built-in function for a specific functionality. If you frequently use that particular functionality, it's going to take time for you to implement every time. So you create a built-in function. You create a custom function. That's we call it as a user-defined functions. Okay. So introduction to Spark and Scala. So yeah, tell me, what do you know about Scala or Spark? Let's start with Spark. So what do you know about it? Any basic understanding in simple terms? What is Spark and what is Scala? So it's processing the large data. What is the advantage that we get with Spark? I mean, see, we already know that there are some frameworks, for example, Hadoop, that can process large amounts of data sets. So why Spark? It's open source. Hadoop is also open source. Okay, faster than Hadoop. Why? How is it faster than Hadoop? Any specific reason? What's the main core concept behind the Spark or the Scala functionalities? So generally, we consider Spark and Scala. Spark, let's say, and let's talk about Scala in some time. But so generally, Spark is mainly used for the real-time data processing, both batch as well as the real-time data processing, and it's considered to be a fast processing tool, almost like 100 times faster than whatever the MapReduce way of handling it. Okay, so the reason why we say it's fast, because it is doing a in-memory processing. Okay, so that's the most important factor for the speed that it is achieving. Okay, so in-memory processing is something which is gonna increase the speed drastically, and that is why we are getting this kind of an advantage. Okay, so what do you mean by this batch and real-time processing? Okay, let's get to that slides. Okay, so for the agenda being, so we should be able to complete the we should be able to understand the batch and real-time processing, difference between Hadoop and Spark. These are all the concepts that we will be discussing. And big data analysis can be done in two ways. So there is a batch processing and a real-time processing. So what exactly do you mean by batch and real-time? What is batch data processing? So real-time, you must be knowing it, right? Okay. So we'll divide the data into batches and then process it. Then what is real-time? Okay. So generally, the batch processing is something where you have the data already available. Okay, so the file has already been generated. Okay, so it's not a scenario where the file keeps getting updated every second or every minute. Okay, so the file has already been generated, and you already have whatever the extension, you already have the file getting stored, and then now you are trying to analyze that particular data file. Okay, so let's say I'm generating a CSV file. So yeah, I completely loaded the CSV file in so and so network drive, and you have to read that file and do some kind of analytic process. Okay, so the file is already available. It's already got loaded. It's already completed. It's in completed stage, and you're trying to access it now. So how you can access it is secondary. You use Spark, you use Hive, whatever the tools and technology you wanted to use, but that all comes under the batch processing. You read the data which is already available, you break that into multiple batches, and you'll be loading it into your framework and processing it. But real time is that something that keeps changing every instance. Okay, so there is a file that is getting updated, or there is a database that is getting updated at regular intervals. So for example, I have a database, I have a table, and I kind of inserting the records at every minute. So what you need to do, as and when the data gets generated, you're supposed to extract it and you're supposed to process it. That's what we consider to be a real-time processing. Okay. So that's the difference. When the data is already available, when it's not moving, it's not changing frequently, then we consider it to be a batch processing, and real time is something which keeps updating every time, and you are supposed to access it in a real time manner. So there is no system which is going to access it in a real time manner. It's always near real time. Okay, so near to the real time process. Getting it? So let's understand what is batch data processing. So batch data processing is an efficient way of processing high volumes of data, such as group of transactions, which is collected over a period of time. So how do you handle this data, which is very huge? You kind of divide that into multiple batches and do whatever the analytical process that you're trying to do. So data is collected, entered, processed. Batch results are then produced. Hadoop is focused on batch data processing. So there is one example that I can share in real-time scenario. So there is one requirement where we have some 20 lakh records in one of the database, in one of the NoSQL database. So we have written a program. We have written a Python program. We have written a Spark program. And see, in both the scenarios, you are using some kind of a connector to a relational database, or no SQL database. It's MongoDB. So you are using a connector to a NoSQL database, and you are trying to extract the data from a NoSQL database into your Python data frame, pandas data frame of the Spark data frame. So how many of you are aware of Python? At least very high level. Okay, that's fine. So using some connectors, we will be extracting the data. So it's always not possible. It's always not possible for you to load the entire 20 lakhs of records into your whatever so-called processing frameworks, Python or Spark. So what you're gonna do, you divide that into multiple batches. So the first time, whatever I'm doing is I have a job to import all the records, all the 20 lakh records. But 20 lakh records at a time is not possible. So what you will do, you will break the data into multiple batches. I'm not breaking it actually. So I'll only collect the data whichever is with some timestamp, let's say. Okay, so if the data has been generated from so and so time to so and so time, I'll select that as a first batch, and I'll flow this particular batch of data through all the processes, and I'll dump it into whatever the destination it is. Okay, so you're extracting some amount of information, some batch of information, transforming it, then loading it into some destination system. So all these things you are doing it in batch wise. Okay, so depending on some timestamps, so from here to here, here to here, something like that, giving an upper limit and lower limit, you'll be extracting some data and you'll be processing it. So this is batch data processing, which has already been generated, which is already there. That is a historical load, I can say. Okay, when you want to migrate the entire data into your Hadoop ecosystem, then comes a near real time. So after you have loaded the entire data, whichever you have, all the 20 lakh records, whichever you have into your Hadoop framework, into HDFS, let's say. Now, whatever the records keep generating every day, for example, today I have run the job. So tomorrow, the same time, I'll trigger the job. So whatever the records that have been generated from now to till tomorrow morning, till tomorrow the same time, those records I'll be pulling it. So that is a near real time. I'm calling that as a near real time. So it's not a very near real time scenario. We are giving 1 day interval, but that's how it's going to be. So you generate the events or extract the data as and when it is generated. So there is a real time streaming also available using Kafka and different tools. You can do that as and when the data gets generated, the trigger will happen. But again, everything comes under the near real time process. Okay, so ETL process extract and transform and load the data which is already available, and you do that in the form of batches. Okay, then what is real time data processing? So real time data processing, involves a continual input, process and output of data. So it provides an organization the ability to take immediate action in times when acting within seconds or minutes is significant. So for example, back ATMs, customer services, radar systems, and point of sale systems. So what are they trying to do here in near real time? So the data keeps coming continuously within seconds interval or within some minutes interval. So your job is to try and read the data as soon as possible it is generated. Okay, so as and when it is generated. So how do you do this? you kind of establish a trigger with the source system with the database. Let's say on the source side you have a database, on the destination side you have a HDFS system. In between you have some process. So you will establish some kind of a alerting mechanism on the source side. So this is a very odd term to use, alerting mechanism on the source side. So it will just keep watching that database, of watching the table. So whenever the table gets updated with some new records, it will trigger a specific set of process. Okay. So what does this process do? It will start importing the data, it will start processing it, and it will load the data into whatever the destination storage system, HDFS or whatever. Okay. So what is that mechanism? How that mechanism is being triggered? There is something called as Kafka, you can say. There is something called as Spark streaming, you can say. So what are they going to do? They keep they just try and watch the database or watch the table always. So whenever there is some change happening, they will trigger some other process. Okay, so that's the near real-time processing. So how is it going to be used? In most of the live examples, like I can say, like in bank ATMs, in POS, point of sale systems, and radar systems. So whenever there is a the change in the temperature, you kind of get alerted. Yeah, you get alerts on the mobile, or you alert whatever the authorities you wanted to alert them. Okay. So this is the real time data processing, and like I said, there is no system which is real time. Every system is almost near real time processing only. Okay. So now the comparison. So data processing using MapReduce, data processing, real time processing in Spark. So if you look at the comparisons between these two in Hadoop versus Spark, so the processing, the input data is on day 1, and this has been processed on day 2. And whatever the data that you generated on day 2 has been processed on day 3. That means there is some time lag between the data getting generated and the data getting processed using MapReduce. So it's not feasible for a real time processing. Okay. So but whereas in real time processing there is no time lag, as and when the data gets generated on day 1, the data gets processed on the same day. So it's not in terms of days, but generally there is no time difference between the data getting generated and the data getting processed. Okay, so there is very limited time lag in terms of the data getting generated and the data getting processed. Okay, so this is one representation they've selected to use, but it's not going to be something like this. So yesterday the data got generated and there is something like today you will be processing it. There's definitely some time lag in MapReduce, and there is hardly any time lag in your Spark processing. Okay, and then we'll now understand what is Spark. It is an open source cluster computing framework for real-time data processing. It's introduced in 2009, and some history about it. So 2010 it got some license, and 2013 it got donated to Apache Software Foundation. So once it is under Apache, then it is termed as an open source solution. Okay, so all the tools under Apache would be open source solutions only. Then features of Spark. What is it? First feature of Spark, it is real time. So what does this mean? Real time computation and low latency because of in memory computation. So what exactly is happening is you are doing a real time processing, and you are able to do the real-time processing because of this in-memory computing. Because see, for example, I think we have discussed about this scenario earlier as well. So there is some data in HDFS, let's say. So there is some data in HDFS, and you are doing some kind of a processing. I mean, you've written some program to process it. So what happens? You extract the data, you run the operation, you process the operation, and you load the data into HDFS back again, let's say. Okay, or there are some multiple set of operations running. Okay, so there is a task 1, task 2, task 3, task 4. These are not MapReduce tasks, just to let you know. So there are multiple tasks within the same job. Okay, so this is kind of an iteration which is happening within the same kind of a processing activity. So you run a specific task. The output of the task 1 has to be sent to the task 2. The output of task 2 has to be sent to task 3. So something like that, you have some series of tasks that are getting executed. So what happens, the data initially was in HDFS, some location in HDFS. So you ran that job, you got some output of that particular task 1. So where do you store this output of task 1? In general. So you have some list of jobs to run, job 1, job 2, job 3, job 4. So after generating the job, where do you store it? You again store it in HDFS, right? So after executing that particular job. But here in this particular scenario, what is happening? My job 2 is also dependent on the job 1. So it will wait for job 1 to complete. After the job 1 after the job 1 is executed, the output of job 1 has to be sent to job 2. Similarly, the job 2 will complete execution, and then the output of job 2 will be sent to job 3. So here, after the output of job 1 is getting generated, you are storing it into HDFS. You're not directly sending it to job 2. You're storing it in HDFS, and that path job 2 is using it. So when there are multiple jobs getting executed in the form of an iteration, in the form of a loop, multiple reads and write to HDFS are going to happen, right? So in that case, the time consumed for actual write and read of data in HDFS is going to be more compared to the actual processing time or whatever it is. I mean, the time taken for the read and write is going to be very, very huge. So to avoid that, what Spark does is it's going to do an in-memory computation. So whatever the results that you generate intermediately within the set of jobs, this task job 1 output, job 2 output, job 3 output. So you'll be storing that output, resultant output in the memory itself. So it's very faster to retrieve the data from the memory rather than retrieving it from the HDFS. HDFS is a physical storage, a hard disk storage, whereas a memory is something which is available to the processing unit. Okay, so the processing, everything is happening in the memory only. So the data is also available within the memory, and you tend to process it, you tend to retrieve and store it very quickly. So all the intermediate results, you store it in the memory only. You'll not do the storage in the physical, you'll not give it to the hard disk. And that is the reason why the time taken for the entire execution is going to be very less. Getting the difference? Yes, guys. So that is the reason mostly your Spark applications or your Spark nodes, when you define them, the RAM size of their Spark cluster is going to be very huge, around 64 GB or 128 GB of RAM is something which you're going to select. So when we were working, we were having some 64 GB of RAM, I guess. I don't believe that exactly. But in developed environments, you have around 32. So that is how your RAM size will be when you are dealing with the Spark applications. Okay. Then coming to the next feature, there is a generality. So combines SQL, streaming, and complex analytics. So now you're saying there is a better framework compared to MapReduce, and that is something called as Spark. So when I say I have Spark, I should be able to handle any kinds of data for that matter. So any kinds of data, as in unstructured, structured, everything can be handled. There is no problem with that. But how about this Hive functionality? So Hive has a better features, or Hive has some better working in terms of dealing with the SQL related data, the structured data. So in Hadoop framework, you have something like Hive. When you're migrating to Spark, what do you do? I mean, how do you handle the data which is in terms of databases and tables? So for that reason, you have something called as Spark SQL, which is again similar to your normal SQL statement. So whatever the table structure, the schema, the column, rows, and database tables, all that mechanism, all that scenarios are going to come into this Spark SQL also. So you're giving some kind of a support for the SQL way of handling the data also in Spark. So there is a completely different module, Spark SQL, which is going to help you deal with the structured data. And what happens when with regards to this streaming data? So in streaming in Hadoop framework, we had something called as Kafka, we had Flume. So do you have something similar framework in Spark environment also, in Spark framework also? And there is, yes, there is a streaming platform also available. There is a completely another module listed, that is Spark streaming, which is going to deal with the streaming sets of data. Okay. So now you have Spark SQL, Spark Streaming. In addition to that, you have Spark Machine Learning, Spark Graphics. So these are all different modules within the same framework to deal with different types or different forms of data. If it is an SQL format, you deal with Spark SQL. If it is an streaming data, you deal with Spark Streaming. If it is some graph related data, Spark Graphics. If it is a machine learning algorithms you are supposed to execute, and you have this Spark Machine Learning, right? So for different forms of data, you have different modules allocated within this Spark framework. And one simple thing, one most important thing here is there is a concept of RDD. I mean, when we get into the details, we'll discuss more about it. But when there is a concept of an RDD, that's a basic building block in your Spark framework, and it's going to be common across all the different modules. So you have an RDD. You in Spark SQL, you have an RDD. In Spark Streaming, you have an RDD. So that is something generic across all the different modules. Or something, right? So that means you are creating, you're taking one input, whichever is it in whichever is it in any format. Okay, forget about whatever the format it is. We still don't know which module to use, let's say. So I still create the data, I still take the data, I read it in the form of an RDD, and then I'll be using it for different modules. So the data is being flown across different modules using a simple data set, that's an RDD. Okay, so we'll get into the details. It's going to be very disconnected now. But in terms of generality, what does that mean? Generality, it has got features, it has got support for all the any forms of data sets. And the speed, like I said, it is almost like 4 times faster, actually 100 times faster than the large scale data processing frameworks. And the deployment is very easy to deploy. It can be deployed along with Hadoop, or it can be deployed on its own platform, standalone, on its own cluster with a specific cluster manager. And it can also run with Hadoop via Yarn, or it can also run with the Mesos application. And then the ease of use. So what does this ease of use mean? It is flexible with any kind of a programming language. So mostly, what do the programmers do in general? What kind of programmers do we have? We have a Java programmer, we have a Python programmer, some kind of a .NET programmer, and all that, right? So if you are familiar with Java, that's fine. If you are familiar with Scala, if you are familiar with Python, if you are familiar with R, very recently R has got its importance, and if you are familiar with SQL, so all this kind of support you have got with your Spark framework. Okay, so you can write a program in Python, you can write a simple SQL statement for Spark SQL, you can write it in Scala, you can write it in Java. Okay, so Java and Scala, again, I mean, I'm merging both of them together. Both seem to be the same, right? So you can use any of the programming listed programming model to interact with your Spark framework. Okay, so it does not have any language or the program dependency, the coding dependency. So whoever is familiar with whatever the frameworks or with whatever the programming model they have, they know they're that won't be a limitation for anyone, right? So powerful caching, provides powerful caching and disk persistence capability. So what does this caching mean? We will discuss that in detail, but generally, when for frequently running operations, you tend to cache the data in the memory or in the disk. So the caching mechanism is properly done. It's a very powerful mechanism component in your Spark applications. And there are some domain scenarios that have been listed. So what are these domain scenarios? There are some real-time examples that we can see. Okay, so in most of the what do you say? In most of the applications, in most of the domains. So when I say domain, it's going to be across different industries. The financial domain, the tourism domain, or the retail, e-commerce, or the social media, or the healthcare, right? So all these, like, so this can be healthcare, this is social media, the movie industry, or the financial domain, the retail, e-commerce domain, or the tourism. So whichever domain it is in, like, it has got its own importance, it has got its own own features. Okay, So it's across the domains. I mean, it has got its features, it has got its applications running across the domain. So most of the clients are now running on the Spark framework only, right? So now Hadoop is something which is gone, I can say, gone as in like regardless of you use Hadoop or not, the companies are using Spark. Okay, so that is how the importance is, and even though with a lot of competition with Spark SQL or the other SQL ways, Hive is still being used for most of the use cases. Hive is a better or it's a better tool compared to other SQL framework. So Hive is still in the market. It's being vastly used in most of the companies. And there is Kafka also. Even though you have Kafka, even though you have Spark streaming, Kafka also has got its importance. It is still being used by most of the companies, right? So even though you have the competition, the better tools, but people tend to use for various reasons. Hive is still, and Kafka is also still in the market. Okay, sustaining Spark SQL and Spark streaming. Okay, then now getting into what is Scala. So Scala is one way of interacting, or there is one way of interacting with your Spark framework. So it's a programming language, and how is it designed, when is it designed, all that history you have. And it's a multi paradigm programming language which is designed to express common programming patterns in a concise and type safe way. So we will get into the details anyway. But so it has been released in 2003. Okay, and yeah, so we'll get into the features of Scala. First one is the object oriented. What do you mean by an object oriented programming model? What do you mean by object oriented? So what's your core background, guys? Is it Java or is it Python? What's your core programming language? Which one are you comfortable with among Python and Java? Oh, most of you are Java. Then I think it won't take much time for us to get into the Spark, Scala, and the other concepts of Scala, right? You are already familiar with all those object-oriented models and all that, right? Anyone from Python background? Yes, no? So we'll see the features of Scala here. So first is object-oriented. So what do you mean by object-oriented programming model? See, all the questions are gonna come to you. So you guys are already comfortable or already been into Java. So let's keep it interactive. Like what do you mean by object-oriented model? In simple terms, characteristics for an item. Yes, for an item to be called as an object, right? Okay, so it is a pure object-oriented programming model. And what else? It is also functional. So what does this functional mean? So it's suitable for defining various functions for various activities. So when you have a specific use case, you kind of create this lightweight function. So it's, I mean, compared to Java, it's very easy, or it's very lightweight, I can say. Yeah. So as the term itself suggesting, so it's very lightweight syntax for defining different functions and working with it. And statically typed. What do you mean by statically typed? So it's going to bind the type of a variable for its entire scope. So whatever the data you have, you allocate it to some kind of a variable, and you're going to work with it. And extensible. So provides a mechanism that makes it easy to smoothly add new language constructs in the form of libraries. So what does this? What do these libraries mean? What do you mean by these libraries? What are the different libraries? Can you name one? Any simple library that you have worked with earlier? Okay. So fine. So why is Scala preferred for Spark? Can someone tell me one simple reason for preferring Scala over Python? So I mean, I understand you guys have come from a Java background, but in general, why do you think Spark is preferred? I mean, Scala is preferred for Spark rather than Python. So which one is faster, do you think? Whether Python with Spark is faster or Scala with Spark is faster? So Spark itself is faster, but which one is faster in terms of Scala and Python? Yes, any guesses? Okay, so why did you say Python? Yes, because the programming model of Python is designed in such a way that it's very interactive, or it's not that complicated. I mean, it is, I feel, complicated working with Scala, and because it's very close to Java. Maybe that's the reason I feel kind of bit complicated. But so yeah, I agree. Python with Spark, PySpark is kind of easy to understand, easy to work with. But in terms of performance, Scala is something which gets an edge. Okay, so it is something which is better than PySpark. The only reason being it is running on a JVM. Okay, so Scala Spark is running on a JVM, and moreover, if you compare it with the program that you write in Java, it's almost reducing the complexity. So whatever the program you write in Java, it's let's say you have some 20 to 30 lines of program in Java, you can simply replace it with one single line of code in Scala. So there are methods defined, there are very efficient methods defined, and there is a predefined subset of libraries also available within Scala. The support for these libraries and the complexity, the reducing complexity of a complex Java code, and the reason that it is working, it is running on a JVM, will make it more effective. Okay, so that is the reason we if you have an option to compare, or if you have an option to select between Scala and Python, it's definitely going to be Scala because of the performance related advantage. Okay, so that is some things we have. And the Scala shell, how do we start it? It's I mean, when you have a Scala alone install, you just run Scala and it will open a Scala shell. But generally we started using the Spark shell. Okay, so using Spark shell we will be starting it, and that's going to start a Spark environment with a Scala programming. Okay, so for starting PySpark, you will be running PySpark command. For starting Scala Spark, you'll be running Spark-shell. Okay, so the data types, you can see the different data types that it is supporting. Okay, so double, float, long, int, short, byte, unit, boolean, char, list, option, and whatever the null data types you have. Okay, and the range, the data types range, what is the range for each and every data types is listed here. So nothing changes, it's the same thing that you're going to see in other programming frameworks. Okay, programming models. So string is all that is going to see, all that is going to be the same compared to everything. Okay, then variables. So what are these variables? You allocate some data, you allocate some value to a variable. We store that in the form of a variable. Every value you store in the form of a variable, and we have two types of variables available. One are the mutable variables and one is the immutable variables. Have you heard about these two anywhere before? So in that case, what is mutable, what is immutable? Okay, so where is mutable, val is immutable, is that what you're saying? So where is mutable and we can change the value of it. So what if I'm saying where a equals to 5 and then I'll say a equals to 10, is it possible? And val a equals to 5 I say, and I define, and a equals to 5 again, is it possible? No. So val a equals to 10 is one statement, then I do val a equals to 5, is it possible? Okay, so reassignment of a variable is can be done in both the scenarios, but it's something that you cannot assign a new value to the existing variable. Are we clear with these two concepts? Mutable variables, immutable variables. Mutables are where, mutables are val. Mutables cannot be, mutables can be changed. The value can be reassigned or allocated with a new value, but immutables cannot be assigned to a new value. So you guys are pretty much clear about this mutable and immutable concept. So there is some example also listed here. So we will, that's fine. It's just a string example that we gave. Now, multivariable assignment. So what does this multivariable assignment mean? So supports multiple variable assignments in a single statement. So you can assign multiple variables in a using a single line command. So val myvar1 comma myvar2, and you gave the value as 25 and hello. So there are two values getting assigned using a single assignment statement. Okay, so two or more is also possible. myvar1, 2, 3, and 4 you are allocating with so and so values. All these are val variables, immutable variables. Okay. Now, then lazy evaluation. So lazy evaluation is an evaluation strategy that delays the evaluation of an expression until its value is consumed by your application. So have you heard about this lazy evaluation concept before? It's one of the most important feature for the Spark. So what it actually does is, let's say I have created a value. Okay, I've created some variable, and I've allocated some data to a variable. And what example we can take? Let's say, okay, so maybe we can take one simple example. So for example, have you heard about this concept before? Do I have to tell you from the scratch, or you guys are aware of this lazy evaluation? Not aware of it. Okay, so in terms of Spark, let's talk about it. See, I have a data in a so and so file. Okay, so home, training, some HDFS location, I have a data file. Okay, and you allocated that data, you read that data using some mechanism, and you allocated that into some variable. Okay, some whatever, some variable or var variable or val variable. Okay, you allocated some data to it. So now when you are doing this allocation, it actually does not matter whether the data file is available in HDFS or not. See, this Spark or Scala is not going to look for the data in HDFS at the time of the value assignment, only when you are actually using it. For example, in the next line, I'm doing print of whatever the variable. Okay, so only then you are trying to look for the data file, and it's going to try reading the data file and try allocating the data file to this particular variable. So in the first statement, when I actually assigned the data to this variable, it is not even looking for whether the data is available in HDFS or not. It is just one single statement that it's going to execute. It is not taking care of the assignment of the data to this variable, because now at this moment, the variable is still empty. Okay, so Spark or Scala has not spent time to go to the HDFS, get the data and allocate the data to this particular variable. When is it actually allocating it? When you're actually using it. Next statement, what did I do? I have written print variable name. So that's when it's going to go to the HDFS location, check whether the data file is available, and then assign the data to that particular variable, and then print that data in the variable. Getting it? So what is the difference is, in the first statement, it actually does not matter whether the data is available or not. Okay, so if the data file is not available at all, you gave that var statement, allocation statement, it won't give you an error. In the print statement, when you're actually using it, that's when you'll be getting an error message. Getting it? So that is a lazy evaluation. You're evaluating it is lazily. Okay, you're not doing it in the first place, but when you're actually executing them, when you're actually performing some kind of an operation on top of that variable, or some type of an val or a var variable, that's when it is identifying, it's actually evaluating the data. That is what we call it as a lazy evaluation. So the same concept is going to get applied in Spark as well. In Spark data frames or in Spark RDD creations, when you assign some data to it, it will not allocate any memory, or it will not allocate any RAM to perform that activity. It is not going to execute at that time. Only when it is being used by some analytical process by some transformation, that's when it is going to try and execute it. So that is the most important factor of your lazy evaluation. So what is the advantage that we get? So it helps to resolve the circular dependencies. It provides performance enhancement. Sorry, yeah. No, okay. So there is one example defined, lazy val donut service. There is some data allocated to it, and this is your value. And when you have actually printing it, val donut service equals to this one, it is allocating some data to it. Okay, so that's the difference between a lazy allocation and a normal allocation of the data. Okay, so in Scala you have this lazy allocation, but in Spark, or if you get into the Spark concepts of it, Every variable for that matter is gonna be a lazy allocation only. So no matter what the data, when you allocate it, it's not gonna get executed. Only when you start using it for some kind of an operation, it's going to allocate. It's going to execute that particular data. Okay.
Just a quick info, guys. If you want to make a career in big data, then Intellipaat provides an advanced certification in big data analytics by ENICT Council IIT Guwahati. It is taught by IIT professors and industry experts. With more than 10 years of experience, this course is designed to upskill and land your dream job. Now let's continue with the session.
So there are some control structures. You must have heard about them. What are the control structures available? Control statements. There is one if statement. What is it going to do? It's going to validate for a specific condition. If the condition is failed, you execute whatever the following statements. If it is, if the condition is successful, it will execute the following statements. If it is failed, there is an else component which will be getting executed. So you must be aware of all these basic concepts, anyways. And there is for loop for a specific range. It keeps executing whatever the statements that are listed here. You will be giving a range in the beginning for loop, and all the statements will execute it for so and so range, right? And then okay, so there is multiple generators, there's conditions in multiple generators, variables in for loop. So there are all different conditions. There are multiple conditions listed here, right? And conditions in multiple generators. This is how you can define. There is, and this is the variables in your for loop. So here there is a while loop. So the while loop is the difference. The difference isn't like your condition will get executed. Whatever the statements will get executed in the form of a loop until the conditions get failed. Okay, so it will keep checking for this particular condition until this condition fails. It executes this set of statements. Okay, so very generic. And there is something called as a do while. So the difference between while and a do while is the do while will first execute the statement and look for the condition, whereas a while will check for the condition and then execute the statement. So that's the only difference, right? So in Scala, we have just tried to understand what this framework is, what are the different control statements are, and see, firstly, we need to understand what's the core concepts of Spark, how Scala can be used to interact with your Spark framework. Okay, so let's dig a little deep into what this Spark framework is all about. What is the architecture? What are its different components? So I've just tried to see what are the features of Spark, right? What are the different advantages that we get? But let's also get into some understanding of architectures, right? So Spark in Hadoop ecosystem. So here in Apache Hadoop ecosystem, these are the components that we already have, right? So the ones which are grayed out are something related to Spark, so forget about it. So Hadoop platform, we know there is a yarn execution, yarn processing component framework that is available. Under that, you have this HDFS location, HDFS storage. On top of these, there are different tools allocated for it. So right, this is MapReduce version 1, version 2, Pig, Taze, and Mahout, Impala, Hive, Drill, and HBase, and Storm. This is not Storm, this is Storm. Okay. So for batch processing, we have Pig and MapReduce version 1 and version 2. And for machine learning, we have Mahout. No one, I mean, very hardly we use this Mahout related things. SQL, you have Hive. We have seen how to use Hive or what Hive does. And there is also something called as Impala, which is almost similar to Hive, just with minor changes. And for NoSQL, we have HBase, and for streaming, you have Storm, Kafka, and also Flume. Okay, so this is your Hadoop ecosystem, and if you look at these versions, the components which are grayed out here, which are highlighted, these are the components which Spark is going to provide you. Okay, so for every component, for every form of data handling, you have some component in Spark using it, right? So some component in Spark helping it. So for batch processing, your core Spark framework itself is going to help you. For machine learning, you have graphics and machine learning libraries or component. And for SQL, you have Spark SQL. For streaming, you have Spark streaming. So there is no component for NoSQL way of handling in Spark. Okay. So apart from that, it was almost handling all the other modules. It almost got its existence in all the other modules of your Hadoop ecosystem. So for every tool, or for almost like for every tool in the Hadoop ecosystem, you have got some alternative in the Spark framework. That's what we mean to say. Okay. So for any kind of a data handling, you have some kind of a module, some kind of a framework inside your Spark components. Okay. So that's the difference. That is why Spark has got its importance. Like it try to, it's almost overcoming, or it's almost replacing Hadoop in terms of data processing or whatever, right? So there are many systems. There are in real-time systems, like at least if you look at my particular project, so it does not have Hadoop at all. So Spark has been built on its own cluster. We have a specific cluster built on top of it, and Spark is running individually. There is no Hadoop at the back end. So we don't need Hadoop at least, right? So we don't need Hadoop components or whatever it is. So HDFS and all that, MapReduce and Yarn and all that can come. I mean, HDFS, you have a better storage mechanism. You have the cloud storage anyways now, right? So you don't need a HDFS component. So everything, all the storages are now hosted on cloud. So there is no point in having an HDFS storage here. So there is no requirement for your Hadoop ecosystem to exist for Spark to run. It can also run independently. And there is also something called as Databricks, which is giving you a proper Spark cluster creation. So have you heard about it, Databricks? Have you heard about it, Databricks? So it's a cloud-based Spark framework. It's going to give you access to the Spark clusters. It's going to create the clusters by itself, and it will just give you access. You just have to configure. You just have to let the system know that what configuration you would need, how many clusters you would need, what is the version of Spark, and what is the version of Python and Scala. So that's going to create a cluster for you, and it's going to give you. So all your applications can be hosted on top of it. So it's a paid version again. It's a paid component. So that's one of the way of working with the Spark ecosystems. So different scenarios, different use cases there are for your Spark applications to run. And how Hadoop is helping Spark, or how Spark is helping your Hadoop ecosystem. So there are two scenarios which can be considered: Spark and Hadoop together. So Hadoop adding value to Spark. So how Hadoop is actually giving some advantage to the Spark. So Hadoop includes HDFS, which allows you to distribute data across nodes within a cluster of servers, thus eliminating the need of lots of custom hardware. Hadoop provides enhanced data security, which is critical for production workloads. So when you want to run Hadoop and Spark together, how both are helping each other. So Hadoop is helping it by providing a better storage mechanism, HDFS, for distributed data storages, and also with respect to the security. So it's not that Hadoop alone is going to provide these kind of features, but there are other storage mechanisms also which are pretty much doing the same thing. But as we are working Hadoop and Spark together, this is the advantage we get from Hadoop to your Spark framework. And how Spark is adding value to the Hadoop. So whatever the machine learning algorithms that we have, they can execute faster than the MapReduce programs, or any particular programs can execute faster with the in-memory feature of your Spark framework as compared to the MapReduce framework. Okay, so Spark is used for data streaming and in-memory distributed processing for faster real-time analytics, and moreover for the real-time data processing also we have been using it for some of the components. Then the companies that are using Hadoop and Spark together, there are Yahoo, Amazon, NASA, Hortonworks, some of the examples. Okay, Uber, Altiscale, how they're building both Hadoop and Spark applications together, and they're really leveraging the use cases of both Hadoop and Spark. Some of the examples. And what is the advantage we get with Spark and Hadoop together is using with the faster analytics and optimized cost. So how do we get this optimized cost? Because of this HDFS cluster, because it has got its better storage mechanism. HDFS has got its better storage mechanism in terms of building the clusters, the custom cluster, which is built on top of the commodity hardware, and avoiding the duplication, how HDFS can remove all the duplicates using your Spark programs. Okay, and then Spark components. It has a Spark core. It has this data frame concepts or machine learning pipelines, and it can interact with any of these programming models, Scala, Java, Python, and R. And the modules which are coming along with it will be Spark Streaming, Spark SQL, Machine Learning, and Graphics. We've already seen how these modules are built, and the external systems, how we can interact with each other. All these things have got some connectivity with your Spark core systems, Postgres, Elasticsearch, MySQL, JSON, CSV files. It's a direct read and write format of a JSON and CSV. It has got its connectivity with HBase, Hive, Cassandra, and all the Hadoop, other Hadoop components. Okay, so very high level, very basic concepts, just to understand. And what is your Spark core doing? It's the core functionality of your Spark framework. So all the modules, whatever you run, I mean, you create data frames, you create RDDs on top of each and every component. Everything is going to execute on the Spark core framework only. And Spark SQL is used for SQL and unstructured data processing, structured data processing pretty much. Spark Streaming is for streaming related use cases, machine learning for machine learning algorithms, and graphics for graph related processing. Okay, so we've already seen these things. And so base of what is a Spark core? It's a base of a Spark engine. It's the core functionality of every Spark framework, regardless of what you're executing, what component you're using. Everything gonna get executed on this Spark core itself. And this is where your RDDs will get created. So RDDs are unified across all the other components, your machine learning or Spark SQL. So once your RDD is created, that posted on Spark core, and you can access it through any of the other modules. And there is some introduction given to Spark SQL, how this SQL is gonna work. Anyway, we're gonna deal with Spark SQL in the details. How do we create a Spark SQL component? How do we create a data frame? How do we can load all these kinds of different data files and create the data frames on top of it? How do we access them? Okay. So Spark Streaming, there are some limitations, I can say. Okay, so this is mainly used for the streaming applications. So Kafka is better used. I mean, Kafka is preferred over Spark Streaming for some of the reasons. I'll let you know what are the challenges that you have when interacting with the other third-party tools. See, Kafka can easily interact with the third-party tools using an API call. So it has got some built-in connectors also. And the advantage, the most important advantage that they have is there is some kind of a component called as Confluent Kafka. Have you heard about it? Confluent Kafka. There is a company called as Confluent, which is providing a licensed version of Kafka with better features and better connectors. So you need not write any code, or you need not build your code in Kafka components. So Confluent itself has got its own connectors to different mostly used systems. So that is one advantage we have over Spark Streaming, but that's a paid tool. Again, Spark Streaming is an open source, definitely. So if you see the categories of Spark components on the storage side, it can be anything. It can be HDFS, it can be a standalone node machine, and it can be a cloud storage, or it can be an NoSQL RDBMS storage. So depending on whatever the storage requirements you have, you will be selecting any one of it. So it need not be only HDFS. It can also be hosted on any of the cloud enterprise. So for example, you have hosted it on an AWS cloud. So your storage will be an S3 bucket. Okay, so you'll be pointing some location in the S3 bucket to the Spark framework, and it will keep using whatever the storage you have there. Okay, so you'll be building a system on an EC2 machine or an Azure VM. You'll be hosting the Spark application on an Azure VM, and the storage allocated for that Azure VM will be your underlying storage for your Spark framework also. Okay, so guys, am I deviating? Is it clear? Is it making sense what I'm talking? This is all very high level information. There is nothing in detail where we can get into. Okay, so how Spark is being deployed, how Spark can be used, all that things. Okay, so same thing we are kind of repeating. Okay, so there are some repetitive slides available. So let's just quickly move on. Are we clear, guys? Any questions do you have? Let me clarify once again about that. But I mean, for now we can continue. Okay. So the cluster management, Spark scheduler is one. Hadoop Yarn, how we manage the nodes in the cluster, and Apache Mesos. So Mesos we have not used it before anytime. I've not worked on a Mesos cluster, but Hadoop Yarn and Spark Scheduler around we have used it. And the core execution engine will be the Spark core, right? And on top of it, we have this different modules, different libraries: Spark SQL, machine learning, graphics, and streaming. And the programming languages are the Scala, R, Java, and Python. Okay. So on the storage side, or where you deploy Spark is depending on what storage you get, or what the cluster management you're gonna get. So generally we have the deployment done on the cloud systems. Like I said, it's going to be done on a particular VM. Okay, so if it is an Amazon AWS, you have this EC2 instances, you deploy Spark on top of it. And if it is an Azure related environment, you have this Azure VMs posted, right? So similarly for GCP, you have this Dataproc environment. Okay, so in AWS, you have got also another feature, whereas this is EMR, Elastic MapReduce, wherein you build the cluster. The AWS instance, the AWS itself will build you a cluster with Spark, and it will take care of all the installations and everything. You don't have to worry about that admin related stuff also. So when you define an EMR cluster, it's something like it's going to create a Spark installation and it's going to give you the access. So all the setup, everything will be done by the AWS itself. Okay, so there are different ways of ways how you can execute this Spark applications, different environments where you can execute the Spark applications. Okay, and then we have the Spark architecture. So there is nothing in detail. There are two things again: master and a slave. So cluster manager is going to be the master, and worker nodes are the slaves. Where in the worker nodes you have these executors, multiple executors running the individual tasks. Okay, so for each and every executor, you'll have a cache memory. This is the in-memory component, wherever the frequently running outputs or frequently running data frames will get stored into the cache. And the driver program will have the actual code, whatever the Scala or the Python code where you have written the program, and you'll be submitting that driver program to the cluster manager. So once you get access to the cluster manager, it will interact with the worker nodes. Whichever worker node is available, it's going to allocate this particular program to run on the specific worker node. So now for a driver program, so when you are actually defining a driver program in the actual Spark program, what you're going to do is you're going to create a Spark context. So that's the initializing, that's starting point for any Spark application to run. Okay, so you'll be creating a Spark context in the driver program, in the Spark program. And when the workers are allocated for your program to execute, you will execute this Spark context. So you'll execute these kind of operations on top of this worker nodes directly. Okay, so there are two ways again: this driver program or this client. I can say this entire thing as a client. Okay, so this driver program can work on the client side, or it can work on the cluster side. So whatever the program I have, it can stay away from the cluster manager. It can stay away from the architecture of the cluster of the Spark, and it can work independently as in from the client node itself, wherever from wherever location the client is submitting the program. From that mission itself, it will start executing, it will start using the worker nodes, and it will start executing the program. Other way of doing it is you move this driver program to the cluster manager, and it will be available locally to the Spark environment, and it's going to run the whatever the Spark program that you have defined. So in both the cases, so the driver program is in one scenario is in the client location, one in the other scenario the driver program will be in the cluster manager within the Spark environment. So that the only difference it's going to make is when it is available, when the program is available in the client location, you are not supposed to disconnect. You are not supposed to get disconnected from the Spark framework, from the cluster manager, because it has to be intact, because the program itself is in the client side. But whereas in the other mode, in the other way of execution, the driver program will be available within the cluster manager. So your client can get disconnected from the Spark framework. Even if it is getting disconnected, your program will still run as usual, because the driver program is available within the cluster manager. So there are different modes. We'll get into the details, but this is how we will be running your Spark program. Okay, so in the program, you will be defining the Spark context. That's the initializing point for any of your program to run, which interacts with the cluster manager. Cluster manager will identify the list of available worker nodes, So those worker nodes will be allocated for your Spark program, driver program to run. So generally, if you are talking in terms of a single node, if it is a standalone node Spark environment, if your Spark is set up on a single machine, then your cluster manager, worker node, everything will be the same machine, and whatever the RAM you have for that particular machine will be considered as a will be divided into this worker nodes. Okay, will be used for executing this particular program. Okay, so we will get into the details of each and every component here. So there is a Spark application, a user programs which is built on Spark. Applications are a container having a Spark application, a Spark driver program, a program that runs the main function for a Spark application, a cluster manager, a service to acquire the resources, and the deployment mode, the configuration on which the driver process runs. Okay, so what is this worker nodes? A node that executes the applications. And what is this executor? And what is his job? What is his task? So similar, I mean, very known terminologies for I mean, we have been talking in terms of the same terminologies, a cluster manager, whatever the program it is. I mean, if it is an application jar, you are converting that program into a jar file and submitting it. That's the only difference. And Spark executor, what is a job? What is a task? Right? All these things we have heard. And the deployment modes is a standalone deployment, and Spark on Apache Mesos, and Spark on Hadoop Yarn, on EC2, and on Kubernetes. So we have already seen, or we already know what is this Spark standalone means, right? It's a standalone cluster where you have installed your Spark cluster on your own machine, okay, on your separate individual machine. And Apache Mesos, it comes along with the Apache Mesos component. We are not sure about what this Mesos is all about. We've not used it before. And Hadoop Yarn, we know how we can deploy Spark on top of the Hadoop environment using Yarn resource management. We will be executing the applications. And on EC2, this is using the cloud instance. On AWS Amazon EC2, you'll be launching a Spark application. You'll be launching the Spark installation. Like I said, this also comes along with the EMR cluster. This is not an EC2 basically. You can call it as an EMR, where the Amazon itself will launch a Spark cluster for you. It will launch a Spark cluster. It will create a Spark cluster, and it will be configuring everything. All the applications and everything will be configured and will be handed over to you. So that basically is an EC2 instance only, but when you install Spark and everything, when you configure everything, we call that as an EMR. Okay. So how many of you are aware of this terminology, EC2, EMR, AWS related cloud instances? Have you heard about these things before? Do you know what is a VM, a virtual machine? A virtual machine. Virtual machine is something which is virtual, and you've got some RAM and you've got some storage for it. Okay. So there is a machine which is available remotely to you. Okay. So using some IP address, you'll be connecting to that machine and you'll be executing your tasks. So instead of you running the programs on your own machine, you'll be connecting it to a remote machine. Okay, so that's what we call it as a virtual machine. So if the machine is hosted on an Amazon cloud, AWS cloud, that instance we call it as an EC2. So EC2 is nothing but it's a virtual machine. It's a machine which is hosted on cloud, Amazon cloud. Okay, so every EC2 instance, when you're configuring it, you will have the privilege or provision to specify the amount of RAM you wanted to allocate, or the amount of storage you wanted to allocate. Okay, so this is how we will be defining and we'll be creating a virtual machine on Amazon or Azure or whatever. So on Amazon, we call it as EC2, and on Azure instance, we call it as Azure VM. That's it. That's the only difference. So ultimately, what is it? It's one machine which has some amount of RAM and some amount of storage for it. So instead of you doing it on your own machine, which is a physical machine available that to you, instead of you doing it on your own machines on premise, you are connecting to a cloud machine and interacting with or running applications on top of it. So now you understood what is EC2. It's a virtual machine which is hosted on an Amazon cloud. Similar to EC2, you have Azure VM, which is hosted on Azure cloud. That's the only difference. And I have used a term called as EMR, right? So what is this EMR? EMR is also a neat EC2 machine only, but the only difference is it comes with a Hadoop installation, or it comes with a Spark installation. Okay, so if you select an EC2 instance, who has to do the installations? You have to do the Hadoop installations or Spark installations. If you select an EMR instance, it will give you an EC2 instance with installations done by Hadoop, by Amazon itself. Okay, Amazon itself will take care of the installations and it will give you it. So both are the same, EC2 instances only, both are the same virtual machines only, but one is Amazon itself is doing the installations, it's creating a cluster for you and giving it. And on the other hand, if you wanted to manage it, if you wanted to create it, you can do it by taking an EC2 instance alone. Now you have some clarity, idea, better? Same thing, if you are migrating to GCP, there is a virtual machine instance, we call it as. So the same thing. Again, you configure whatever the requirements, whatever the cluster storage you want, you can configure and you can create your instance. So how do we connect to those EC2 instances or Azure VMs? Is using an IP address. Using an IP address and a key. There is a PPKP P and key files available using which you can connect to it. Okay. So right, so this Spark can be deployed on all these things. It can be deployed as an individual machine, standalone machine on Apache Mesos, or it can also work along with Hadoop Yarn for the resource management component. It can be deployed on an Amazon EC2, and it can also be deployed on a Kubernetes environment. So using some Docker containers, you'll be deploying it on a Kubernetes environment. Using some YAML file, you'll be deploying it. Okay. Are you aware of this Kubernetes? Have you heard about it? So Kubernetes is some kind of a container related approach. So you'll be installing Spark in the form of a container. So it's easy to deploy on different instances. It's not environment dependent. So you can deploy it anywhere you want it to. So the same version of Spark, the same version of all the environment, whatever the variables you have set, will be generic. And when you have different applications are using the same version of Spark and the environment variables, it can be deployed. It can be it's some kind of a container. You deployed everything and you're keeping it ready. You can take it anywhere you want it to. Okay, so you have some requirement in this particular application, you run it here. You go to a different application, you run it there, and wherever you wanted to, you can maintain the same. You can maintain one single Spark cluster across different applications wherever you wanted to run. Okay. So running Spark applications on Yarn. So forget about whatever unnecessary things that we discussed. See, if it is going on top of it, just ignore. You'll get to know more about those details. But our core feature is like it can be deployed. Our Spark can be deployed on different ways. It can be deployed on a standalone cluster or a cloud VM or wherever you wanted to deploy, you can deploy it. And running Spark applications on Yarn, how do we run the Spark applications on Yarn is you will be setting the master, -- master, you will be setting it as Yarn, and that will use the existing Yarn installations or Yarn cluster management resources to run this particular application. Okay. So how do we run a Spark application? There is something, so launching a Spark application in client and a cluster mode. So this is what I was saying. If you go back to the diagram, I think we have a better diagram available. Yeah. So this is the entire Spark framework that I was talking about, right? So Spark, you have a application master, you have the node manager, you have this containers, you have this executor. So forget about whatever the Yarn related components you have this entire Spark architecture here. Okay. So one way of running your program is you are keeping the Spark driver program inside the Spark environment here. Okay, inside the Spark environment, inside the application master to be very specific. So here your client can get disconnected. Your client can get disconnected from the application, and the program can run as it is. I mean, it won't disturb the execution of the program, even if the client is connected to the application or if it is getting disconnected to the application, because the Spark driver is already available within the Spark framework. And in the other example, the Spark driver, you have it here in the client application. So in this case, as the Spark driver is available on the client application, your client has to be intact with this execution process, with this application master. Okay. for you to able to execute this Spark driver program. So the Spark driver shouldn't be here. Only this particular Spark driver has to be here. So when your Spark driver is on the client side, your client has to be intact with your application master for your program to run. So these are the two things. One is Spark driver working on the client side, Spark driver working on the application side. Okay. So if the Spark driver is on the cluster, we call it as a cluster mode. If it is on the client, we call it as a client mode. That's the only difference. Okay. So cluster mode and the client mode. So where do you specify deployment mode is cluster and deployment mode is client. So depending on what mode you select, your Spark driver will be sitting on either sides, on the client and as well as the cluster. Getting it? So now how do you submit a program? There is a command called as Spark submit. You write some program, you write some Java, you write some Scala or whatever the jar program you define, you convert that into a jar program and then submit this using a master parameter as well as a deployment mode parameter. It will run, this particular jar will run on this particular Spark cluster node. Okay, getting it? So similarly, this is you are submitting using a Spark submit command. So using Spark submit command, you will not log into the Spark shell. You will directly execute this program on top of the Spark cluster. But using Spark shell, you are using the Spark shell. You are navigating to the Spark command line, and after you navigate to the Spark command line, you can run or whatever the commands you wanted to. Okay. So this is Spark submit. There are different parameters allocated to it. So we will look at what each and every parameter is. What is this executor memory, driver memory, deployment mode? What is this master? What is this queue? And all that we will see that one by one. Okay. Now, are we clear with this two deployment modes, the cluster deployment mode and the client deployment mode? Do we have any questions? Okay. So how do we start the Spark shell? There are different ways of starting a Spark shell. You can start a Spark shell with Scala support, with Python support, and with R support. So Scala support, it's going to be a command is going to be spark-shell. For Python support, the command is going to be PySpark. And for R support, it's going to be Spark R. So for our concern, for our in our sessions, we are only going to do a Scala support. So we will always start it with Spark-shell in your environments. So Spark-shell, this is how it's going to be. So some of you might have already seen it. We've already finished the installation for some of us. And using Spark shell, you were able to launch the Spark environment. Okay. So this is PySpark, the same thing, but here you can see the Python version. And in the previous slide, you can see the Scala version somewhere here. Yeah, using Scala 2.11, using Python 2.7. And similarly for Spark R, you can see whatever the version of Spark R it is running, and it's going to open a R shell. Okay, so that's the only difference by running it in different modes. Okay, are we clear? Okay, so now we will look at some of the arguments that we have. There are different arguments that we have passed while submitting the applications. So firstly, what is the master? Like we discussed, master can be your standalone node where you can give the host name as well as the port name, or it is a Mesos, Apache Mesos cluster with a specific host and port. It can be a yarn or it can be a local machine. Okay, so depending on what deployment you have done, you can specify whatever the master URL. Okay, then deployment mode, hyphen deployment mode will be a client mode and the cluster mode. We have seen these two parameters already. What is client mode and what is deployment, what is cluster mode. And the class name, whatever the application main class, whatever the program you have written, whatever the main class name you have, you will be specifying the class name. And here in the jars, you will be giving the jar file name. Okay. And the name, you can give any specific name for the application. So this is only required for you to identify in the web UI. So after you submit this application, in the web UI, you can see the list of applications that are running. So you can differentiate using a specific name by giving a specific name to it. Okay. So this is one, these are some of the arguments. And in addition to that, we have files. So comma separated list of files to be placed in the working directory of each executor. So whatever the files, whatever the input file locations, or whatever the output, for example, if I'm giving an input file or an output file path, you can specify the input file name and the output file name, it will get created. And there is a configuration parameter, whatever the property and whatever the value. So conf -conf can take a lot of values. There are a list of values which it can take. I'll take you through the different values which it can execute. So the property name and the property value. So you can give any number of properties for that matter under -conf. Okay, so this varies from application to application if you are interacting with a different third-party tool. So whatever the parameters that you want to set with that third-party tool will be listed everything using a -conf only. And there is a property file. You can navigate it to spark-defaults.conf. If this is not available, if you want to use a some other property file, if you want to give some extra properties, you can create one own property file and you can give the path of that particular thing. So by default, it's going to look for spark-defaults.conf only. If you want to update some additional properties to it, you can add this to the existing property file, or you can also create one new property file and you can launch it. And the proxy name, just to give some name for your application. And -help will give you the list of commands and the usage for each and every command. And version will give you the version of current Spark application that it is running. Okay, and then Spark context, like I said, it's going to be the initial step, the beginning of any Spark application is going to be using a Spark context. So Spark context is kind of an initial piece of execution to your Spark application, whatever the application that you're trying to run. Okay, so by default there is a SC Spark context that is getting created when you launch the Spark shell. So you can use the existing Spark context, or you can also create your own Spark context for a different set of applications if you are trying to run. Okay, so by default, SC is the Spark context which comes along with your Spark shell. Then, like you can say, you can also create a Spark context, explicit Spark context, by using some of the configuration properties. So here the configuration properties are the application name I have set and the master I have set, local application mode. And you're creating a Spark context here using this property files, using these properties. So you can define whatever the properties you wanted to. You can add all these additional properties here, and you can create your own Spark context. Or you can use the existing Spark context which is coming along with your Spark version. So this is coming from the recent versions. In the earlier versions, we used to create the Spark context by default. We used to create a Spark conf and then used to create a Spark context. Okay. Then what are the configurations it can take while you're creating the configuration file, configuration properties? What all the parameters it can take? It's it's a beginning step of your Spark application. Okay, so it's some kind of a door for your Spark framework to a Spark application to execute. Okay, so you have written a program. So where do you execute it? You have to execute it within the Spark environment, right? So how do you execute it? With the help of Spark context, you'll be allowed to run this program on top of the Spark framework. Okay, so it's an initialization for every program to run on your Spark framework. We'll create one Spark context and we'll be running Spark programs using that Spark context only. So by default, it comes with SC, so you can run whatever the applications you wanted to use in this Spark context. See, again, there are two ways of doing it again. So if you have logged into the Spark shell, now you're already available in the Spark shell, right? And you already have a Spark context with the name SC. Okay, so you already have a Spark context. So now you can run whatever the commands. I mean, you will be running SC dot so and so read operation, so and so write operation, or whatever, right? So you can run whatever you want with this SC. But when you are submitting the programs externally, that means without logging into the Spark shell, you have written a program, you have written some Python program, you have written some Scala jar, and you wanted to submit it explicitly. So those will be multiple Spark contexts will be getting created for each and every application. So when I'm saying I'm creating an application, there will be a Spark context getting created for this. I'm submitting another application, there will be another Spark context getting created for it. Getting it? So using this Spark submit, whatever the commands I'm executing is kind of an external what I'm saying is an external way of running a program on the Spark application, Spark framework. Okay, so in simple terms, let's say I'm using Spark context to establish some kind of a connection to the Spark cluster. Okay, so now I have a Spark cluster available. I have a program available. Using Spark context, I'll be connecting to the Spark cluster and I'll make sure this application is run on top of that Spark cluster. Getting it, Spark context will help you connect to the Spark cluster and execute your applications in simple terms. Are we clear with this now? So now I logged into a Spark shell that created a Spark context. That means that created a connection for your Spark cluster. So using that Spark connection, now I'll be running all the applications. I'll be running all different processes. Okay, so I don't have to create a Spark context now because already a connection has been established and you're already inside. But when you are running the programs externally without logging into the Spark shell, you have to write in the program, you have to write a methodology, you have to specify some parameters. So now I wanted to establish a connection. What parameters I should use? I should use all these parameters. How much memory I should allocate for this connection? How much executor memory I should allocate for this connection? What is the local directory that it has to look? What is the configuration folder that it has to look? What is the name of this connection I have to give? So all these parameters I'll use. I'll call this as a configuration parameters. Using that configuration parameters, I'll create a connection. I can say SC1, okay, for application 1. I created some SC2 for different application. I created another connection SC3 for different applications. So all this is gonna hit on the same cluster. But what parameters or what configurations they are using for different connections is different. Got it? Fine. So this is it. So here I'm establishing a connection. So I have already got the Spark context created with some set of parameters. This is master is local and application ID I receive. And explicitly, how do you do it? I'll be creating your own configuration parameters, and using that configuration parameters, using this conf, I'll be creating a Spark context here. Right. So what all configuration parameters you can give is listed in this particular this thing, whatever the sheet. Okay, application name you can specify, the driver memory, the executor memory, how much memory you can allocate for the driver, how much memory you can allocate for the executor, what's the difference between this driver and executor, we'll discuss that in detail. And what is this local directory, what is a log directory. So everything you can specify. These are all optional. There is not nothing is mandatory component here. Master you can specify what master you have to specify to. If you want to, for example, I want to run this particular application on yarn system. Okay, I'll create one Spark context. I'll be specifying that configuration as master as yarn. So this particular connection, this particular application is running on yarn. Let's say I have another connection. I want to run it on Mesos. I'll give the host name. I'll give the port name. So different connections running on different modes of execution, different execution modes. Okay. So deployment mode, you can specify either client or cluster. For every application, you can specify whether it want to run it on client or a different cluster. And the class path and the jars and the UI port. So this is by default going to be 4040. So when you open the web UI, for every application that you are running, there will be a URL that is going to get generated. When the execution is happening, there is going to be a URL. So if you click on that URL, it will take you to the application statistics. So how the application is getting executed, what are the logs, or what is the progress of the application. Otherwise, there is also a default URL, default web URL for your Spark that is available on 8080 or 8081. I'm not sure. So there is a conflict between these two. 8080 is the default value. But if you already have some applications running on it, then you can specify, you can change it to 8081 or 8082, whatever. Okay. So I can also show you the default web UI. In the default web UI also, you can list out all the running applications, all the completed applications, all the failed applications. So why is it failed? You can also check the logs and statistics of it. Okay. And again, for each and every application, you'll also be getting a URL separately. Okay. Right. So web UI 4040, this is 8080 actually. I mean, whatever the configuration in 3.1.2, whichever we are using, is 8080. And there were some problems with this 8080 port. I mean, 4040 is maybe the older URL. So in 8080, there might be some problems because there are many applications which use the same port number. Okay, so if your local machine is already running some other application on 8080 port, then it's going to throw you an error. you have to get into this Spark configuration folder and you have to make the changes. You have to change it to some other port name, 8081 or 8082, whatever. Okay. So this is how your UI will be shown. All the completed jobs, all the failed jobs, and all the statistics when it is submitted, what is the time it has taken, how many steps it has, and you can see all the information in the Spark Web UI. Okay, is that fine? Yeah. So commands to launch Spark daemons. There are multiple daemons. A master there, slave is there, and you can start them by running this start all.sh. Right, so using start all.sh, your Spark cluster will start, and then you can navigate to the web UI and you can see the UI page. Okay, so there will be no applications that are submitted. Zero, everything is zero. You can just go through what are the list of completed and successful applications. Okay, clear? So I'm using a version, so you can check ls cat conf spark env.sh. This is my environment.sh file, and this is where your Spark web worker web UI port or the Spark master web UI port you have to edit. Okay, you have to make the changes to this file to be able to point to a different directory. And let's say I'm navigating to bin, or sorry, I'm navigating to spin ls and start all.sh. This will start the master as well as the worker nodes. Okay, so do a JPS, it will list you the Spark master as well as the Spark worker. So after you do this start all, you may navigate to a browser. I'm sharing my screen. So just refresh this page, and 8081 is a port that I allocated, and it is running on this particular node. Okay, so the running executors, you can just navigate to the master. This is running on 8080 port. This is your Spark master IP, and the number of workers is the same. Again, the same machine is being allocated as a worker, and running applications and completed applications. So this is how your master web UI or the worker web UI will be listed, will be shown. Getting it? So for you to just check what parameters I have updated, what parameters I have made changes to. So cd, okay, so cd bin Spark shell will launch your Spark shell with the Scala version. So guys, even I'm using a different version of Spark here. So my Spark version is 3.2. One second, let me check. It is 3. What is it? Yeah, Spark is 3.1.2 and Scala is 2.1.1, but Hadoop is built on 2.7 only. Okay, so even then I was able to load because my latest Hadoop version is around 3.1.2. Okay, so I was able to load. I didn't have any problems with it because I have done Spark installation first, and then on top of it I've installed Hadoop. Okay, so the both are independent. There is no interlink between those Spark as well as the Hadoop. So both are working fine, PySpark as well as Spark shell. So I would request you to downgrade or upgrade the Hadoop version, Spark version, and or else if I mean, as we don't have anything to do with Hadoop, you can just remove all the parameters or values that are set for Hadoop. Remove the entire directory itself and just change the Hadoop home. You can even remove the Hadoop home. There is not required at all. So if you look at cd sbin, so if you look at cat start all, there is no parameter required for Hadoop home. So the only parameter that it's taking is Spark home, right? So it's not required at all, Hadoop home. So I would suggest you to do this better. Okay, so the Spark 1.3.1.2 version, and we have downloaded the 2.7 Hadoop related tar file, So that's fine. Let's be it with it. And you just remove the entire Hadoop setup, remove the Hadoop setup and remove the Hadoop home from the environment variables. Is that fine? So here on the downloads, maybe you can get into the archive. This will give you all the other pages also. So 3.1.2 is what I'm using. Just navigate to 3.1.2. Here's this page. This one. Not this. Here, yeah. So here from disk to Spark, I'm navigating to 3.1.2, right? So 3.1.2 and 3.1.2 built on top of Hadoop 2.7. This one. So try downloading this file. This is the file which I have used for my setup. And the WinUtils, where do we get the WinUtils? Okay, this is 2.2.1, 2.7. Okay, so fine. Windows WinUtils. Not this, not this. There should be a GitHub repository. Fine, I can get it from here also. So just scroll down. This is a page that we have used, right? Let me take another one. So scroll down and you will find a WinUtils directory path here. So as you can see, these are not verified GitHub repository page. So there is someone named Steve. Let's see how many downloads have been done. There are 2.1 stars. So it's not a verified thing, but we can still use it. That's okay. So this is a WinUtils file. So do you have this path? You have to download this file from here. Okay. So this is one path, and there is one more. Let's see what is the other guy telling. Scroll down. WinUtils. Where is it? This is done. This is done here. So you can see there is another guy. This is a CEDAR lint. Right, only 1.1, 36 watching, 1.3k folks. So here we have 2.7 inside the bin folder. Do we have a bin folder directly? There is no Hadoop 2.7.0. So 2.7.2 is available. So fine, just try using any one of these files. This is not a proper version, but let's see.
Just a quick info guys, if you want to make a career in big data, then Intellipaat provides an advanced certification in Big Data Analytics by ENICT Council IIT Guwahati. It is taught by IIT professors and industry experts. With more than 10 years of experience, this course is designed to upskill and land your dream job.